Now what we will do, we will pass xt capital for each keyframe and any input for each keyframe through our Stable Diffusion model, and we will do reverse diffusion to generate these images. Okay, let's do that. Here we created this very simple function. The name of it useSD. This function has many arguments. The first one is the scheduler that we want to use with our Stable Diffusion model, and the latent and the canny input, the width and height of our image that we want to generate, text condition, keyframe number, and here we have first time step argument, and here we will make it by default equal to the first time step t capital, but if you want you can start with different time steps. Okay, now we created this loop for t in scheduler.time steps. First time step colon. Here we will pass it through time steps. We will start with our first time step and we will move on to time step 0. Okay, now what we will do, firstly we will take this argument latent, we will put it in this list and we will multiply this list by 2, which means that the resulted list will have 2 elements like this. Okay, and we will concatenate these 2 elements together. Actually here we will put these 2 elements on the batch dimension, but why we did that? We did that because we want to do classifier free guidance, which will make us able to define the guidance scale and use it to control the importance of the prompt in the generated image. And we will put the result in latent model input. Now what we will do, we will pass this latent model input with the current time step t through our scale model input or scheduler.scale model input, and we will get latent model input. Now we will prepare our canny input so that we can pass it through our control net. So we will do the following: control net condition equal to pipe.prepare input, and here we will make image argument equal to canny input, the width equal to the width, and the height equal to the height, and we will make batch size equal to 1, and the number of images per prompt equal to 1, and here we will make dtype equal to torch dtype, torch dtype. Okay, now here is our control net condition. We will also multiply it by 2, and here we will concatenate them together, and now we will have this control net condition. Now we will use our control net, so we will type with torch.noGradient, when here we will type down block res samples, comma mid block res sample, which is equal to control net, and here we will pass our latent model input, the current time step, and here we will make encoder hidden states equal to the text condition, and the control net condition equal to control net condition, which is this one here, and return dict equal to false, and conditioning scale equal to 0.7. Okay, we will take these 2 things here and we will pass them to our network. So here we will type noise production equal to network, and here we will pass our latent model input, and here we will pass the current time step, and we will pass the text condition. We will make encoder hidden states equal to CP, and we will make down block additional residuals equal to down block RES samples from our control net, and we will make mid block additional residual equal to mid block RES sample from our control net, and we will make return dect equal to false. And here we will open these square brackets and put 0 between them. Now we have our noise prediction, our predicted epsilon. What we will do here we will do classifier free guidance. Here we will type noise prediction and conditional. Actually, we used our negative prompt to find this noise prediction and conditional. And we have noise prediction text. This one, we used the positive prompt to create this one, which is equal to noise prediction.chunk, and here we passed 2. Now what we will do, here we should specify the guidance scale. Let's make an argument here, which is guidance scale, and let's make it equal to 0.6, okay? And you can change it if you want. And yes. So here we will type noise prediction equal to noise prediction and conditional plus guidance scale times noise prediction text minus noise prediction and conditional. Now what we will do here, we will move one time step backward. So we will type latents equal to scheduler.step or latent equal to scheduler.step, and here we will pass our noise prediction tensor, our current time step, and our latent tensor, and we should type dot previous sample, and we will repeat this loop again and again until reaching time step 0. And after reaching time step 0, what we will do, we will multiply our latent with 1 divided the variational auto encoder scaling factor. It's something important to create the final image. So now we have our new latent. Here we will use our decoder, so we should type with torch.noGradient, and here we will pass our new latent through our decoder, and we will get our new images or our new image. And here we will make the highest possible value inside the new images equal to 1, and the lowest possible value in this new images equal to, and this new image equal to 0. So we will type the following: new images equal to new images times 0.5, and we will add the result to 0.5 dot clamp, and here we will put 0, 1. And now we will send our new image to our CPU, and we will change the order of the dimensions inside this tensor. We will keep the first dimension as it is. We will make, here we will put the channel dimension at the last, and here we will put the height and the width dimension. Okay, and we will convert this tensor into an NumPy array, and we will multiply this tensor with 255, and we will convert the type of this array to unsigned integer 8. Now what we will do, we will pass this new image through our image.from array, and actually we have just one image, so this list will have just one image. And now we have our image. We will save this image inside our output keyframes folder, which is this one here. And the name of this image or this frame, it is equal to the keyframe number. So here we will put keyframe number.jpg. So here the path of the file is output keyframes slash the keyframe number.jpg. And here we will also return the latent, this one here. We have one thing we should change here in this function. We will make first time step equal to 0, okay? Here we want the index of the first time step, not the first time step itself, okay? Yes. Now what we will do, we will create these two variables, latent directory variable. This variable will have the directory of the folder that we put our latents inside it, which is keyframes latents folder. And we have this variable, Kenny directory variable, which represents the path of the folder that we put our Kenny inputs inside it, which is Kenny inputs folder. And here we will create this function, generating new frames function. This function has 3 or 4 arguments. Latent directory argument, which is by default equal to this directory, and Kenny directory, which is by default equal to this directory, and width equal to the width of our frames, and the height by default it is equal to the height of our original frames. Now what we will do, we will extract the names of the latents from the paths of the latents. So what we will do here, we will add this directory, latent directory, to this part here, and this glob.glob will return all paths of our latents, and we will pass it through each path, and we will extract the name of the latent, and we will convert it into integer, and we will do this thing for all latents paths, and we will put them in this list. And now we have this latents names list. We will sort all the elements inside this list from the first keyframe latent to the last keyframe latent. And we will do the same thing here to get Kenny inputs names. We will use a glob.glob method to return all the Kenny inputs paths, and we will pass it through each path, and we will extract the name of each Kenny input, and we will convert it into integer and add it to this list. So now this list will have the name of each Kenny input in our Kenny inputs folder. Okay, now we have this Kenny inputs names list. We will sort the elements inside this list from the first Kenny input to the last Kenny input. Now what we will do, we will pass it through each latent name in our latent names list. Okay, so now we have this current latent name. We will create the path of this latent by adding our latent directory to this part here, which is a slash, and here we will put the name of our latent.pt. So now we have this complete path for our latent file. We will put this path in this variable current keyframe latent path. And we will also create the path of the current Kenny input. We will add this Kenny directory to this part here, slash current latent name, which is similar to the current Kenny input name dot jpg. And now we will put the path in this variable current keyframe Kenny input path. Now we will load our Kenny input using load image method. So we will type Kenny input equal to load image, and here we will pass current keyframe Kenny input path. And here we will load our latent tensor. So we will type latent input equal to torch.load. As you know, it is PyTorch tensor, so we should use torch.load. And here we will pass the path of our latent file, which is current keyframe latent path. And we will send our tensor to our device like this. And here we will use our useSD function. We will pass our scheduler, and we will pass our latent input and our Kenny input and our text condition, our current latent name, okay, and the width and height that we want, and the guidance scale, and let's make it 7, and our conditioning scale, and let's make it 0.7. It's a good idea to choose a number between 0 and 1 for this argument. And here we will make this first time step equal to, for example, 0. But actually, let's go back to this place here, to this create keyframes. Here we made our T capital equal to scheduler.time steps, and here we open these square brackets and put it 0 between them. We will change this a little bit. Okay, we will make T capital equal to 0, and here we will do the following. We will put scheduler.time steps, and here we will put between these square brackets this T capital. Okay, so now T capital will represent the index of the first time step in our scheduler.time steps list. So here we will copy this and put it here. Okay, so when you change this T capital, you will change the time step that you will start with in reverse diffusion. Now let's run this cell, and here we will call our function generate new frames function. And here we made our guidance scale equal to 9 and conditioning scale equal to 0.8, and here is the result. Here is the first image. It's good image. And let's see the other image. And here is another image. As you can see here, there are a lot of differences between the first and the second image, and that's a problem for us. Let's move to the third image. Here's our third image, which is also different from the previous images, the previous keyframes, and the same thing here. This frame, this new keyframe, it is different from the previous new keyframes, and the same thing with this new keyframe, and this new keyframe, and this one, and this one, etc. When we use these keyframes to create our video-to-video animation, the video that we will generate, it will not be good. We will not see any consistency in our new video. So we need a way to make these new keyframes have the same style and have some kind of consistency between them. In other words, we want to reduce the flickering. We want to fix the background. We want to make these new keyframes share the same global style, okay? And we want to make sure that the person in this frame, for example, in this new keyframe, similar to the person in the other keyframes, in the other new keyframes. In the future lectures, we will learn how to do all these things. Thanks for watching. Hi, in this lecture we will learn how to generate new keyframes that sharing the same global style using cross-frame attention method. What is the meaning of global style? It is just the general idea behind the image. When your keyframes sharing the same global style, it means that these keyframes will have the same colors and the background will be a little bit similar, which is something important to create our video-to-video animation. Now, what is cross-frame attention? We said previously that inside our U network, there are many attention blocks. And inside each attention block, we have self-attention layers and cross-attention layers. And we talked previously about what is self-attention layer and a cross-attention layer. Let's say, for example, that we passed this latent through our U network, okay? And we reached to this layer here, this place. And let's say that the feature map that we want to pass through this layer here, it is this one here. And here is the size of this feature map, 4 times 4. We didn't put a depth dimension here for simplicity. Okay? Now, this layer here, it is, let's say that this layer here, it is self-attention layer. This layer will do the following. Firstly, it will extract a Q vector for each pixel in this feature map. So we will get Q vector for this pixel and this pixel and this pixel, etc. Okay? And this layer will also find a key vector for each pixel here. K1, K2, K3, etc. And this layer will also give us a value vector for each pixel in our feature map, our input to this self-attention layer. So we will have a value vector for this pixel, V1, and a value vector for this pixel, which is V2, and a value vector for this pixel, V3. And we will use all these things to find the contribution of all these pixels in this pixel, and the contribution of all these pixels in this pixel, and the contribution of all these pixels in this pixel, etc. Here in cross-frame attention, we will not find the contribution of all pixels of our feature map in each pixel in our feature map, but we will find the contribution of the pixels of different feature map in each pixel in this feature map. To make things more clear, let's say that we have two frames, two latents. Here's the first latent, xt sub 1, and here's the second latent, xt sub I. These latents, they are different from each other. We created this latent from keyframe 1, the first keyframe in our video, and we created this latent from the current keyframe, keyframe I. Now we will pass this latent through our U-network, and we reached to this place here. Okay, and now we have this feature map, and now we will pass this keyframe through the same U-network. Okay, and we reached also to this place here, and we have also a feature map in this place here. The size of this feature map similar to the size of this feature map, but of course with different values, because here we created this feature map by passing this input, and we created this feature map in this place here by passing this input, and these two inputs, they are different from each other. Now let's say that the feature map in this place here, the input to this self-attention layer, it is this feature map with this size, which is similar to this size. Our self-attention layer in this place will also find a Q value and a key value and a vector value for each pixel in this keyframe. Here I will say that this feature map here, it is the feature map that we will pass through this self-attention layer here, and now we have the Q vectors and key vectors and value vectors that we will get from the self-attention layer here for this feature map. And I will say that this feature map here, it is the input to this self-attention layer here. Our self-attention layer in this place will also create a V vector, Q vector, and key vector for each pixel in our input feature map. But here we will just focus on the key vectors and the value vectors. Our self-attention layer will create this value vector and this key vector. Okay, and it will create this value vector 2, and this key vector 2 for this pixel here, and it will also create this value vector 3 and this key vector 3 for this pixel, etc. As we said previously, we will find the contribution of all these pixels here in this feature map that created by passing this latent, the latent of the first keyframe, through our U-network. Here, to compute the contribution, what we will do actually, we will take the key vector and the value vector for each pixel in this keyframe. Okay? And we will take just the Q vectors from this feature map. We will multiply the Q vector for this pixel with all these key vectors in this feature map to find the attention matrix. And after finding the attention matrix, we will multiply this attention matrix with all these value vectors. Okay? By doing this, you will make all these pixels here contribute in the pixel that we will get from this self-attention layer. And here it's like that we asked about how much each one of these pixels in this feature map is related with the first pixel in this feature map. And we will compute the value of the new pixel by using these relations, or in other words, we will do weighted sum of all these value vectors. And this is our new pixel. And we will do the same process for all these pixels in this feature map. Pixels. And here actually we are trying to transfer the global style inside this keyframe, the first keyframe, to this current keyframe. Okay? And we will do the same thing with this pixel here. We will take the Q value of this pixel and we will multiply it with each key value in this feature map. And we will apply the softmax to find the attention matrix, and we will multiply it with all these value vectors in our feature map, in this feature map, to create a new pixel here. The vector that represents this pixel will be the weighted sum of all value vectors, and as you know, based on the attention matrix. The value vector in this feature map that has strong relationship with this pixel here, it will have large effect on the final vector, or in other words, our new pixel. And that's it. That's what we mean by cross-frame attention. Okay? Here what we will do actually, we will take the key vectors and value vectors from our self-attention layers in the decoder part of our U network. This one we call it decoder part. Okay? So we will take all key vectors and value vectors from all self-attention layers in this decoder part of our U network. These key vectors and value vectors, they created by passing the latent of the first keyframe. And we will take just the Q vectors from each self-attention layer of our U network. These Q vectors, they created by passing the latent of the current keyframe. We will use these Q vectors in the decoder part of our U network that we created by passing the latent of the current keyframe with the key vectors and value vectors that we get after passing the latent of the first frame to do cross-frame attention at each self-attention layer of our decoder part of our U network. We will multiply each Q vector that we created by passing this current latent by each key vector that we created by passing this first latent, and we will apply softmax to find the attention matrix. And we will multiply the attention matrix of each self-attention layer with the value vector of the same self-attention layer that we created by passing the first latent. And we will get xt minus 1, which means the latent at time step t minus 1 or time step t minus delta t of the first keyframe. And we will get also xt minus 1 sub I, or the latent at time step t minus delta t of the current keyframe. In the next lecture, we will learn how to do all these things practically. Now let's learn how to do cross-frame attention. Firstly, we should import system package here. Okay, and let's run this cell. Now we will create the hooks that we will put on our U network. We will put a hook on each self-attention layer in our U network, in our encoder part of our U network. When we pass the latent at time step t for our first keyframe through our U network, and when we reach the first self-attention layer, this hook, the first hook, will take the key vectors and the value vectors for each pixel in the input feature map. This self-attention here created all these key vectors and value vectors. For simplicity, let's say that K1 is just one key vector, and V1 it is just one value vector, and K2 it is just one key vector, and V2 it is just one value vector, etc. It's like our feature map, our input feature map has just one pixel. And when we reach self-attention layer 2, our hook that we put it at this layer will take the K2 and V2 from it. And when we reach self-attention 3, our hook that we put it to this layer will take K3 and V3. And when we reach self-attention 4, our hook that we put it at this layer will take K4 and V4, etc. We will use all these vectors to transfer the global style from this latent of the first keyframe to the latent of the current keyframe. Our hooks that we created to take all these K and V vectors, it will replace the K and V vectors at each self-attention layer in our decoder part of our U network that we will get after passing the latent of the current keyframe by the K and V vectors that we took from our hooks previously. These vectors we created by passing the latent of the first keyframe. And when we replace the K and V vectors that we created by passing the latent of the current keyframe by the K and V vectors that we created by passing the latent of the first keyframe and applying the formula of self-attention mechanism after that, this thing we will call it cross-frame attention. Firstly, we will create 3 variables. The first variable is blocks. In our decoder part of our U network, we have 3 blocks. Block 1, block 2, and block 3. We created this list that has the ID of each block in our decoder part of our U network. Okay? And inside each block, we have 3 self-attention layers. So we created this list, attentions list, which is equal to this list here. The first element is 0, which means attention 0. It is the first attention layer in any block, this attention layer will have two layers inside it. We will take just the self-attention layer. And attention 1, which is the second attention layer in any block, and attention 2, which is the third attention layer in any block in our decoder part of our unit work. And here we will create global dictionary. What is the meaning of this? Here we will put all these key and value vectors in a dictionary, and we should be able to reach the values of this dictionary from any place. So it should be global dictionary. It is something similar to what we did to do style transfer previously. So we will make this variable global variables equal to globals. Okay. Now we will pass it through of our decoder part of our unit work. So we will create this loop for block number in blocks, and now we will pass it through each self-attention layer in that block. So we will create this loop here for attention number in attentions list. Now, as you know, we should create a function for each hook. Firstly, we will specify the name of the function. So we will create this variable function name equal to f, and we will put these quotations, and here we will put up block. Why we set up block? Because in the decoder part we call each block up block because it will increase the spatial dimensions of the input. And here we will put the block number. If we are talking about block 1, which is the first block in our decoder, so we will put 1 here. If we are talking about block 2, so we will put 2 here, etc. Underscore. And here we will specify which self-attention layer we are talking about inside this block. We will put attention here, underscore, and here we will put the attention number, which is the number of the self-attention layer that we are talking about. Let's say we are in block 1, and if we are talking about the first self-attention layer, so we will put 0 here. If we are talking about the second self-attention layer, we will put 1 here. If we are talking about the third self-attention layer, we will put 2 here. And here we will use this function to take the key vectors of each pixel in the input feature map to this self-attention layer. So here we will type underscore k, and here we will type underscore hook, and here is the name of the function that we will use to create our hook. Now let's define our function. We will define our function here as a string, and after that we will create to make the generation of the functions that we will use to create the hooks dynamic process. And here is the body of our function. Let's call it function body variable, which is equal. Here we will put f, and we will put all these things here and here. Now we will define our function. We will type define, and we will open these curly brackets, and here we will put the name of our function. Okay, we will put this variable function name variable. For example, if we are talking about up block 1, which means the first block in our decoder part of our unit work, attention 0 k hook. This means that we will create a hook and we will put it on the first self-attention layer and the first block in our decoder part of our unit work. This hook will take the key vectors of each pixel of the input feature map to this self-attention layer. Now let's go back to the function that we will use to create this hook. And here this function will take three arguments: module, input, and output. And we talked about that previously. And here we have also another global variable, which is attGate variable. This variable will specify what is the latent that we passed through our U-network to get the key vectors of each pixel in the input to this self-attention layer. Actually, we don't want to take the key vectors of each pixel in the input to the self-attention layer that we created by passing the latent of the current keyframe. So we change this based on what we want to pass through our U-network. We will not change this variable inside this function, but we will change it from outside. So this variable is a global variable. We will create this variable, key variable. We will use this variable to be able to access to the key vectors of this self-attention layer and extract them from our dictionary or update these key vectors of this self-attention layer in our dictionary. Key equal to system, here we will use system package.getFrame, and we will open and close these parentheses, .f underscore code .co name. Here this one will give you the name of your function automatically. It will give it as a string. We will remove the last 5 characters by typing the following: :-5, and here we will add to our string underscore I1. Now we will check the value of this variable, attGate variable. So if it is equal to I1, it means that we passed the latent of the first keyframe through our U-network, which means that these key vectors at this self-attention layer, they created by passing the latent of the first keyframe. So we will store these key vectors in our dictionary, and we will store it with this name, okay, in our dictionary. If we passed the latent of the current keyframe, at this case I want from you to make the latent. At this case we will extract the key vectors of the self-attention layer that we created by passing the latent of the first keyframe, and we will replace the key vectors that are created by passing the current latent by these key vectors that are created by the latent of the first keyframe. At this case we just need to type return, and here we will type the name of our dictionary and the name that we used to store the key vectors that we created by passing the latent of the first keyframe. And now we will use execute method to create this function. Here it is just a string. Now we will create it. So we will type exec, and here we will pass the body of our function body. Now we have our function. Now we will create our hook. So k hook, it is equal to unit.addBlocks, and here we will pass the block number, .attentions, and here we will pass the self-attention layer number, .transformer blocks, this is not important, .attention1, it is not important also, .2k, and here we will type register forward hook. Here we will pass our function. we will take the name of our function name, and we will type globals, and we will open and close these parentheses, and between these square brackets we will put the function name. So now we passed our function through our register forward hook method. Now we put our hook on this specific self-attention layer in this specific block. We will do this thing for all self-attention layers in all blocks in our decoder part of our U network. Each self-attention layer will have its own function, or in other words, its own hook that we will use to take the key vectors from each self-attention layer in our decoder part of our. Now we will create the hooks that we will use to get the value vectors from each self-attention layer in the decoder part of our U network. And these hooks will also replace the value vectors that are created by passing the latent of the current keyframe by the value vectors that are created by passing the latent of the first keyframe. And here we will do the same thing. We will define a function for each self-attention layer in our decoder part of our U network. We will use these functions to create the hooks that we will put on our self-attention layers in our decoder part of our U network. And yes, that's it. We just need to create function name one variable. Let's call it function name 1, which is equal to f, and here we will put up block, and here we will put the block number and the attention number, and here we will put v, which means that this hook or this function we will use it to get the value vectors. And here we will put hook, okay, and here we will create this variable function body1 variable, and here we will define our function as a string. We will type define, and here we will put the name of this function, and here we have 3 inputs, and we have this att gate global variable that we can use to decide if we want to take and store the value vectors or replace them. And here we will specify the name that we will use to store the value vector for each pixel in our input feature map that are created by our self-attention layer. These value vectors, they created by passing the latent of the first keyframe. And now, so here we will take this part, just this part, and we will add to it underscore I1. Now, if attribute gate equal to I1, it means that these value vectors that are created by this self-attention layer, they created by passing the latent of the first keyframe. So we should store them in our dictionary. And here's the name that we will use to get these value vectors in the next time. Now if we passed the latent of the current keyframe, in this case we don't want to save these value vectors, but we should replace them with the value vectors that are created by passing the latent of the first keyframe. So we just need to type return, and here we will put our dictionary, global variables dictionary, and we will put the name that we used to save the value vectors that are created by passing the latent of the first keyframe. And that's it. Now we will execute this function and we will create our hook. We will call it vhook equal to unet.upblocks, and here we will put the number of the block that we are talking about and the number of the self-attention layer that we are talking about right now, and here we will reach to the value layer in our self-attention layer, this self-attention layer. So we will type .attention1.2v, and here we will type register forward hook, and here we will pass our function. So we will type globals we will open and close these parentheses, and between these square brackets we will put function name 1, okay, which is this one here. And that's it. Now we created our hooks to do cross frame attention. Now what we will do, we will change our use SD function a little bit to make it support cross frame attention. So now we created this function, this new function, use SD with cross frame attention. We will pass to this function our scheduler, our latent that related with the current keyframe, the Kenny input of the current keyframe, the latent of the first keyframe, and the Kenny input of the first keyframe, and the text condition, which is the same in the first keyframe and the current keyframe. And we have keyframe number, which is the number of the current keyframe. We have the width and height and the guidance scale, conditioning scale, first time step. Now what we'll do, we will make this variable att_gate variable global variable, so we can change it from this place and it will change in all other functions that we created previously. Now we will create this loop. We will pass it through each time step, inside each time step, and at each time step we will do the following. Firstly, we will change our att_gate variable and we will make it I1, which means here we will pass the first keyframe or the latent of the first keyframe through our Stable Diffusion model. And here we will prepare our input, and it is similar to what we did previously, okay? But here we will do this thing for the first latent, or the latent of the first keyframe. And we will prepare the control net condition 1, like what we did previously. We will use pipe.prepare image and we will pass our Kenny input 1 through it, okay? And here we will convert it into PyTorch tensor, and here we will use our control net. We will pass all these things through our control net to get down block RES samples and mid block RES samples. And here we will use our U network to get noise prediction 1. Here by using our U network, by passing latent model 1 through our U network, our hooks will automatically get the key vectors and the value vectors from each self-attention layer in the decoder part of our U network. Now we saved all what we want in our global variables dictionary. Now we want also to move one step backward. Now we will move to the time step t minus delta t. So we will type noise prediction and condition 1 and noise prediction text 1 is equal to noise prediction dot chunk 2, and here we will do classifier free guidance, and here we will get latent 1, or in other words it is the latent of the first keyframe at time step t minus delta t. So now we did our reverse diffusion and we have all what we want about the key vectors and value vectors in our global variable. Now we will change our att_gate variable to I, which means now we will pass the latent of the current keyframe. We will do all these things. We will create latent model input I, and we will create control net condition I. We will pass Kenny input I, the Kenny input of the current keyframe, and we will prepare our control net condition I. We will pass them through our control net to get these two things, okay, like what we did previously. And here we will use our U network. We will pass our latent model input I, and we will pass our text condition and all these things from our control net. And here our hooks will automatically replace the key vectors and the value vectors that are created by passing the latent of the current keyframe by the key vectors and the value vectors that are created by passing the latent of the first keyframe. And they will do this for each self-attention layer in our decoder part of our U network, which means that we are doing cross-frame attention. And in other words, we are transfer the global style of the first keyframe to the current keyframe. And here we will do reverse diffusion for our current keyframe. We will extract noise prediction and condition I, noise prediction text I, and here we will do classifier free guidance, and here we will move one step backward. And we have now latent I. This latent, it is the latent of the current keyframe at time step t minus delta t. And when we reach the time step 0, at this case we will multiply the latent of the current keyframe at time step 0 by 1 divided by the variational autoencoder scaling factor, and we will pass this new latent through our decoder, and we will convert the range of the values inside our new images to make it between 0 and 1, and we will send it to our CPU, and we will multiply all these values by 255 to make the range between 0 and 255, and we will convert the type into unsigned integer 8, and that's it. Now we have our image, our new keyframe that has the global style of the first keyframe. We will start with this name. So we will type output keyframes, and here we will put keyframe number, which is the number of the current keyframe, and here we will put the extension of that file, which is JPG. And we can also return this latent 0 of our current keyframe. Now we will use this function, use st with the cross frame attention. Inside this function, generate new frames with cross frame attention. Here we have our latent directory, canny directory. We will pass them through our function, and the width and height also. And here we will create a list of the latents names, and here we will sort the names in this list, and here we will create a list from canny input names, and we will sort the names. We will load our canny input 1 and latent input 1. So we will type canny input 1 equal to load image, and here we will put canny directory, and here we will put the name of the first canny input, or the canny input of the first keyframe. So we will type canny inputs names, and here we will put 0 between these square brackets, and here we will put .jpg. And that's it. Now we have this complete path. We will pass it through our load image, and now we have our canny input 1. Now what we will do, we will load our latent. So we will type latent input 1 is equal to torch.load, and here we will put our latent directory, and here we will put the name of the latent of the first keyframe, which is latent's names, and here we will put 0 between these square brackets, and here we will put .pt. Now we will send this tensor to our device, our coda, or our CPU, and here we will also specify the torch data type, which is float 16 in this case. And now what we will do, we will create this loop. We will pass it through each latent. For current latent name, in latent names, we will do the following. We will create this variable current keyframe latent path and current keyframe Kenny input path. Same as what we did previously. We will get Kenny input for the current keyframe and latent input for the current keyframe. We will send it to our device, and here what we will do, we will use our use SD with cross frame attention function. We will pass our scheduler, our latent input I, Kenny input I, latent input 1, Kenny input 1, text condition, current latent name, the width and the height, the guidance scale. We will make it 9, conditioning scale is equal to 0.8, and first time step it is equal to T capital. Let's see firstly the keyframes that we generated previously. Here is the first image and the second image. As you can see here, the background here, it is completely different, and the colors also. And here's the third image. As you can see here also, the colors are very different. So these keyframes, they did not share the same global style. And this one here, as you can see, the colors and the background, they are very different from the previous keyframes. And this image here and here, and this one is very different. Now let's use our cross frame attention method to see our new keyframes. As you can see here, our hooks are taking the key vectors and the value vectors from our first keyframe, and it will put them in our U network during passing our current keyframe or the latent of the current keyframe. Let's see the first image. Here is the first image or the first keyframe. Let's see the global style now of the second keyframe. Now that's good. As you can see here, the background, it is something similar to the first keyframe. As you can see here, and the colors also, and that's good. Now let's move to the next keyframe, the next generated keyframe. Now that's also good. The colors are good and the background also. It is something similar to the previous keyframe and the first keyframe. Okay, let's take another keyframe. This one is also good. The background, the basic idea behind the background, it is something similar to the first keyframe, the first generated keyframe. Okay, and the colors also, as you can see here. This blue color here, it is also available here. And let's take another keyframe, and this one also good. The background is something similar to the first keyframe, and this one also, and this one also. That's great. That's good, but not enough actually. There are some flickering in the background between frames. In the next lecture, we will learn how to create shape-aware module that will make our keyframes even better. Thanks for watching. Hi. In the previous lecture, we talked about cross-frame attention, and we used cross-frame attention to make our generated keyframes sharing the same global style. Now we want from our generated keyframes to share the same textures and local shapes. To do that, we will use shape-aware module. We talked previously about just this part here. Okay. We did here cross-frame attention. Here we will pass two things to our U network. We will pass xt subscript 1, which means the latent at time step t that are related with the first keyframe, and the second input is xt subscript I, which is the latent at time step t that related with the current keyframe. When we pass this thing, this latent through our U network, we will get this thing here, which is epsilon at time step t that related with the first keyframe. And when we pass this latent through our U network will give us this thing here, epsilon at time step t that related with the current keyframe. Here we will use our shape-aware module in the first time step in reverse diffusion, or in the first two time steps in reverse diffusion. Let's say now we are at the first time step in reverse diffusion, which means that t here is equal to t capital. Here we will check in this place if t it is greater than t capital sub d, which means that we didn't finish the first two time steps yet. At this case, we are at time step t capital, so we are at the first time step. At this case, we will pass this epsilon t subscript 1. Here, we will pass it to this DDIM algorithm. Here, what we will do actually, we will use DDIM algorithm to extract the predicted x0 that related with the first keyframe. But how we extracted this latent here? As you know, previously we talked about DDIM. Okay? And here is the formula for DDIM. xt minus 1 equal to the square root of alpha bar t minus 1 times the predicted x0 plus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon at time step t. Now we will move this predicted x at time step 0 to this place here, and we will get the following. The predicted x at time step 0 equal to x t minus 1 minus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon at time step t divided by the square root of alpha bar t minus 1. That's good, but it is not enough. Actually, here we want to apply our shape-aware module in the first time step, at time step t capital. But here in this formula, we are using xt minus 1 or xt minus delta t to find this predicted x0. It's like that we skipped time step t capital. We didn't do shape-aware operation at time step t capital. So what we will do here, we will do the following. We will change this formula a little bit. So now the predicted epsilon at time step 0 it will be equal to xt, the latent at time step t, the current time step, minus the square root of 1 minus alpha bar t. We replaced alpha bar t minus 1 by alpha bar t times epsilon t divided by the square root of alpha bar t. Now you might ask yourself why we used the predicted epsilon at time step t. Here, it should be epsilon at time step t plus 1 or t plus delta t. The answer is easy, because it is not possible to find epsilon t plus delta t, because here we are at the first time step, at time step t capital, and there is nothing before that. And using our predicted epsilon at time step t with our xt to find the predicted x0, it will also give us good results. Actually, we did this thing previously when we talked about style transfer. So now we found this predicted x0 that are related with the first keyframe using DDIM algorithm, using this formula here. Now what we will do, we will wrap this predicted x0 that are related with the first keyframe to make it similar to this predicted x0 that are related with the current keyframe. And by similar, we mean that we will move the pixels of the predicted x0 that are related with the first keyframe to put them in the new positions, the positions in the current keyframe. But we will not change their values, we will just move and change their positions. In this case, we will be able to combine these two things together. How can we do that? And why we need to combine them? We need to combine them in some way to transfer the textures and the local shapes from the first generated keyframe to the current generated keyframe. To do that, firstly, we should pass the first keyframe and the current keyframe through our GM flow model, and here we will extract forward optical flow and backward optical flow. We will use this forward optical flow to wrap this predicted x0 that related with the first keyframe, and we will get this latent, this new latent, which is x0 dash subscript I, and here we can combine this latent here with this latent here without any problem. But what is this latent here, the predicted x0 that related with the current keyframe? As you can see here, we passed this xt subscript I through our U network, and we got this thing here, epsilon at time step t, that related with the current keyframe. And here we will check if the time step here it is equal to t capital, or we didn't finish the first time step. At this case, we will apply this DDIM algorithm, or to be more specific, we will apply this formula to extract the predicted x0 that related with the current keyframe. This latent, it doesn't have any information about the textures and the local shapes of the first generated keyframe. To transfer all this information to this latent, we will use this latent here. This latent that we will use to generate the first keyframe. Now what we will do, we will create a mask that represents the occluded regions. We will use our forward optical flow and backward optical flow to find this occluded mask. We will use it to combine these two latents together. Firstly, we should resize this mask to make the shape of this mask similar to the shape of any latent. Okay? Why? Because the shape of this mask will be equal to the shape of any one of these keyframes. So we should resize it to be able to apply this mask on these latents. And these latents, they are of course smaller than our keyframes. After resizing our occluded mask, we will do the following. We will multiply this latent by 1 minus the mask. This thing here will represent the unoccluded regions, which means here we will use just the information that related with the unoccluded regions that is available in this x0 dash subscript I. These informations will have the textures and the local shapes of our first generated keyframe. Why we didn't take the information inside this latent that related with the occluded regions? Because as you know, our GM flow will not be able to find the correct optical flow for these occluded regions. So we will remove these informations from this latent. We don't need to use them. Actually, we will use the information inside this predicted x0 subscript I that are related with the occluded regions because they are good and we can use them. So here what we will do, we will multiply this mask by this predicted x0 subscript I. This mask will specify the occluded regions, and this one will remove the information inside this latent that related with the unoccluded regions, and it will keep the information that related with the occluded regions. Okay, now we will add these two latents together. We will combine them together to get full latent, which is this one here, the predicted x0 subscript I. We will add a noise to it, or we have another way. We can use this formula here to get xt minus 1. We have this one here, and we can find this one and this one, and we have this one, which is this one here, this predicted epsilon at time step t subscript I. So we can find this latent x t minus 1 subscript I, and this one we will make it equal to xt subscript I, because now the time step it is equal to t minus delta t or t minus 1. The current time step now it is t minus 1. So now what we did actually, we transferred the textures and the local shapes that is available in the first generated keyframe to the rest generated keyframes. So now all our generated keyframes will have the same textures and local shapes that is available in the first generated keyframe. Now we will learn how to do all these things practically. Hi, in this lecture we will create our shape-aware module. Firstly, we need to download GMFlow repository. So we will type git clone, and here we will put the link of GMFlow repository. And here we will import GMFlow class from gmflow.gmflow.gmflow, and we will import all things inside utils package. So we will type from gmflow.utils import everything. And here we will create our gmflow model like what we did previously. And here we will load the pre-trained weights and we will put them in our gmflow model. And here we will type gmflow.evaluation because here we will use our gmflow model and we will not train it. And here we created this function, getFlow and mask function. This function will take two arguments, first frame argument and current frame argument. This function will return three things. Firstly, it will return the occluded mask, and it will return forward flow, and it will also return wrapped first frame. We put it inside this function all what we learned in the previous lectures about optical flow. Okay, and we created this function use SD with cross frame attention and shape aware module. This function will take many arguments. The first argument is a scheduler, the second argument is the occluded mask, the third argument is forward optical flow, and this argument is the latent at time step t that related with the current keyframe. And here we have the canny input of the current keyframe, and here we have the latent at time step t for the first keyframe, and we have here the canny input of the first keyframe and the text condition and the number of the current keyframe and the width and height and the guidance scale, conditioning scale. And here we made first time steps equal to 0 and TD equal to 2. Actually, we will change this one to TD equal to 1, okay, to apply this shape aware module in the first time step in reverse diffusion. Because when you apply this shape aware module in many time steps in reverse diffusion, the results will not be good. We talked about all these things previously. We will talk here just about what we changed and added to our previous code. And here we found xt-1 that are related with the current keyframe. And here we will find the predicted x0 that are related with the first keyframe by passing our xt that are related with the first keyframe, the predicted epsilon that are related with the first keyframe through our DDIM algorithm. Here we will use this formula to find the predicted x0 that are related with the first keyframe. Here we created this function to time step 0 function. This function will take 4 things: the latent at time step t that are related with the first keyframe, and the scheduler, the name or the number of the current keyframe, and the predicted noise that are related with the first keyframe. Okay, so now we have the latent, the predicted latent at time step 0 that related with the first keyframe, and we will do the same thing to get the predicted latent at time step 0 that related with the current keyframe. So we will type latent I at time step 0 equal to, and here we will use this function to time step 0, and here we will pass the latent at time step t that related with the current keyframe, the scheduler, and the current time step, and the predicted noise that related with the current keyframe. Now let's see what is inside this to time step 0 function. And here's our function. We have 4 things here: xt, scheduler, I, noise prediction. Here we have this condition. We will check if we didn't reach to the last time step in reverse diffusion. At this case, to get the value of alpha bar t, we should use our scheduler.alpha as cumulative product, and here we should take the alpha bar t that related with our current time step. Actually, here we didn't specify what is the meaning of I here. Here we have t, which is the current time step. Let's make I equal to t, or in other words, we can pass t here and here. And at this case, we don't need to type all these things here. We just need to pass this t, okay, like this. So by doing this, we will get alpha bar t that are related with the current time step. Now we have alpha bar t that are related with the current time step, or in other words, alpha bar at time step t. And if we reached the last time step in reverse diffusion, at this case we will make alpha bar t equal to 1. It is something important actually. Here what we will do, we will find the predicted x0. So we will use this formula here. The predicted x0, it is equal to xt, the latent at time step t, minus the square root of 1 minus alpha bar t times the predicted epsilon divided by the square root of alpha bar t. Let's do it. So now the latent at time step t minus the square root of 1 minus alpha bar t times the predicted noise divided by the square root of alpha bar t. That's good. Now we will type predicted x0 equal to predicted x0.clamp, and here we will put minus scheduler.configuration.clip sample range, comma, scheduler.configuration.clip sample range. So at this case, anything inside this predicted x0 greater than this thing here, scheduler.configuration.clip sample range, at this case we will make it equal to scheduler.configuration.clip sample range value. And if anything is smaller than this minus scheduler.configuration.clip sample range, we will make it equal to minus scheduler.configuration.clip sample range value. Okay, and here we will return this predicted x0. And here we will change this thing here to t. Okay, and that's it. This is our function that will move us to the predicted x0. Okay, now we have all these things, and now we will wrap this predicted x0 that related with the first keyframe by using this forward optical flow. So here what we will do, firstly we will type wrapped latent 1 at time step 0 equal to f.decred sample, and here we will pass latent 1 at time step 0 and our forward optical flow, and here we will multiply our wrapped latent 1 at time step 0 by 1 minus the occluded mask, and we will multiply our latent I at time step 0 by the occluded mask, and here we will add them together. So latent I at time step 0, it will be equal to latent I at time step 0 plus wrapped latent 1 at time step 0. Now to get xt minus 1 that are related with the current keyframe, Here we have this alpha bar t minus 1, and we have the predicted x0 that are related with the current keyframe, and we have this one, and we have this one. So that's easy. And here we will find xt minus 1 that are related with the current keyframe, which is equal to the latent I at time step 0 times the square root of alpha bar t minus 1 plus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon that related with the current keyframe. And here we extracted alpha bar t minus 1 from our scheduler dot alpha's cumulative product. Here we created this condition. Here k, it means the index of the next time step in reverse diffusion, and here it means the index of the current time step in reverse diffusion, and a plus 1 it means the index of the next time step in reverse diffusion. We will use it to extract this next time step in reverse diffusion if we didn't reach the final time step in reverse diffusion. Okay, at this case we will make alpha bar t minus 1 equal to scheduler dot alpha's cumulative product, and here we will put the index of the next time step in reverse diffusion, which is k. So now we extracted alpha bar t minus 1 that are related with the current keyframe. And here, if we reached the final time step, or if t minus delta t time step, it is the final time step in reverse diffusion. At this case, we will make alpha bar t minus 1 equal to 1. And here we have another mistake in this condition. Here we should type scheduler.time steps, and we should put this k between square brackets, not equal to. We should also put here scheduler.time steps, and we should put minus 1 between these two brackets. And we have another mistake here. Here we should pass the next time step in reverse diffusion, not the index of the next time step in reverse diffusion. So here, rather than passing k, we will type scheduler.time steps, and we will open square brackets, and we will put k between them, and we will put the result between these two square brackets here. Now you should change these two things that I talked about previously before running the code. Now, here we will use our formula that we talked about previously, this one here, to find xt minus 1 that are related with the current keyframe. And finally, here we will make latent I equal to this xt minus I, and we will make latent 1 equal to xt minus 1 underscore I1, and that's it. And we also changed the many things inside our generate new frames with cross frame attention. We added here and shape aware module. Here we have all these arguments: latent directory, Kenny directory, and here we put it frames directory, which is the directory of our frames, and the width and height. Let's just talk about what we changed here, what we added here. Now here we downloaded our first keyframe. Here what we did actually, we put it our frames directory, and here we added this thing here, and here we put it F, and we put it these two quotations, and we put it slash curly brackets, and between these two curly brackets we put it Kenny input names, and between these square brackets we put it 0, which means the first element in this can inputs names, which is the name of the first keyframe, also colon 04, okay, which means that we should have 4 digits. Firstly, we will put the name of our first keyframe, and we will put zeros and the rest digits to the left. And here we will put the extension .png. Now we have our first image. What we will do now, we will download our current keyframe. We will pass them through our getFlow and mask function. Here we will get the width and height of any latent, and here we took the width and height of the first latent, which is related with the first keyframe, and here we created Y and X locations. Here Y, it is just an array, two-dimensional array, which has all Y locations. And here X, it is just a two-dimensional array which has all X locations. Here we have our forward optical flow. We will change its size to make it similar to the size of any latent in our latents. We will use interpolate to do that. We will pass the desired width and height. And here what we will do, we will combine these two arrays together to create a grid. And we will add our forward optical flow to this grid to get wrapped grid using FWD. Now we will take the shape of this grid, this wrapped grid using FWD, and we will normalize the locations inside this wrapped grid using FWD. We will make the X locations and Y locations between -1 and 1. So we will do the following. Normalized wrapped X grid FWD, it is equal to 2 times wrapped grid using FWD. Here we will put colon, comma, 0, which means that we took the X locations, we multiplied them by 2, and we divided them by the width -1, and finally we subtracted 1 from the resulted tensor, and the same thing here. And now here what we will do, we will combine them together again to get normalized wrapped grid FWD. We use torch.stack to do that, and here we will pass our normalized wrapped X grid FWD and normalized wrapped Y grid FWD, and here we specified the location of the new dimension that we will use to put these two things along it. So now we have the batch size, the width and height, and finally our new dimension with length 2, which has these two things here. And here we also have our occluded mask. Okay, we will convert it into NumPy array. This M matrix, it has also batch dimension, so we should put 0 here, okay, to get just the mask, and we will resize it using our OpenCV library, and we will put the desired size, which is the size of any latent, because as you know, we want to use this occluded matrix with our latents. We want to multiply it with our latents, so the shape of it should be similar to the shape of any latent that we have. And here what we will do, we will convert it into PyTorch tensor again, and we will send it to our device. And here we will add a new dimension with length 1, okay, which represents the batch dimension. And here we will add another dimension with length 1 also. Here we will repeat the second dimension, the second dimension that we put it here with length 1. Now we will repeat it 4 times, and we will keep the rest dimensions as they are. Why we did that? Because in any latent, in the second dimension of any latent, we have 4 feature maps. So when we want to multiply our occluded mask, we should multiply it with each feature map in our latent. So we should repeat this mask 4 times. And we talked about all these things previously. And finally, what we will do, we will use this function, use SD with cross-frame attention and shape aware module. Here we will pass our scheduler, our occluded matrix, our occluded mask, our normalized wrapped grid FWD, our latent input I, our Kenny input I, our latent input 1, Kenny input 1, and our current latent name, and the width and height that we want, the guidance scale, and the conditioning scale. Let's make the guidance scale equal to 0.7. Let's make TD equal to, for example, 1, and that's it. And we put this condition here, as you can see, to apply our shape aware module just on the first time step in reverse diffusion. And here, if we finish the first time step, we will not use our shape aware module. Now we will call our function to generate the keyframes. Now these our generated keyframes with just using our cross-frame attention method. And here are the generated keyframes with using cross-frame attention and shape-aware module. Our generated keyframes now sharing the same textures. You can see that now our generated keyframes, they are more similar to the first generated keyframe. Thanks for watching. Hi, in this lecture we will talk about pixel aware module. We will use this pixel aware module to concentrate low-level texture features during the mid steps. Because as you know, we used our shape aware module just in the first step of our reverse diffusion process. So we need another module to sharing the low-level texture features between our generated keyframes. And when we say low-level texture features, we should work on the pixel level, not the latent level. And that's what we will do now. This module will work with our frames. It will not work with the latents of our frames. Now let's learn how to build this module. Firstly, we should use our previous module, shape aware module with cross-frame attention, to generate our new keyframes. Okay, so now we have all our generated keyframes using our cross-frame attention with shape aware module. We will use these things with our pixel aware module. Now what we will do, here we will generate new keyframes again, but using our pixel aware module. Firstly, we will check if we completed the first time step. At this case, we will not use our shape aware module anymore. And now we should use our pixel aware module. And here we will check if we are trying to generate the second new keyframe. If it is the case, we will take the original current keyframe and the original first keyframe. We will pass them through our GM flow to get the forward optical flow and the backward optical flow that we will use to create our occluded mask. And we will also use the forward optical flow to wrap the new first keyframe that we generated previously using just cross-frame attention and shape-aware module. And because that we are trying to generate the second keyframe, we can say that this thing here equal to this thing here, and this thing here equal to this thing here. Because in this case, I equal to 2, and I minus 1 will be equal to 1. Now, because that we wrapped our first generated keyframe and the previous generated keyframe, we can combine them with our current generated keyframe that we took from these keyframes that we generated previously, and of course by using our occluded masks. Firstly, we will take the pixels that are related with the unoccluded regions from our wrapped previous generated keyframe, which is similar to the wrapped first generated keyframe. Because here we are trying to generate the second keyframe, which means that I equal to 2. And we will take the pixels that are related with the occluded regions from our current generated keyframe that we took from these keyframes that we generated previously. So now this formula will give us a keyframe. This keyframe will have pixels from our wrapped previous keyframe that we generated just using our shape-aware module and cross-frame attention. And to be more specific, we took it from these keyframes here, these generated keyframes. And this keyframe that we will get from this formula will also have pixels from this current keyframe. This current keyframe created just by using cross-frame attention and shape-aware module. To be more specific, we took it from these generated keyframes. And because that the unoccluded regions, they are more than the occluded regions, so at this case, most of the pixels in the frame that we will get from this formula, they will be from our wrapped previous keyframe. In other words, most of the local textures of the wrapped previous keyframe, we transferred it to our frame that we will get from this formula. And a small region, or in other words, the occluded region, will have just the local textures of the current keyframe that we took from these keyframes that we generated previously with just using cross-frame attention and shape-aware module. And now we will combine the frame that we will get from this formula with the wrapped first keyframe that we took from the keyframes that we generated previously with just using shape-aware module and cross-frame attention. So now what we will do actually, we will take just the pixels of our wrapped first keyframe that generated just by using cross-frame attention and shape-aware module. We will take the pixels that related with the unoccluded regions from this wrapped first keyframe. And of course, the occluded regions here, they are different from the occluded regions here. Here we are talking about the occluded regions between the first keyframe and the current keyframe, while previously we talked about the occluded regions between the previous keyframe and the current keyframe. And we will fill the occluded regions with pixels from this frame. To be more specific, the occluded regions that are represented by this occluded mask between the first keyframe and the current keyframe. By doing this, we will transfer the local style of our wrapped first keyframe that we took from these generated keyframes. And we previously added also the local features of the wrapped previous keyframe that we took from the keyframes that we generated previously. By doing this, you will be able to fill large part of your occluded region that represented by the mask between the first keyframe and the current keyframe by the pixels from the wrapped previous keyframe, which is something good. Because now most of your generated keyframe will have the local features from the wrapped previous keyframe and wrapped first keyframe with a small amount of your current keyframe that generated previously by just using the cross-frame attention and shape-aware module. Now we will pass this new keyframe through our encoder part of our variational autoencoder to get the latent that related with this new keyframe, which is x0 dash subscript I. We did this thing because, as you know, we need to use our U-network to do reverse diffusion. So we should change this keyframe to its latent. And as you know, the latent of each one of these keyframes, it is at time step 0. So we need to add a noise to it to move it to time step t-1 or t-minus delta t. And here we will combine two latents together. The latent that we will get from our U-network after doing reverse diffusion, which is xt-1 subscript I, and the latent that we created here, which has the local features from the previous generated keyframe and the first generated keyframe that we took from these keyframes that we generated with just using our cross-frame attention and shape-aware module. And here we will take just the values that related with the unoccluded region from this xt-1 dash subscript I, and we will take the values that related with the occluded regions from our xt-1 subscript I. The occluded region that we are talking about right now, it is different from the previous occluded regions. It is just the intersection between the first and the second mask, the mask between the first and the current keyframe, and the mask between the previous and the current keyframe. Here this mask will be smaller than the mask between the first and the current keyframe and the mask between the previous and the current keyframe. We will fill this one with the latent that we created by using our U-network or by doing reverse diffusion. Here we use this latent xt-1 subscript I to be able to use our control net to force the generation to give us what we want based on our prompt and our text also, not just using xt-1 dash subscript I. And here when we are working on the third keyframe, fourth keyframe, etc., here we will not take our first keyframe from these keyframes that we generated previously with just using cross-frame attention and shape-aware module, and we will not take our previous keyframe from these generated keyframes, but we will take them from what we have, because as you know, now we have the first generated keyframe with pixel-aware module that we generated using pixel-aware module, and we have the previous generated keyframe that we generated using also our pixel-aware module. Here we used our shape-aware module in the first time step, and we used our pixel-aware module in the second, third, fourth, fifth, and sixth, for example, time steps, and we used the cross-frame attention along all time steps to generate this keyframe, previous keyframe, and the same thing for the first keyframe. So we will use them with this formula here to do pixel-aware process. And here we will use this latent that we created using our pixel-aware module xt-1 subscript I. We will use it, we will pass it through our U-network, we will make it equal to xt subscript I. Now the previous time step t minus 1. Now it is the current time step t. So xt minus 1 subscript I, now it is xt subscript I. We will pass it through our U network to predict the noise and to do reverse diffusion, and we will also use our pixel aware module to create xt minus 1 subscript I again and again until stopping this module, pixel aware module, and in the rest time steps we will use just our normal reverse diffusion process. Here it is like that we are doing in painting. We are trying to harmonize the information that we put it in the included regions with the information of our xt minus 1 dash subscript I that we put it in the unincluded regions. And this in painting operation, it is guided by our prompts and our control net and the surrounding information of our xt minus 1 dash subscript I latent. Now we learned how to build a pixel aware module to constrain the local textures between our keyframes. Now we will learn how to build all these things practically. Hi, in this lecture we will build our pixel aware module. Previously we created new keyframes using our generate new frames with the cross frame attention and shape aware module. And all these frames are available in this folder, output keyframes folder. We will use them with our pixel aware module. Firstly, this function use SD with the cross frame attention and shape aware module and pixel aware module will take all these arguments. The first one is x0 bar IINU, which is this one here. And we have also our scheduler, the mask between the first and the current keyframes after resizing and make the shape of it equal to the shape of any latent. Okay, and we have also the mask between the current or the previous keyframe and the current keyframe, and here the shape of this mask, it is also similar to the shape of any latent. The next argument is this one here, the forward optical flow between the first and the current keyframes, and the forward optical flow from the previous to the current keyframe, the latent of the current keyframe, the Kenny input that related with the current keyframe, the Kenny input that related with the first keyframe, the text condition, and the current keyframe number. And we have also this normalized wrapped grid FWD latent. This tensor will have the new locations. We will use this one with our grid sample method to wrap our input latent. Our input latent here, it is the latent of the first keyframe. We will wrap it to the latent of the current keyframe using this tensor. And here we will pass the width and height of the generated image or generated keyframe, the guidance scale. Here we will make it 7.5. By increasing this parameter, we will increase the importance of our text condition in the generation process, and here we will make conditioning scale equal to 0.7. This argument, it is related with our control net, and here this argument will specify the first time step that we will start with in reverse diffusion. And here we have this argument. This one will specify how many times we will use or we will apply our shape aware module. And here we have this parameter, TP parameter, will specify the number of time steps that we will use our pixel aware module with. And here we have this parameter, threshold parameter, will specify the threshold that we will use here. Previously we used 0.02, but now we can change it. Here in this get flow and mask, we have another argument which is threshold, which is by default equal to 0.01. You can increase it or decrease it as you want to get the best results. And here we created this global argument gate attribute. Okay. This is something important for our cross-frame attention process. And here what we will do, we will make this M capital equal to M1 and I, which is the mask between the first and the current keyframe. And the shape of this mask, it is equal to the shape of any latent. Now, we will make this FWD equal to normalized wrapped grid FWD. We will use this one to wrap our input latent to the current latent. And here what we will do, we will create this loop here. And here firstly we will make attribute gate equal to I1. Okay. And here we will create our latent input 1 like this, and here we will scale our latent model input 1, and here we will create our control net condition 1, and here we will pass it through our control net, and we will pass also our text prompt and our conditioning scale, and we will get these two things. And here we will use our U-network to get the predicted noise that related with the first keyframe. Here we will do classifier free guidance, and here we will make attribute gate equal to I, and here we will create latent model input I, and here we will scale it. Here we will create control net condition I, and here we will use our control net. We will pass our latent model input I, our text condition, our control net condition I, and our conditioning scale to get these two things here. We will pass them through our U-network, and we will pass also our latent model input to get our predicted noise that related with the current keyframe. Here we will do also classifier free guidance, and here what we will do, here we will check if we finished the first time step. Actually here we will make TD equal to 1, and we will also check if we are working on the second keyframe or more, because as you know our shape over module needs our first keyframe, keyframe 1, and the current keyframe. So our shape over module needs 2 keyframes to work. Here we will define this variable, k variable. This one will have the index of the next time step in reverse diffusion. Here we will use this function to time step 0 function to, and we will pass our latent 1, which is the latent that related with the first keyframe, our scheduler, our current time step, and the predicted noise, the predicted epsilon that related with the first keyframe. So we will get this latent 1 at time step 0, and we will also get latent I at time step 0. Here we will use our to time step 0 also. We will pass our latent I, our scheduler, current time step, noise prediction I. And here what we will do, we will use our grid sample to wrap our latent 1 at time step 0 based on this tensor FWD, and we will get wrapped latent 1 at time step 0. Now we will combine all these latents together. So now wrapped latent 1 at time step 0, it is equal to, here we will take just the unincluded regions from this wrapped latent 1 at time step 0, and we will multiply our latent I at time step 0 by this mask here. So by doing this, we will take just the occluded regions from this latent I at time step 0, and here we will combine them together to get this latent I at time step 0. And here we will check if we reached the final time step in reverse diffusion. At this case, we will make alpha bar t minus 1 equal to 1. Otherwise, we will make alpha bar t minus 1 equal to scheduler dot alpha as cumulative product. And here we will put the index, or we will put the next time step in reverse diffusion. And here what we will do, we will create this variable xt minus 1 I, which is equal to latent I at time step 0 times the square root of alpha bar t minus 1 plus the square root of 1 minus alpha bar t minus 1 times the predicted epsilon that are related with the current keyframe. So here actually we did DDIM, and here we will make the current latent equal to xt minus 1 II and latent 1 equal to xt minus 1 I1. And here, if we finished the first time step, so now we don't need to use our shape aware module anymore, and we will use our pixel aware module only. Here we will create this variable, k variable, which will specify the index of the next key time step in reverse diffusion. Here we will create a noise. We will take Gaussian noise. The shape of this noise should be equal to the shape of any latent. Here we will add this noise to our x0 bar II new to get xt minus 1 bar II new. Here we moved our x0 bar II new to time step t minus 1 or t minus delta t. Here we passed the next time step in reverse diffusion, and here we will find the intersection regions between these two masks, M1 and I, and Mi minus 1 and I. We will fill these intersection regions with our original current latent that we can take from our U network. And here what we will do, xt minus 1 II equal to this new mask times xt minus 1 II plus 1 minus this mask here times xt minus 1 bar II new. So actually we are working on this place here, and we will make our current latent equal to xt minus 1 II, which is this one here, and we will make latent 1 equal to xt minus 1 I1. And if we finished the time steps that we won't use our pixel aware module with, in this case we will just do our normal reverse diffusion process. We will just make our latent I equal to xt minus 1 II and latent 1 equal to xt minus 1 I1, and we will take these things just from our U network without using our shape aware or pixel aware modules. Okay, and that's it. Now let's talk about this function here. Here we created this function generating new frames with the cross-frame attention and shape-aware module and pixel-aware module. And here this function will take these arguments. The first argument is generated keyframes directory. Here we will put our new keyframes in this directory and this one latent directory. We talked about this one previously. And this one and this one, and here we put this argument, the threshold argument, which is by default equal to 0.01. Here we will put the names of our latents in this list here. Let's call it latents names list, and here we will sort this list, and here we will create this list Kenny inputs names list, and we will sort this list. We will take Kenny input 1 image, and we will take latent input 1, which is the latent that are related with the first keyframe, and we will take it from this directory like what we did previously. Here what we will do, we will take our original first keyframe, we will convert the order of the color channels from BGR to RGB. This is something important actually, and we didn't do that previously in shape-aware module lectures, so please do it. Okay, now we will create this loop here. We will pass it through each latent, and we will get the current original keyframe. We will convert the order of the color channels for this keyframe, and here we will check if we are working on the first keyframe or on the second keyframe. At this case we will do the following. We will make keyframe 1 equal to keyframe I minus 1. Okay, and now what we will do, we will take this generated keyframe, the current generated keyframe, because it is something important for our pixel aware module. We will convert the order of the color channels from BGR to RGB. So now we have this generated keyframe I, this one created with just using our shape aware module and cross frame attention, and without using our pixel aware module. We just used this function to get these generated keyframes with just using shape aware and cross frame attention. And now what we will do, we will create this variable I new, this tensor. Here we should convert this one from NumPy array to PyTorch tensor, and we should add the batch dimension with length 1, and we should change the order of the dimensions. We will put the channel dimension at in this place here, and we will put the width and height dimension here and here. And here we will keep our batch dimension at the same place. The length of this dimension equal to 1 actually. Here we will check if we are working on the first keyframe. At this case we will make generated keyframe I equal to generated keyframe 1, and we will make generated keyframe I minus 1 equal to generated keyframe I. And here we will make all the keyframes equal to the generated keyframe I, because here we are working on the first keyframe. So now we have just one keyframe here, one generated keyframe. So we will make generated keyframe 1 equal to generated keyframe I, and generated keyframe I minus 1 equal to generated keyframe I. And here we will make I1 new equal to II new, which means that the first generated keyframe with just using cross frame attention and shape over module should be equal to the current generated keyframe with just using cross frame attention and shape over module, because here we have just one generated keyframe. We are working on the first generated keyframe. And the same thing here, II minus 1 equal to I1 new, which is equal to II new. Or we can put this here also to be more clear. And here what we will do, if we are working on the second keyframe, in this case we will make generated keyframe I minus 1 equal to generated keyframe 1. Okay, and we will convert it into a tensor. II minus 1 equal to, here we will convert this one into tensor, and we will add the batch dimension, and we will change the order of the dimensions. Here is the first dimension, which is the batch dimension, and the second dimension, which is the channel dimension, and the third dimension, which is the height dimension, and the last dimension, which is the width dimension. And here what we will do, if we are working on the, for example, the third, fourth, fifth keyframe, we want to generate the third keyframe. In this case, what we will do, now we will take our generated keyframe I minus 1 from our generated keyframes directory, okay, which is this one here, okay. So now we have our generated keyframe I minus 1, and we will change the order of the color dimension. So now we have this generated keyframe I minus 1. We will also read the original previous keyframe. So keyframe I minus 1 equal to, and we will take this one from our frames directory, which is this one here. This one will have our original frames of our video. And here what we will do, we will change the order of the color dimension, and here we will convert it into a tensor, and we will add our batch dimension. And now we have this II minus 1. Here we pass this one to it to get this II minus 1, and we have our original previous keyframe, and we have also our keyframe I, and we have also our keyframe 1. That's really good. Now what we will do, we will use our optical flow model. We will pass our keyframe 1 and keyframe I, and we will pass our threshold to this get flow and mask function to get the mask between the first and the current keyframe, and the forward optical flow between the first and the current keyframe. That's good. Now we will find the mask between the previous keyframe and the current keyframe, the occluded mask, and the forward optical flow between the previous and the current keyframe. We will use our get flow and mask. We will pass our keyframe I minus 1 and keyframe I and our threshold. And here what we will do, we will take the height and width of our II new, which is the height and width of any keyframe. We will create a Y list and X list based on these two things here. We will change the width and height of this FWD 1 to I based on these two things here, the height and width of our II new. Here what we will do now, we will create a list of Y locations and X locations, and here we will resize our FWD 1 to I based on these two things, the height and width of our I1 in U. And here we will get this FWD 1 to I. Here what we will do the same thing for our FWD I minus 1 to I. We will also resize it, and here we will stack these two tensors together and adding this FWD 1 to I to get this wrapped grid using FWD to I. And we will stack these two x and y locations together, and we will add our FWD I minus 1 to I to this tensor, and we will get this wrapped grid using FWD I minus 1 to I. Here we will do normalization. Here we will take the shape of FWD I minus 1 to I, and what we will do, we will type normalized wrapped x grid FWD 1 to I equal to, here we will multiply 2 by wrapped grid using FWD 1 to I. Here we will take the x locations, we will divide the resulted tensor by the width minus 1, and we will subtract 1 from the resulted tensor. We will do the same thing for our wrapped y grid, and here normalized wrapped y grid FWD 1 to I equal to 2 times wrapped grid using FWD 1 to I. And here we will put the index of our y locations. Here we will divide this resulted tensor by the height minus 1, and here we will subtract 1 from the result. Okay, now what we will do here, we will type normalized wrapped x grid FWD I minus 1 to I equal to, we will do the same thing here, 2 times wrapped grid using FWD I minus 1 to I, and here we will put the index of this of x locations divided by w minus 1 minus 1, and here we will type normalized wrapped y grid FWD I minus 1 to I equal to 2 times wrapped grid using FWD I minus 1 to I, and here we will put the index of the y locations divided by the height minus 1 minus 1. Here we will stack normalized wrapped x grid FWD 1 to I with normalized wrapped y grid FWD to I. And we will do the same thing here. Normalized wrapped grid FWD I minus 1 to I equal to, here we will stack this normalized wrapped x grid FWD I minus 1 to I with normalized wrapped y grid FWD I minus 1 to I. Yes. Now we will do wrapping. Wrapped I new equal to, here we will use grid sample method. What we will do actually, we will convert this I1 new into tensor, and we will specify the type of this tensor. And what we will do here, we will pass our normalized wrapped grid FWD 1 to I, and here we will specify the type. Okay, so now we will get our wrapped I1 new, and here we will get wrapped I minus 1 new. Here we will pass our I minus 1. You can call it I minus 1 new, okay, like this one here, no problem. So now we will pass it, we will change the type of this tensor, and we will send it to our device. Here we will pass our normalized wrapped grid FWD I minus 1 to I. Okay, so now we will get wrapped I minus 1 new. Here we will get the shape of any latent. We will get the height and width of any latent. Here what we will do, we have this capital, the occluded mask between the first and the current keyframe. We want to resize it to make it the shape of it equal to the shape of any latent. So let's call it m small 1 and I. And here what we will do, we will change it to numpy array. We will do the same thing to mi minus 1 and I. We will get m small I minus 1 and I. We will convert this one into numpy array. Okay, so now we will do resizing. Here we will type m1 and I. Here we will put 0. And here we will put the new size. So now we have this m1 and I. We will do the same thing for our mi minus 1 and I. And we will get this one mi minus 1 and I. Here we will change the type of this tensor to, or this numpy array to PyTorch tensor. We will convert it into PyTorch tensor. Now we have this PyTorch tensor. We will do the same thing for our mi minus 1 and I. And here we will add another dimension, which is the batch dimension, to our m1 and I. And we will do the same thing for our mi minus 1 and I. And we will put another dimension, okay, to our m1 and I, because as you know, any latent will have 4 dimensions: the batch dimension, the feature maps dimension, the height, and the width. Okay, so now we will add feature maps dimension, and we will repeat it 4 times, because in any latent, this dimension, the length of this dimension equal to 4. So we will do the same thing for our mask. So m1 and I equal to m1 and I dot repeat, and here we will repeat this one 4 times. Okay, and the same thing for our mi minus 1. We will repeat it 4 times, and we will do something similar to our m capital I1 and I. The size of this one, actually, the width and height of this one equal to the width and height of any keyframe. But this one will not have the color dimensions. And we will put this dimension in this location in the same place of our feature maps dimension. And we will repeat it 3 times, because this dimension, the color dimension, will have 3 channels. Okay, so now we made this mask something suitable to multiply with any keyframe that we have. We will do the same thing to our mi minus 1 and I. And now what we will do, here we will compute I bar new. Okay, this one here, we will learn how to compute this one. So I bar new equal to m1 and I times, here we will multiply our capital M I minus 1 and I times I new, plus 1 minus m I minus 1 and I times wrapped I minus 1 new. Okay, we have this one here. We will multiply this one by m1 and I, plus 1 minus m1 and I times wrapped I1 new. We will divide this I bar new by 255, and here we will put with torch.noGradient, and here we will use e star function. We will pass our I bar new to this function. But what is inside this function? Why we don't just use our encoder? Okay, here is our e star function. This function will take just one argument, which is I bar. Here we will make the values of this I bar between -1 and 1, because it is something important for our encoder, part of our variational autoencoder. And here we will use our E, our encoder. We will pass this new keyframe to our encoder, and we will get x0r. And here we will make x0r equal to decoder input. We will pass this one through our decoder, and we will get I capital R. We will make this I capital R equal to encoder input. We will pass this encoder input through our encoder to get this x0rr. We will subtract this x0rr from this x0r to get the error tensor. Actually, this encoder will create an error, so we need to reduce that error. It's not a good idea to use it directly. So we will reduce this error. We will add this error to our x0r to get this x0r with a small error. And finally, we will multiply this x0r with a small amount of error by variational autoencoder scaling factor. By using this E star, you will reduce the error of our encoder. And now we have our x0r, which is our x0 bar II new. So now we have this one here. Okay. Now what we will do, we will create this variable current keyframe latent path and current keyframe Kenny input path and Kenny input I and latent input I. And here we will take the height and width from any latent input 1. We will create our x and y locations, and we will resize our FWD1 to I to get this FWD. We will add this FWD to our tensor here to get wrapped grid using FWD latent. Here we will take the shape of this grid, and what we will do, we will normalize our x locations and y locations by doing the same way, and here we will stack them together to get this normalized wrapped grid FWD latent. And here what we will do, we will use our function. Okay, our use SD with the cross frame attention and shape aware module and pixel aware module. We will pass our x0 bar II new and scheduler and m small 1 and I and mi minus 1 and I and fwd 1 to I and fwd I minus 1 to I and latent input I, Kenny input I, latent input 1, Kenny input 1, CP, current latent name, normalized gradient FWD, width and height, guidance scale, conditioning scale, first time step TD equal to 1, TP equal to 6, threshold equal to 0.01. Here we will apply our pixel aware module and the first 6 time steps in reverse diffusion. Okay, that's it. And now we will call our function generate new frames with the cross frame attention and shape aware module and pixel aware module. And here we actually changed our prompt to this one here, digital painting man CG style. Okay, now let's see the results. Here's our first generated keyframe, the second one. That's really good. As you can see, the background is the same textures and shapes, and now we can say that this person here is similar to this person here. And let's move to the third keyframe. That's good also, and this one is good also, this one. Okay, that's really good actually. In the next lecture we will learn how to convert these keyframes to a video using EB-Synth. Thanks for watching. Hi, in this lecture we will learn how to convert our generated keyframes into animation. Firstly, we have two folders. Frames folder. This folder will have our original frames, and the second folder, it is output keyframes folder. This folder will have our generated keyframes. Here we will use EB-Synth program. You can download it easily from internet. Now what we will do, we will drag this frames folder and drop it here in this place. Okay, and we will drag this output keyframes folder and put it here. And now what we will do, we will click on run all, or you can select advanced and click on high, and after that click on run all. It will take time to convert your generated keyframes into animation, and your generated animation will have 316 frames. It will generate these frames based on our generated keyframes. The first 18 frames will be based on keyframe 1, and the frames from 18 to 35, it will be based on keyframe 18, etc. Now let's go back to our folders. Let's move to the first one. Okay, let's click on this one here. That's really good. Let's move to the next folder, and let's click on this one. This one, it is also good. And this one really good. We have just a small distortion here, but in general the animation, it is good actually. And this one, and this one also good. And this one, that's amazing. And here we have a few distortion. Thanks for watching. Hi, in this section we will talk about EMO, Emote Portrait Alive. Here we will try to make videos with the token heads looking more real and expressive. Here what we will do, we will try to convert our single image into a video. And we will try to make the token head inside our generated video more real and expressive. All the information that I will say, I took it from this research paper. Here I need two things actually, a single image and an audio file. I will use these two things to create amazing videos. And here we will not use facial landmarks. They found that it is enough to use just an audio file with a single image to create these amazing videos. Let's see one of the generated videos using EMO.
我都1年没吃苹果了，到超市偷了一袋苹果，大家觉得这要不道歉？你1年没吃苹果，你就能偷苹果啦？啊，吃水果是必需品还是奢侈品？
That's amazing, right? Here we will use diffusion models to do this task. Here, EMO will try to capture a wide range of realistic facial expressions. It will try to extract the detailed facial expressions from your input audio and put them in the generated video. And this EMO model will not just focus on conveying the small emotions, in other words, micro expressions, but it will also focus on making the movement of the head more realistic. It's like that you are trying to extract all the emotions inside the audio file and convert them into a video, which is something amazing. And you should know that audio signals are rich in information that related with facial expressions. They are much better than the facial landmarks. Hi, previously we talked about how our audio signals are rich with facial expressions information. And we said that we will use diffusion models to convert our audio signals to videos. But actually it is not easy to combine our audio signal with our diffusion model. It is tricky to match up sounds with facial expressions. There is a lot of uncertainty about how to connect the audio signals and the facial expressions in the generated video. So you should find a way to connect these two things together, otherwise your generated video from your model will be unstable, which leads to facial distortions and shaky movement between video frames. To solve this problem, they added stable control mechanisms to EMO model. The first controller is speed controller and the second controller is face region controller. They added these two controllers to enhance the stability during the generation process. And there is another important thing. Here is our reference input. To make sure that the character in the generated video stays similar to the character in the reference image, they created frame encoding module. This module will try to preserve the character's identity across the video. And as you can see here, this character here, he is the same person here in this frame and in this frame and in this frame and in this frame. And the character in our generated video is similar to the character in our reference image. And finally, they created a large data set of audios and their videos. They used this data set to train their model EMO. This data set has a wide range of content, including speeches, films, and television clips, and covers multiple languages like Chinese and English, which will make sure that the training materials captures a wide range of human emotions and ways of speaking. Thanks for watching. Hi, in this lecture we will talk about the first component in our EMO machine, which is backbone neural network. Here we took the U network from our Stable Diffusion model, as you can see here. And here we will pass multi-frame latent input at each time step to this U network. Let's say, for example, we are at time step T capital. Okay, we have all these latents. We will take the first one and we will pass it through our U network, and our U network will try to remove the noise inside this latent. Okay, now we will take the other latent and we will pass it through our U network, and it will also try to remove the noise from it, and the same thing with this latent. And after completing all the latents, we will move one step backward. So now we are at time step T capital minus delta T, and we will do the same thing again, which means that at any time step we have many latents that we need to remove the noise inside them. And when we reach time step T0, at this case we will pass all our latents through our decoder part of our variational autoencoder to get all these high resolution frames. But that's not enough actually. We need to add many other things to this U network for consistency. And we need also to learn how to add the audio to this U network during the generation process. We will talk about all these things in the future. Thanks for watching. Hi, in this lecture we will learn how to inject our audio signal in the generation process. Firstly, let's say that we have an audio file, and here is our audio file. We will divide it into parts. This part here of our audio file, it is related with this latent here, the first latent, the first frame, and the second part here related with the second frame, etc. Now let's say that we are working on latent 2. We are working on the second frame. Okay? Here we will not take just the segment of our audio signal that related with the second frame, but we will take many other segments from the past and the future. Why? Sometimes when we want to say something, you need to open your mouth without any sound for inhaling. Okay, so in this case we need the future audio segments to know the right motion of the mouth that our U network should create in the frame that we want to generate right now. And it's also important to take into account the previous audio segments, because the movement of the mouth in the current frame, it will also depend on the previous sound segments. And that's it. Now let's say that we are at this latent, at the second latent, and here is the segment that related with this latent, and we will also take the previous segment which is related with this latent, and the future audio segment which is related with this latent. Okay, we will concatenate them together, we will combine them together, and now what we will do, we will not pass this vector of numbers through our U network directly, but we will pass it through this pre-trained model, wave to vector pre-trained model. This one will create a new representation for our original audio signal. The number of elements in this new representation, it is much smaller than our original vector that we passed through our wave to vector pre-trained model. Why? Because this pre-trained model will just focus on the most important thing in our input audio signal. Now we have this new representation, a generative for frame 2, because here we are trying to generating frame 2, which is the second frame in the video that we want to generate. And what we will do, actually, we will use this thing, this vector, in this cross attention layer. Okay, we will call it audio layer. It is something similar to what we did previously when we converted our text into a feature vector, and we used it with our cross-attention layers in our U network to make a condition. Okay, that's it. Now we should know that before any cross-attention layer that we use our audio information with, there is another layer, we call it reference attention layer. We will talk about this layer in the next lecture. Thanks. Hi, in this lecture we will talk about reference network. We will use this reference network to extract the detailed features from our input images. This reference network, it is similar to this backbone network. We took these two U networks from our Stable Diffusion 1.5. In other words, it is easy to integrate what we will take from this U network in this U network. As we said previously, we want from the character in our single image, our reference image, to talk. Okay? We will pass this reference image, this single image, through our reference network. And what we will do, we will extract the reference feature maps from different self-attention layers in our reference network. As you can see here, we have this reference feature map that we got after passing our reference image, our single image, through our reference network. We took this feature map from one of the self-attention layers in our reference network, and here are the dimensions of this feature map: the height, the width. Let's say the number of channels equal to 1, but actually it is more than that. And yes, this feature map will represent the detailed feature in our reference image. We will use this feature map and many other feature maps that we will take from different self-attention layers in our U network after passing our reference image to maintain the consistency of the character's identity in the generated frames. In other words, we want to see the same character in our reference image in the generated images from our backbone network. We will use these features, these feature maps, to achieve this task. So, firstly, we will pass this reference image through our encoder part of our variational autoencoder to reduce the spatial dimensions. And after that, we will pass the output from our encoder through our reference network. And during moving through our reference network, we will extract the reference feature maps from different self-attention layers in our reference network. And you can store these reference feature maps in your memory. For example, this feature map extracted from self-attention layer 1 in our reference network. Here's the height, the width, and the depth dimension, and the channel dimension. And let's say that this reference feature map we extracted from self-attention layer 5, for example, and etc. And you should know that we don't need to add a noise to our reference frame before passing it through our reference network to move it to the current time step. Okay? This reference network, as you know, it is at time step 0. Okay? And you can pass it through your reference network and use these reference feature maps that you created by passing this reference image at time step 0 in this backbone network that is trying to remove the noise from a latent at time step t, and it will not affect on the results actually. In other words, we don't need to use our reference network at each time step. This thing will help us to speed up the generation process. And you should know that the reference attention layers in our backbone network, or in other words, the self-attention layers that will take the reference feature maps as input, these layers should be before the audio attention layers in our backbone network, which means that after each reference attention layer, we should have an audio attention layer. Now we learned how to make sure that we will get the same target object's identity in the generated frames. But now what we want actually, we want to make our backbone network able to know about the previous generated frames, because this thing will help our backbone network to maintain continuity and consistency across frames in the generated video. So what they did actually, they changed some of the self-attention layers in our backbone network to self-attention temporal layers. So what we will do actually here, firstly, let's say that we will take the last 3 generated frames from our backbone network. We will concatenate them with our reference single image, okay? And we will pass all these things through our encoder part of our variational autoencoder, and we will pass these 4 frames. Now we have 4 frames through our reference network. And what we will do actually, we will take our reference feature maps from some self-attention layers in our reference network, and we will take motion feature maps from other self-attention layers in our reference network. Why we said motion feature maps? Because these feature maps will have information about the last 3 generated frames. And these last 3 generated frames, of course, will have information about the previous motions. And here we have 4 dimensions in this motion feature map that we took from one of the self-attention layers in our reference network. The first dimension is the width dimension, the height dimension, and let's say that the channel dimension equal to 1 for simplicity. And here we have the fourth dimension, which is the frame dimension, which represents the number of the previous generated frames that we want to consider to create our motion feature maps. And in this case, it is equal to 3. Okay? And here is the shape of our motion feature map. The first dimension, it is the batch dimension, which is equal to 1. The second dimension is the depth dimension or channel dimension. The third dimension, it is the number of previous frames dimension. And the fourth dimension, it is the height, and the fifth dimension, it is the width. Here, before passing this motion feature map to the corresponding temporal layer in our backbone network, they will reshape this motion feature map to the following. As you can see here, the batch dimension, the height dimension, the width dimension, and here we have the number of previous frames dimension and the channel dimension. And now we will apply our self-attention layer on this temporal dimension or number of previous frames dimension to make our backbone network able to capture the dynamic content of the video. We should put a temporal layer in front of each audio attention layer, as we can see here in our backbone network. And they put these temporal layers at each resolution level in our backbone network. As you can see here, we have this motion feature map that we took from one of the self-attention layers in our reference network after passing the last 3 generated frames through our reference network. Firstly, we will pass this motion feature map through an attention layer. We will talk about this attention layer in the next lecture, and we will concatenate the output from this attention layer with the output from the previous layer in our backbone network, which is the self-attention layer in our backbone network that corresponds to the self-attention layer that we took our motion feature map from in our reference network. Now we will pass this new feature map through our temporal layer, and we will get this new feature map here. So in this case, the dynamic information now are available in this feature map. You should know that after generating each frame, we will update these 3 motion frames that we will use. Okay? We will remove the first one and we will add the new generated keyframe to the rest. Thanks for watching. Hi, in this lecture we will talk about face locator and speed layers. Previously we talked about temporal layers and we said that we use them to make continuity in the generated frames, which means that the transitions between frames will be so natural and the viewers will not notice any breaks or gaps. in the generated video. And to make the generated video more stable and consistent, they used another control signal which called weak control signal. And this control signal is just a mask, okay, that we will pass through our unit work to specify the region that the character face will move in, okay? So how can we find this region? This region, we will find it using this formula here. We will combine the mask that related with each frame that we consider in the generation process. Let's say that we will consider the last 10 frames. So we will take the mask from each frame in the last 10 frames and we will combine them. We will combine all of them together. So we will get just one mask. And here is our face region. The face region that our generated character, the face of the generated character, will move in. By doing this, you will improve the consistency of the character's motion across the clips. Actually, we call the frames that we consider in the generation process by clip. So, when you want to generate another frame and you will add it to the last, for example, 9 frames, you created another clip. And for this clip, you will get another mask. This mask will be slightly different from the previous mask because here this mask created by considering the mask of the last frame that you want to generate, and you removed the mask of the first frame in your clip, in your previous clip. So it will be changed a little bit. Now let's say that we have our mask, let's call it a clip mask or face region mask. Now what we will do, we will pass this face region mask through this face locator, which is just a model that has a bunch of convolutional layers. These layers, we will pass this mask through them to get an embedding. So now we encoded our face region mask. What we will do now, we will add this new representation for our face region mask to our noisy latents. Okay? By doing this, we will be able to control where the character face should be generated in our generated frames. The last thing that we need to control is the motion frequency. We don't want from the head to move very fast. So we want to add the target head motion speed in the generation process. So how can we do that? Firstly, we need to find the speed value, okay, which is the rotation velocity of the face in a frame F. So now we have the rotation velocity of the frame F. What we will do now, we will divide the region of speeds into discrete speed buckets. So now we have these speed buckets. Each one will represent different velocity level, and each bucket will have central value and a radius. As you can see here, here is the motion velocity of frame F. for the head in frame F. And as I said previously, for each bucket we have central value and a radius. Now what we will do, we will convert this velocity, this speed value, to this vector s. But how we can do that? Now what we will do, for each bucket in our speed buckets, we will subtract the center of the bucket from the actual speed of the frame F, and we will divide the result by 3 times the radius of the bucket. By doing this, you will make sure that the difference between the actual and the center of the bucket will not be that much. It's like doing normalization for the difference to make it not that big. After that, we will take tan h hyperbolic tan for the result to make the result between 1 and -1. We don't want to make it greater than that. And we will get a vector, okay? This vector, the number of elements in this vector, will be equal to the number of the buckets, the speed buckets. And here we will do same as what we did with audio signal, the audio signal. Here we have this embedding, which has the following. It will has the speed vector, let's call it speed vector, that we computed using this formula. We applied this formula for each speed bucket to get this vector, the vector of the current frame. And we will also do the same for the previous frames and the next frames in the reference video that you have. We will apply this formula to get many vectors from here and here. We will aggregate all of them together to get this new embedding. And here is the shape of the embedding, the speed embedding that we will get. The first dimension is the batch dimension. The second dimension represents the number of frames that we considered here. Here we will take the previous M frames and the next M frames. Okay. And the third dimension, which represents the number of speed buckets dimension, which is equal to D. Okay. We will pass this thing through our multi-layer perceptron layers, and we will get this speed embedding. Now we will use this speed embedding in the temporal blocks. As you can see here, we have this attention layer. Here we will repeat this speed embedding vector to make it like an image with width and height. Okay, so we can use it with this attention layer to implement a cross attention mechanism that operates between the speed features and the reshaped feature map across the temporal dimension F. So now we learned how to specify the target speed. Thanks for watching. Hi, in the previous section we talked about EMO model. In this section we will take another model to do portrait image animation. Here we will take a brief introduction about how their model works. We will not go in depth, but the most important thing that I want to teach you is how to use this model, okay? Let's try to understand how this model works. Firstly, we will compress our reference image using our variational autoencoder, okay? And we will pass it through our reference network, which is something similar to what we saw previously in EMO model. By doing this, you will make sure that the global features of your generated frames will have the same global features of your reference image. And at the same time, we will also pass this reference image through this face encoder. The purpose of this component, this new component, is to produce high fidelity portrait identity features. We will use this component, the output of this component, in both our reference network and the network that we will use to create our video. And as you can see here, we will use these cross attention layers to inject the output from this face encoder in these layers. Okay, we have also this audio encoder. This audio encoder component will take our audio as input and it will convert it into embedding. And here we will inject the output from this audio embedding component to the cross tension layer. By doing this, you will make your audio able to also affect on the generated frames from your Stable Diffusion model. And here what we will do, we will focus just on the most important things in the output of our cross attention layer to make things easier for our network. Here what we will do, we will generate 3 masks from our reference image. The first mask will focus on the pose region, and the second mask will focus on the expressions region, and the last mask will focus on the lip region. We will multiply each one of these masks with the output of our cross attention layer, and finally we will get 3 outputs. We will merge them together using this adapter component, and we will get just one final output, which will pass it through the rest layers. And finally we have temporal attention layers. These layers will make sure the character in the generated keyframes will move smoothly, which means when we want to generate a frame, this frame will be depend on the previous frames also, previous generated frames. And that's it. In the next lecture we will learn how to use this model. Thanks for watching. Hi, in this lecture we will learn how to use our portrait image animation model that we talked about in the previous lecture. This model, it is available in Hugging Face community. Okay, its name is Hello model. If you want to search about it here, we just need to type hello like this, and we should go to spaces, and we should click on this one here, and that's it. To make this model work, you should duplicate the space and run it on your own profile using a private GPU, okay, which costs $0.8 per hour. So you should click on this button here, and you should put your information and the information of your master card. Okay, now this model, it is available in my profile, so I just need to click on profile, and click on this hello, and that's it. Now I can use this model from Hugging Face community. Now let's talk about the requirements. Firstly, the reference image should cropped into squares, okay? Which means that the height dimension and width dimension should be similar. And the second thing is that the face should be the main focus. The face should be facing forward with a rotation angle of less than 30 degrees. Okay? Now let's talk about our driving audio. This driving audio should be in WAV format. Okay? And it must be in English, since the training data that they use to train this model only in this language. And you should ensure that the vocals are clear and background music is acceptable. Now what we will drag and drop our image to this place here, and we will create an audio file by clicking on this symbol here. Let's start with loading our reference image. Here I have this image. As you can see here, the height dimension, it is lower than the width dimension. So let's crop this image to make the height equal to the width. Firstly, I will open it with Paint program. Okay. And here is the width dimension and the height dimension. And now what we'll do, we will click on select. Okay. And we will select this region here. What we will do now, we will try to make the width equal to the height. Okay. Let's drag it and put it here. And let's drag this thing and put it here, and that's okay. We have 1620 and width and 1620 height. Let's save this. And now what we will do, we will drag this image and put it here. So let's drag and put it here. That's okay. Now let's create our audio file. We should click on this symbol here, and we should say what we want this character to say. So let's click on it and click on record. Hi, how are you? I hope you're doing well. Click on stop. Now we will click on generate. Okay, and now it will try to generate our animation. And here's the result. Let's click on this symbol here. Hi, how are you? I hope you're doing well. We can say it's good. We have another result. Hi, how are you? This one it is better. And now we have this image that we created previously using Hugging Face with Stable Diffusion 3 medium. Now what we will do, we will save it in our local machine, and after that we should go to this place here. Actually, I cropped this image previously using Paint program. And now we will drag and drop our image here. And now we should click on generate to create our video. Okay. And here is another result. Let's run this. Hi, how are you? I hope you are doing well. This one actually it is very good. That's amazing. Thanks for watching. Hi, in this lecture we will answer this question: what is diffuser's package? It is a very popular package that has many different diffusion models for generating images, audios, and even 3D structures of molecules. Diffusers package makes it easy for us to use these large diffusion models without any effort, and it will make us able to train these models easily also. This library has three main components. The first component is state-of-art diffusion pipelines. We will use these pipelines to do inference easily. The second main component is versatile noise schedulers to optimize the balance between the speed and the quality in the generation process. The last component is there are many pre-trained models that we can use as a building blocks along with the schedulers to create your own complete diffusion systems. Thanks for watching. Hi, in this lecture we will install diffusers package and all the required packages. And we will also create a pipeline object and we will use it to generate images. To do that, firstly we will type pip install -- upgrade. Here we will install diffusers package and accelerate package and finally transformers package. We will use this accelerate package to speed up the generation process, or in other words, to make the reverse diffusion process faster. And we need to install this package, transformers package, to run the most popular diffusion models like Stable Diffusion model. Let's run this up. Now we will create a pipeline object to do inference. Firstly, we need to import diffusion pipeline class. So we will type from diffusers import diffusion pipeline. Okay. Now we will create a pre-trained pipeline object. We will type pipeline equal to, here I will use this diffusion pipeline class. We will put diffusion pipeline dot from underscore pre-trained, and here we will open these parentheses, and here we will pass the name of the diffusion model that we want to use. Here I will use this diffusion model, Stable Diffusion version 1.5, which is available in Hugging Face community. Firstly, I will copy the name of this diffusion model by clicking on this symbol here, and I will put the name of this diffusion model that I want to use in this pipeline object in this place here, and I will make use save tensors argument equal to true. Why I did that? Let's go back to Hugging Face community. Let's click on files and versions, and as we can see here, this file here represents our diffusion model but with save tensors format, and this one here it is our stable diffusion model but with checkpoint format. We want to load this one because save tensors format is more secure and fast file format for saving and loading the model. So to do that, I will make use save tensors argument equal to true, and I will click on run, and that's it. Now let's see what is inside this pipeline object. As you can see here, we have many things inside this pipeline object. Okay, like image encoder and safety checker, scheduler, text encoder, tokenizer, variational autoencoder, U network, etc. Now I will send this pipeline object to my GPU to make the generation process faster. So I will type pipeline.to, and here I will open these parentheses and I will put coda, and that's it. Now I will use this pipeline to generate one image, or in other words, to do inference. So here I will type image equal to pipeline, and I will open these parentheses, and here I will describe the image that I want to generate by using this diffusion model. For example, an image of a ball dot images, and here I will open and close these square brackets and I will put 0 between them, and that's it. Now let's run this cell. Now we are doing a reverse diffusion process to generate our image. And now let's see what is inside this image variable. And here's our image. It is just a ball. That's great. Now let's save this image. We just need to type image. Let's save. And here we should pass the name of the file that will contain this image inside it. So let's make the name of this file image of a ball dot, and here we will put the format. Let's make it, for example, PNG, and let's run this cell. Let's click on this symbol here, and as you can see here, here's the file that contains this image, the image that you generated previously. Let's click on it, and that's it. You can download it on your local machine by clicking on these three dots and clicking on download button, and that's it. Now let's change the scheduler inside our pipeline and see if we can get better results or not. So what we will do here, we will import Euler discrete scheduler from diffusers package. So from diffusers import Euler discrete scheduler. And now let's replace the current scheduler with this new scheduler. So we will type pipeline dot scheduler equal to, here we will put this class Euler discrete scheduler dot from configurations, and here we will pass the configurations that we used with the original scheduler. So how can we do that? We just need to type pipeline dot scheduler dot config, and that's it. So now we replace the original scheduler with this new scheduler, but with the same configurations. Okay, now let's use our pipeline like what we did previously. Image equal to pipeline dot, and we will open these parentheses. Now let's use our pipeline again like what we did previously. Let's put it here and let's click on run. Now let's see the generated image. And here's the result. Actually, the first image that we generated by using the original scheduler, it is better than this image that we generated by using the new scheduler. Now try to use this scheduler, DDPM scheduler, and see if it is better than the previous schedulers or not. Now let's say that you want to generate many images at once. In other words, we want to increase the batch size. How can we do that? Firstly, we need to create a function. Let's call it get inputs function. This function will take just one argument, which is batch size argument, and let's make it by default equal to 1, for example. And here what we will do, we will create this variable, prompts variable, which is equal to the batch size times, here we will open these square brackets and we will put our prompts. Here what we will do, let's say that the batch size equal to 4, which means that we will repeat our prompt 4 times, okay? Which is something important because here you want to generate 4 images. And we want to use the same prompt to generate all these images. And here you will make the number of inference steps equal to 20. So here you need just 20 steps to generate, for example, let's say 4 images if you made batch size equal to 4. And here what we will do, we will return this dictionary. So here we will type return and we will open these curly brackets. The first key in this dictionary is a prompt, and the value of this key is a prompts list. This list will have, for example, if batch size equal to 4, it will have 4 elements. And the second key is number of inference steps, and the value of this key, it will be equal to 20. Okay, and that's it. Let's run this cell. Now we will import make image grid from diffusers.utils. So what we will do, we will type from diffusers.utils import make image grid. We will use this function to create a grid of images. Now what we will do, we will create this variable, images variable, which is equal to pipeline, and here we will open these parentheses. Here what we will do, we will type star star, and here we will call this function. So we will put get inputs here, and here we will pass the batch size. Let's make it equal to 4, which means that we want to create 4 images at the same time. And here we will type dot images. Now we will use this function, make image grid function. So we will type make image grid function. We will open these parentheses. Now we will pass this variable, images variable, and the size of the grid. This grid will have 2 rows and 2 columns. Okay, let's run this cell. And here is the grid. We have 4 images in this grid, as you can see here. Here's the first image, second image, third image, and fourth image. That's great. But the problem actually, when you run this cell again, you will get different images. Let's see that. As you can see here, now the images, they are different from the previous images. How to solve this problem? We just need to go back to our get inputs function. Now we will create this variable, generates variable, which is equal to, we will open these square brackets. Actually, we should import torch package. Okay, now we will put torch.generator. We will open these parentheses, and we will put Skoda here because we will use our GPU dot manual seed. We will open parentheses. We will open these parentheses and we will put I between them for I in range batch size. Here we should type torch actually. Now here we created a loop. In the first iteration, the value of this variable I will be equal to 0. Okay, so the generator at this case will be with seed 0. In the second iteration, the value of this variable I will be equal to 1. So the second generator, the seed of the second generator will be 1. In the third iteration, the value of this variable I equal to 2. So the third generator in this list, the seed of the third generator in this list will be equal to 2. And in the fourth iteration, the value of this variable I equal to 3. And the fourth generator in this list, the seed of the fourth generator in this list will be 3. By fixing the seeds, you will be able to reproduce the same images again and again and again. And here we should add another key to the dictionary that we will return, which is generator key. The value of this key should be equal to generators list, and that's it. Now we will run the cell and we will generate our images. And here is the result. Now let's run this cell again to see if we will get the same images or not. As you can see here, we got the same images. That's great. Previously, we changed the original scheduler inside our pipeline with another one, and you can also change the variational autoencoder in your scheduler with another variational autoencoder. So firstly, you need to import autoencoder KL class from diffusers package, and after that you should install the variational autoencoder with this path stability AI /sd variational autoencoder ftmse, and you should use from pre-trained method inside your autoencoder class to load this variational autoencoder. And if your pipeline it is available in your GPU, at this case you should send your variational autoencoder to your GPU, and you should make your pipeline.variational autoencoder equal to your new variational autoencoder. So try to do it and see the results, if they are better than the previous results or not.
In this video, we will see how we can compare two arrays to see if two arrays are exactly the same thing. So in this case, you can see I've declared two arrays, numbers 1 and numbers 2, and you can see that they've got exactly the same values at the same positions. Okay, so in this case, we could go and say if numbers 1 is the same as numbers 2, and then print out, if they are the same, we're going to print out they are the same. And if they're not the same, we're going to go to the else, and we print out they are not the same. Okay, so let's look at the logic of this one quickly. If we print it out and we run it now, let's just run this one, otherwise still running the previous example. So if I run this one now, you can see it says they are not the same. So the thing here is you can see the two arrays are exactly the same. It's 2, 4, 6, 8, 10. But when we test using the double equal sign operator there, it will say they are not the same. So remember, the same as with strings, if you try to compare objects with a double equal sign, then it means that you're comparing the memory locations of these two objects. And that's why you cannot compare using the double equal sign. So essentially, in memory, this object gets created somewhere, and the memory location of it will be stored into numbers 1. This one gets created somewhere, and the memory location of it will be stored in numbers 2. But where they get created is two different places, although the values they have is exactly the same way. So that's why we cannot compare using a double equal sign there, because the double equal sign is comparing whether their memory locations are exactly the same thing. So if I do this now, if I say that one is equal to numbers 1, then it means that I'm essentially copying the memory location of numbers 1 into numbers 2. So if I run this now, it will say they are the same. So why are they now the same? Because I've copied the memory location of the two. Okay, so numbers 1 will point to this, and numbers 2 will point to what number 1 is pointing, and that's also the exact same object. So I'm pointing both now. Numbers 1 and numbers 2 is now essentially pointing to the exact same object. So if I change something in numbers 2 or change something in numbers 1, it will go and make the change to the same array. Just go back and get back to that value. Right, so there we've got the two arrays again. So this is the wrong way of doing it. You cannot compare two arrays by using the double equal sign. So how then do we compare two arrays? So in order to do this, I'm going to use a Boolean variable, and I'm going to start this, or call it arrays equal. And let's set this one to true. So we're going to assume that the two are true. Unless we can prove otherwise, then we'll set the value to false. And I'm also going to need a counter there, or a variable, my loop control variable, where we're going to use later on to test for the values. Okay, so I'll need two variables, arrays equal, and then an index value to basically check every value inside of the arrays. Right, so step number 1 is, let's test if the two arrays are of the same size, because if this one can only store 3 values and that one can store 5 values, then we already know that the two are not the same. Remember, when we're testing two arrays, you're not going to always see what values are inside of them, because then it's easy to just decide whether they're the same or not. So we first need to go and test then if the length of the two arrays are the same. So in this case, we're going to say if numbers 1 dot length, that will give me, numbers 1 dot length will give me 1, 2, 3, 4, 5. That will give me a length of 5. If numbers dot length is the same as numbers 2 dot length. Okay, so in this case, we're testing whether the two lengths of the arrays are the same. But because we've got this arrays equal variable to true, let's make this test not equal. So if they're not equal, we're going to set arrays equal to false. So this is step number 1. Step number 1, checking whether the two lengths are the same. Now it's going to give us this condition is always false because we've got two hard-coded arrays. But let's say you got this arrays from somewhere else, from a file or wherever, then this is the way you're going to test this. So we check first whether the lengths of the two are the same. If they are the same, then we can carry on. We're going to go to a while loop, and we're going to test for this arrays equal. So if the arrays equal then was set false here, we will never enter this while loop at all. So I'm going to use an AND operator here. So I can step through the array, but also not get into the array if the arrays equal are set to false. Okay, so in this case, I'm going to say while arrays equal is basically true, and also the I is less than one of the length of the two arrays. So I'm going to say numbers 1 dot length, because at this stage, if arrays equal is still true and it enters the loop, we also know that numbers 1 dot length and numbers 2 dot length is exactly the same. So whether you use numbers 1 dot length here or numbers 2 dot length, it's the exact same thing. So let's look at the loop control variable here. You can see there we set the index value to 0. So that's where we're going to start in the arrays to compare values. So what we want to do in this while loop now is to compare, to check, is the 2 equal to the 2? Is the 4 equal to the 4? Is the 6 equal to the 6? And so forth. So we're comparing positions here, or index values. So I'm going to start the index off at 0. And then I'm going to test to make sure it's less than numbers.length. This is essentially the same that we're doing in this for loop here in the previous video. We start at 0 and we go up until numbers 2.length. So this is also what we're doing here. We start at 0 and we go to I less than numbers.length. And then somewhere at the bottom, we must say I++. So then you can see we're essentially doing the same as this for loop that says we start at 0, we test for that value, and then we increment again. And that's exactly what we did here. We're just using a while loop. And now why am I using the while loop? Because I also need to test for this array equal. So this while loop will run while array equal in the first place is still set to true. If it's false, it will never enter this while loop because of the AND operator there. The AND operator says both sides must be true. So this must still be true. It's still equal. And at the same time, it must be less than the length of the array. Okay, so what do we do then inside of this while loop? I'm just going to do a simple test there to say, if numbers, let's start with 1 there, and then we're going to go to that specific, numbers 1, go to that specific index value and test both of them. So obviously the index is going to start at 0. So I'm testing now if numbers 1's value is not equal to numbers 2 at the same index. And if they're not the same at that specific positions, we will set arrays equal to false again. And then this will also cause the array to stop then, because then the next time not the array, the while loop to stop. When it goes back to the while loop and it tests for array equal, it will see it's false now and stop the loop from executing. So this while loop then, it enters while the arrays equal is still true, and it runs through every element. So it's going to start at 0 and compare numbers at position 0, numbers 1 at position 0, if it's the same or not the same as numbers 2 at position 0. So if the 2 is not the same as the 2, we'll set arrays equal to false. Then the loop runs again. If the 4 is not equal to the 4, we will set it to false. If the 6 is not equals to the 6 and 8 and 8 and 10 and 10, we're going to compare them the whole time. And if just one of these values are not the same, we set arrays equal to false, and it will exit this loop. And then at the end of the loop, we can just go and test this arrays equal variable. So I'm going to say if arrays equal, and remember by saying if arrays equal, it's essentially the same as saying equals true there. But because it already gives you a true or a false value, you don't need to do that. So I'm going to say if arrays equal, I'm going to print out they are the same. And the else there will be when they're not the same. So there's something wrong there. They are definitely not the same. We're going to print out they are not the same. So let's run this quickly. And after running it, you can see then that it says they are the same. And obviously they are the same. We've got the values there. So let's just change one of them there. And I'm going to set that one to a 5, which will make them not the same. So the first test, you can see there they are not the same printed out. The first test there of checking whether the lengths are the same will be true. So it will enter the while loop, check first the 2's, see it's the same. But when it checks the 4 and the 5 there, it will see, they are not the same. So we're going to set arrays equal to false. When it tries to enter the loop again, that part is false. The loop will exit. And then this one will not be true. So it will go to the else part and that will print out they are not the same. So obviously if you've got 2 arrays there and the 2 arrays are not sorted, you will need to sort them first before doing this specific test. But this is how you can compare 2 arrays to see if the 2 values are the same or not.
Hi, previously we saw that by using diffusers pipelines it will be easy for us to do inference. But how these pipelines work? In this lecture we will answer this question. Okay. Firstly, we will import DDPM scheduler class and uNetwork 2D model from diffusers package, and we will run this cell. Here we will load the scheduler that we want to use to do forward diffusion and reverse diffusion process. So scheduler equal to DDPM scheduler dot from pretrained, and here we will put the name of the diffusion model that we want to use. Here we will use DDPM cat 256. This diffusion model, it is unconditional diffusion model, and this one will generate images for cats. And here we will load the uNetwork that we will use. So model equal to unit 2D model dot from pre-trained, and here we will put the name of the diffusion model that we want to use, and we will make use save tensors equal to true to load the model, the network, the U network with the save tensors format. And we will send this model, this U network, to our GPU. Let's run the cell. Now let's specify the number of time steps. Let's make the number of time steps equal to 50. So here we will type scheduler dot set time steps. We will open these parentheses and we will put 50 here. Let's run the cell. Now let's print the time steps. And here is our time steps. Now we will create a random noise. Firstly, we will import torch package, and here what we will do, we will extract the size of the input that our U network expects, and we will save it in sample size. So sample size equal to model.configuration.sample size. Okay. Now we will create our noise, and the size of this noise should be equal to this sample size. So noise equal to torch.random, and here we will open these parentheses, and we will open these parentheses also. Now what we will do, we will put the batch size, we will make it equal to 1, and we will make the color dimension equal to 3, the length of the color dimension equal to 3, and the height equal to sample size, and the width equal to the sample size. And we will send this noise to our GPU. Let's run the cell. Now we will make this variable input equal to our noise. We will pass this noise through our U network. Here what we will do, we will create this loop here. We will create this context manager to avoid computing the gradients, because here we don't need to update our U network. And here our U network will predict the noisy residual. So noisy residual equal to model, and here we will pass our input and the current time step dot sample. And now we have our epsilon. Now we will pass this epsilon, predicted epsilon, through our scheduler. So previous noisy sample equal to scheduler.step, and here we will pass our predicted epsilon, the current time step, and our input dot previous sample. So now we have our xt minus delta t, and we will make our input xt equal to xt minus delta t. We will do this thing again and again until reaching time step 0. Now let's run the cell. Finally, we want to display the generated image. So firstly, we will import image class from PIL package, and we will import numpy as MP. Now what we will do, we will divide our input by 2. This input, which is x0, predicted x0, we will divide it by 2, and we will add 0.5 to the result. And here we will make the highest possible value equal to 1 and the lowest possible value equal to 0. And here we will remove the batch dimension by using squeeze method. And now what we will do, we will change the order of the channels in this variable, image variable. We will make the height dimension the first, and the width dimension after that, and finally the color dimension. And we will multiply the results by 255. And here we will make them right numbers, not fractional numbers. And we will make the type of the resulted tensor equal to unsigned integer 8, and we will send our result to our CPU, and we will convert this PyTorch tensor to NumPy array, and here we will create image object, image equal to image.from array, and here we will pass our image. And now let's see our generated image, and that's it. Okay, here is our image. Now let's try to understand how the conditional pipelines work. Firstly, we will import image, class, PyTorch, package, and clip text model and the clip tokenizer from transformers package, and we will import autoencoder KL and UNetwork 2D conditional model and PNDM scheduler from diffusers package. Let's run this cell. Now we will load our variational autoencoder VAE equal to autoencoder KL class dot from pre-trained, and here we will pass the name of the diffusion model, and here we will take the variational autoencoder folder. So here we will make subfolder equal to VAE, and we will make use save tensors equal to true. And now we will load the tokenizer. So tokenizer equal to clip tokenizer dot from pre-trained, and here we will also pass the name of the diffusion model that we want to use, and here we will take the tokenizer folder, so we will make subfolder equal to tokenizer, and here we will load the text encoder. So text encoder will be equal to clip text model dot from pre-trained, and here we will also pass the name of the diffusion model that we want to use, and here we will take text encoder folder, and we will make use save tensors equal to true, and here we will load the UNetwork that we want to use. So UNetwork equal to UNetwork to the conditional model dot from pre-trained, and here we will pass also the name of the diffusion model that we want to use and the folder that we want to take, which is unit folder, and here we will make use save tensors equal to true. Now we will run this cell. Now we will import UniPC multi-step scheduler from diffusers package, and here we will load our scheduler. So scheduler equal to UniPC multi-step scheduler dot from pre-trained, and here we will pass the name of the diffusion model that we want to use, and here we will take the scheduler folder. Now let's run this cell. Now we will send all these things to our GPU, so we will type variational autoencoder dot to torch device, which is CODA, our GPU, text encoder dot to GPU, UNetwork dot to GPU. Here we will create our prompt, which is red ball. Here we will specify the height, which is 512, and the width, which is 512 also, and the number of inference time steps, which is equal to 25, and the guidance scale equal to 7.5, and the generator equal to torch.manual seed 0, and we will make the batch size equal to the length of this list, which is equal to 1. Now we will pass our prompt through our tokenizer, and we will make padding equal to maximum length, and maximum length equal to tokenizer.model max length, and we will make truncation equal to true and return tensors equal to pt. Now we have our text input, and now we will use our text encoder model to get text embeddings. So text embeddings will be equal to text encoder, and here we will pass text inputs dot input IDs dot to GPU through our text encoder model, and we will get the text embeddings. Now we will find the maximum length. Maximum length will be equal to text input dot input IDs dot shape, and here we will put -1 between these two square brackets. So now we have the maximum length, and now we will make unconditional input equal to tokenizer, and we will open these two parentheses, and here we will create this list, and we will multiply this list by the batch size, which is in this case equal to 1. Okay, we will make padding equal to maximum length, and we will make maximum length equal to the maximum length here, and return tensors equal to pt. So in this case we will get PyTorch tensor. So now we have our unconditional input. Let's get unconditional embeddings, which is equal to text encoder, and here we will pass our unconditional input dot input IDs dot to GPU through our text encoder model to get our unconditional embeddings. Now the text embeddings will be equal to torch.concatenate, and here we will open these two parentheses and these two square brackets. Here we will put unconditional embeddings, comma, text embeddings. Now we will create our noise. So latents equal to torch.random. Here we will open these two parentheses. Here firstly we will pass the batch size, which is equal to 1, and unetwork configuration.in channels, which means the length of the color channel, which is equal to 3, comma, the height divided by 8, comma, the width divided by 8. So by doing this, the size of the latents will be equal to the size of the things that we will get from our variational autoencoder. Okay? Or in other words, the size that our U-network expects. Now we will scale our latents. So latents equal to latents times scheduler.initial noise sigma. Now we will import tqdm class from tqdm.auto, and we will set the number of time steps, scheduler.set time steps, and here we will pass number of inference steps, and here we will create this loop. We will pass it through each time step from time step T capital to time step 0, and here what we will do, we will multiply this latents list by 2, and we will get this latent model input, and now we will scale this latent model input. So latent model input equal to scheduler.scale model input, and here we will pass our latent model input and the current time step. And now what we will do, we will use our U-network to find the predicted epsilon. Here we will pass our latent model input, the current time step, and also the text embeddings. We will make encoder hidden states equal to text embeddings. We will pass all these things through our U-network to get our predicted epsilon. And now what we will do, we will split our noise prediction to two things: noise prediction unconditional and noise prediction text. And here what we will do a classifier free guidance. So noise prediction equal to noise prediction unconditional plus the guidance scale times the noise prediction text minus the noise prediction unconditional. And here we will do reverse diffusion. We will move one step backward. Latents equal to scheduler.step, and here we will pass our predicted epsilon, the current time step, and the latents dot previous sample. And we will do this thing again and again until reaching time step 0. Now let's convert the resulted latent at time step 0 to an image. How can we do that? Firstly, we will multiply our latents by 1 divided by 0.18215. And after that we will use the decoder part of our variational autoencoder to get our image. Now if we want to display this image, That's very easy. We just need to firstly divide this image by 2, and we will add 0.5 to the results, and we will make the lowest possible value equal to 0 and the highest possible value equal to 1. We will remove the batch dimension, and here we will change the order of the channels, and we will multiply the result by 255, and we will convert the type of the resulted tensor to unsigned integer. We will send them to our CPU, and we will convert the tensor to numpy array. We will make the numbers inside our image numpy array equal to right numbers, and here we specify the type, and here what we will do, we will convert this image to image object, and here is the result. That's great. Thanks for watching. Hi. Any stable diffusion model, you can use it to do different tasks, not just passing a text and getting an image, and we will see that now. Here we will import auto pipeline for text to image from diffusers package, and here we will import PyTorch package. Now what we will do, we will create our pre-trained pipeline. So pipeline equal to auto pipeline for text to image dot from pre-trained, and here we will put the name of our stable diffusion model, the stable diffusion model that we want to use, the precision of this stable diffusion model. Let's make it torch.float16. By doing this, you will reduce the size of your model to the half, and at the same time you will make it faster. Save tensors equal to true, and here we will send our pre-trained pipeline to our GPU, and here we created our prompt. Now we will pass this prompt through our pre-trained pipeline, and here we specify the number of inference steps, and we made it equal to 25, and now we will get this image here, and here is the result. Now let's use the same stable diffusion model to do another task like image to image. To do that, we will import auto pipeline for image to image from diffusers package, and we will import our PyTorch library, and we will import requests package, and we will import image class from PIL package, and bytes.io from IO package. Now what we will do, we will create our pre-trained pipeline. Pipeline equal to auto pipeline for image to image, data from pre-trained, and here what we will do, we will put the name of the stable diffusion model that we want to use and the precision, and we will make use save tensors equal to true, and we will send our pre-trained pipeline to our GPU, and here we created this prompt equal to a portrait of a dog with dinosaur body, and here we have this URL link. Here we will load an image from this URL, this image here. Okay, now we will use requests package to get the image. So response equal to requests dot get, and here we will pass our URL link, and now we will convert the content of the response to an image equal to image class dot open, and here we will use bytes.io, and we will open and close these parentheses, and here we will pass response dot content, and we will convert the order of the channels, the color channels in the resulted image to RGB. We will make any dimension greater than 768 equal to 768 by using thumbnail method. So image.thumbnail, we will open these parentheses, and these parentheses 768, 768. Finally, we will use our pipeline image equal to pipeline, and here we will pass our prompt, our image, the number of inference steps, which is equal to 200, and strength, the noise strength, equal to 0.75, and the guidance scale equal to 7.4. And here is the result. As you can see here, it is something similar to this image here, but the face, it is the face of a dog. That's great. Now we use the same Stable Diffusion model to do another task, to edit our reference image based on our prompts. Thanks for watching. Hi, in this lecture we will learn how to find the compatible schedulers for our diffusion pipeline, and we will try to use them. Firstly, I loaded this Stable Diffusion model, rev and mated diffusion model. Okay, and I send it to my GPU, and I passed this text to my pipeline: digital painting man, half body, wearing t-shirt, and here is the result. Now let's find the compatible schedulers for our Stable Diffusion pipeline. We will type pipeline dot scheduler dot compatibles, like this, and here's the result. Now we have many schedulers. We can try each one of them and find the best one. Firstly, we will fix the seed. Okay, we will create generator variable which is equal to torch dot generator, and here we will open these parentheses, and here we will specify the device which is equal to coda dot manual underscore seed. We will open these parentheses and we will put 0 between them. So now we fixed the seed, which is something important if you want to compare between the schedulers. Let's say that you generated an image, and let's say that you want to keep some of its characteristics, but at the same time you want to get better image. To do that, you just need to fix the seed and changing, for example, the scheduler. By fixing the seed, you will start with the same xt capital at each time. Now what we'll do, we will pass our prompt, which is this prompt here. Let's copy this prompt and put it here, and that's it. And we need to import PyTorch package, and let's run this. And here is the result with our original scheduler. Now let's take another scheduler to see if it will enhance the quality of this image or not. Here I will use DDIM scheduler. So let's import DDIM. As you can see here, I will import DDIM scheduler class, and here I will create my DDIM scheduler object with the same configurations that is available in our original scheduler, and I will put this new scheduler in pipeline.scheduler attribute, and that's it. Now let's run this cell, and here's the result. I think it is similar to the previous one with very small changes. Let's take another one. Let's take this scheduler and see. And now I pass this new scheduler to my pipeline, and here's the result. And let's try to use for example this one. Okay, let's copy the name of this scheduler and put it here and here, and let's run this cell. Now let's generate the image. Now let's see our generated image, and here is the result. As we can see here, there are just small changes in our resulted image. So take the one that you prefer. Hi, in this lecture we will learn how to use LoRa models to change the style of the generated images. Firstly, we will install transformers and accelerate package and PEFT package and diffusers package. Here we will import diffusion pipeline from diffusers package, and we will import PyTorch package, and here we will specify the diffusion model that we want to use, and here we will create our pre-trained pipeline equal to diffusion pipeline dot from pre-trained, and here we will pass our pipe ID and the precision of the pipeline, and we will send them to our GPU. Now we will load LoRa weights, so we will type pipeline pre-trained pipeline dot load LoRa weights, and here we will put the path of LoRa weights and weight name toy face as the xl.save tensors. All these weights, they are available in this file, and here you can choose the adapter name that you want. Here we made it equal to toy. Now let's run this cell. Now we will create our prompt equal to toy face of a hacker with a hoodie, and here we made LoRa scale equal to 0.9, which represent the effectiveness of this LoRa style on the generated images. Now image equal to pipe, and here we will pass our prompts, the number of inference steps, and here we will pass this dictionary to cross attention keywords. We will make the value of this key scale equal to LoRa scale, and here we will specify our generator, and that's it. Now let's run this cell, and here's the result. Okay, that's amazing. Now let's say that you want to mix the styles of two LoRa weights. How can we do that? In the previous video we added this adapter, toy adapter, to our pre-trained pipeline. Okay, now we will add another adapter, and we will mix these two adapters together to get a new style. The second adapter that we will add, the second LoRa weights that we will add, is pixel art XL. So we will type pipeline.LoRa load LoRa weights, and here we will put the path of these LoRa weights, and here we will make weight name argument equal to the file that has our LoRa weights that we want to download, pixel art xl.save tensors, and here we will call this adapter pixel adapter. So we will make adapter name equal to pixel. That's it. Now what we will do, we will use just this adapter, and after that we will use two adapters together. So if we want to select between adapters in your pre-trained pipeline, you just need to use set adapters and passing the name of the adapter that you want to use. So here we will type pipeline.setAdapters, and here we will pass the adapter that we want to use, which is pixel adapter. In this case, we will not use our previous toy adapter. Now we will create our prompt. which is our previous prompt. Image equal to pipeline. Here we will pass our prompt and cross attention keywords, and here we will use the same generator, and that's it. Now let's run the cell, and here's the result. Here's the generated image with our pixel LoRa weights style. Now let's mix these two adapters together. How can we do that? To do that, we just need to use again our set adapters. So we will type pipeline.setAdapters, and here we will open these two parentheses, and here we will open these two square brackets, and we will put the adapters that we want to use. We want to use pixel adapter and toy adapter, and here we will specify the weight of each adapter in the generated image. So here we will type adapter weights equal to, here we will create this list. Here's the weight of this adapter, which is 0.5, and the weight of this adapter, which is 1. Let's run this cell, and we will create our prompt and passing our prompt to our pipeline and all what we did previously. Now let's run the cell, and here's the result. As you can see here, this image has two styles, the pixel style and toy style. That's amazing, right? Now let's say that you don't want to use any one of the adapters that you have. How can we do that? We just need to type pipe dot disable LoRa like this. By doing this, you will not use any LoRa weights, so you will just use your Stable Diffusion model alone. Now let's say that you want to know the adapters that you added to your pipeline. You just need to use get list adapters. So you will type list adapters component wise equal to pipe.getListAdapters, and let's click on run. Now let's display this list, and as you can see here in our pipeline we have just two adapters, toy adapter and pixel adapter. Thanks for watching. Hi, in this lecture we will learn how to convert our text into video using AnimateDiff pipeline. Firstly, we will install diffusers package, accelerate package, and transformers package. And you should know that AnimateDiff pipeline needs a special adapter called motion adapter. So we need to load this motion adapter. So we will type adapter equal to motion adapter dot from pre-trained, and here we will pass the checkpoint of this adapter, and here we will make torch dtype equal to torch.float16, and of course we need to import many packages here, PyTorch package, and we need to load AnimateDiff pipeline and DDIM scheduler and motion adapter, and we need to export to GIF. Now let's run this cell. This adapter actually it is just a group of motion modules that work together to make sure that the motion in a series of images, generated images, looks smooth. And now we will load our Stable Diffusion model. Firstly, we will make model ID equal to, and here we will put the checkpoint of the Stable Diffusion model that we want to use. And now we will create our pre-trained pipeline. So pipeline equal to AnimateDiff pipeline dot from pre-trained, and here we will pass model ID, and we will pass the motion adapter. So motion adapter argument equal to adapter, and here we will make torch dtype equal to torch.float16, and here we will create our scheduler. So scheduler equal to DDIM scheduler dot from pre-trained, and here we will pass the checkpoint of the stable diffusion model that we want to use, and here we will take just the scheduler. So we will make subfolder argument equal to scheduler, and here we will make time step spacing equal to line space and beta scheduler equal to linear, and the steps offset equal to 1. And now we will add this scheduler to our pre-trained pipeline, and here we will enable variational autoencoder slicing, and we will enable model CPU offload to reduce the consuming of our memory. And here what we will do, we will use our pipeline. We will pass our prompt to our pipeline: masterpiece, best quality, highly detailed, ultra detailed, sunset, etc. And here we pass this prompt to negative prompt, so bad quality, worse quality. So we don't want to see bad quality and worse quality. And here we made a number of frames equal to 16, and the guidance scale equal to 7.5, and number of inference steps equal to 25. And here we fixed the seed, so generator equal to torch.generator CPU.manual seed, and here we put it 42. Now we will take the frames, so frames equal to output.frames. Okay, and now we will use export to GIF function, and we will pass our frames. So now we will see our animation in this file. Let's run this cell. Now let's click here, and here is our animation. Let's load it, and let's open it, and here is the result. That's great. And here we made a clip sample argument equal to false and beta scheduler equal to linear, because it is something important to make our animate diff pipeline works. Otherwise you will get bad animation. And now we will use animate diff video to video pipeline. Firstly, we will import image.io, requests package, PyTorch package, and we will import animate diff video to video pipeline and DDIM scheduler and motion adapter. And here we will import export to GIF and bytes.io and image class. Let's run this cell. Now we will load our motion adapter, and here we will create our pre-trained animate the video to video pipeline like what we did previously, and we will send it to our GPU. And here we created our scheduler, and we made clip sample equal to false and beta scheduler equal to linear. And here we enabled memory saving, and here we created this function load video function, and we will pass just one thing to it, which is the path of the video. And here we created this list, images list. So now if the path it is URL link, at this case we will use requests package to get our video. So response equal to requests.get, and here we will pass the link, and response.raise for status, and here we will get the content equal to bytes.io, and here we will pass response.content, and here video equal to image.io, get reader, and we will pass the content. Otherwise, we will pass the file path directly to our image.io.get reader. Okay, now we will pass it through each frame inside our video, and we will convert it into image object. So pil image equal to image.from array, and here we will pass our frame, and we will add this image to our images list, and finally we will return this images list. And now we have this link for the video, okay, that we want to load. So here we will call this load video function that we created previously, and here we will pass this link, which is huggingface.co /dataset /huggingface /documentation -images /resolve /main /diffusers /animated diff -video to video -input -1.gif. Okay, now we loaded our video. Let's use our pre-trained pipeline. Output equal to pipeline, and here we will pass our video. So video equal to video, this one here, and here we will pass our prompt, which is robot playing a guitar on a boat in the ocean, high quality. Actually here we have this animal. Now we will replace it with a robot, and here we passed our negative prompt, bad quality, worse quality, and here we made guidance scale equal to 7.5 and inference steps 25 and strength equal to 0.5, and here we fixed the seed. Now we will get these frames equal to output.frames, and now we will use export to GIF method, and we will pass frames to this file, and that's it. And here's the result. As we can see here, now it is a robot rather than a raccoon. That's amazing. Hi, in this lecture we will take another pipeline, which is audio LDM pre-trained pipeline. We will use this pipeline to generate an audio from a text, which means that we can also use the diffusion models to generate audios, not just images. Firstly, we will install diffusers package, accelerate package, and transformers package. Now we will import audio LDM pipeline from diffusers package, and we will import PyTorch library and SciPy library. And here we will specify the ID of the diffusion model that we want to use. So we will make this variable repo ID equal to, and here we will put the model ID, and here we will create our pre-trained pipeline. So pipe equal to audio LDM pipeline dot from pre-trained, and here we passed this ID, and we made torch d type equal to torch.float16, and here we sent our pre-trained pipeline to our GPU. And here we created our prompt, our text, which is tornado sound. And now we will use our pre-trained pipeline. So audio equal to pipeline, and here we will pass our prompt and the number of inference steps, and let's make it 10, and the audio length in second, which is equal to 5. So we want to generate an audio with 5 seconds. Dot audios, and now we have our audio. Let's use SciPy package to save our audio. So scipy.io.wave file.write, and here we will pass the name of the file that will contain our generated audio, which is Let's make it tornado dot wave, and here we will make the sampling rate equal to 16,000 and data equal to audio. Now let's run this cell, and here is our audio file. Let's download it, and here's the result. That's great. Here I changed the prompt to rain sound, and I will save my audio in this file, rain.wave, and let's see the result. That's great. Thanks for watching. Hi, in this lecture we will learn how to use depth map control net to control the output from our Stable Diffusion model. Firstly, you should install Accelerate package, Transformers package, Safe Tensors package, and Diffusers package. Now we will import PyTorch package and NumPy package as MP and image package. And we will also import DPT feature extractor and DPT for depth estimation from Transformers package, and we will import control net model from diffusers package, and we will also import Stable Diffusion XL control net image to image pipeline and autoencoder KL, and we will also import load image from diffusers.utils. Let's run this cell. Firstly, we will create this variable, depth estimator variable, which is equal to dpt for depth estimation data from pre-trained, and here we will pass the checkpoint ID, and I will send this model to our GPU, and here I created this variable feature extractor, which is equal to dpt feature extractor dot from pre-trained, and I will pass the same checkpoint ID. Let's run this cell. Now control net equal to control net model dot from pre-trained, and here we will pass the checkpoint ID and the variant floating point 16, and use safe tensors equal to true, and torch dtype equal to torch.float16, and I will send this control net to my GPU. And as you can see here, we will use control net depth as the XL 1.0 small. So this control net expects that the input to it should be a depth map. Okay. Now I will install our variational autoencoder. So VAE equal to autoencoder KL dot from pre-trained. And here I will pass the checkpoint ID and the torch dtype, which is equal to torch.plot16, and I will send this model to our GPU. Here I will create my pre-trained pipeline. So pipe equal to Stable Diffusion XL control net image to image pipeline dot from pre-trained, and here I will pass the checkpoint of the diffusion model that I want to use, which is a Stable Diffusion XL base version 1.0, and here I should pass the control net variational autoencoder, and I will send this pipeline to my GPU, and here I will enable model CPU offload. Now let's run this cell. And here I created this function, get depth map function. This function will take an image as input, and I will pass this image through our feature extractor that we loaded previously. So image equal to feature extractor, and here I will make images argument equal to our image, and I want to take a PyTorch tensor, so I will make return tensors equal to pt, and here I will type dot pixel values, and I will send the result to my GPU. Okay, now I will put this context manager to avoid computing the gradients, and I will use this depth estimator model to get the depth map. So depth map equal to depth estimator, and here I should pass the image dot predicted depth. So now we have our depth map. Here we will change the size of this depth map. So depth map equal to torch.nn.functional.interpolate, and here I will type depth map.nsqueeze1, and here I will pass the new size that I want, and I will make mood equal to bicubic and aligned corners equal to false. Here I will find depth minimum, which is equal to torch.aMinimum, and here I should pass our depth map and the dimensions 1, 2, and 3, and I will make keep dimension equal to true. And I will do the same thing here to find the depth max. Depth max equal to torch.amax, and here I will pass depth map, our depth map, and the dimensions 1, 2, and 3, and I will make keep dimensions equal to true. And here depth map equal to depth map minus depth map minimum divided by depth map maximum minus depth map minimum. It's like normalization. Okay, and here I will make this variable image, this tensor, which is equal to torch.concatenate, and here I will create a list, and I will put my depth map inside it, and I will multiply this list by 3, which means that I will repeat this depth map 3 times. So now I have 3 elements in the resulted list, and I will put them along the second dimension. Finally, I will change the order of the dimensions. So image equal to image dot permute. Here I will keep the first dimension in the same place, and I will put the height dimension here and the width dimension here, and finally I will put the channel dimension. Here I will send my tensor to CPU, and I will convert it into NumPy array, and I will multiply it with 255, and I will clip the values to make them between 0 and 255, and I will make the type of the array equal to np.unsigned integer 8, and I will return this image, which is our depth map. And here's my prompt, which is equal to a robot 4K photo. Here I will load an image, a reference image. Okay, and here's our image. It is an image for a cat. I will convert it into a depth map using our get depth map function. Firstly, I will specify the control net conditioning scale, which is equal to 0.5, and here depth map equal to get depth map, and here I will pass my image. Okay, here I changed the size of this image to 1024 times 1024, and I loaded this image using the load image function. Now let's run this cell, and now I will use our pre-trained pipeline to generate an image. So image is equal to pipeline, and here I will pass my prompts, and I will also pass our reference image and our depth map. So control image equal to depth map, and strength equal to 0.99, and inference steps equal to 50, and control net conditioning scale equal to control conditioning scale. And that's it. And here is the final result. That's really amazing. Hi, in this lecture we will learn how to install Automatic 1111 software. What is Automatic 1111? It is just a graphical user interface for Stable Diffusion. We can use this software to work with our Stable Diffusion models easily without coding. Here we will install Automatic 1111 software on Windows 11. You should know that if you have Windows 10 or higher than that, so you can install Automatic 1111 software in the same way. And you should also have NVIDIA GPU with 4 GB memory at least in your local machine to run Automatic 1111 software. Firstly, we need to install Python 3.10 version. So we will type here Microsoft Store. We will go to Microsoft Store like this, and here we will type Python 3.10 version, and here you should click on this place, Get Install App, to install Python with version 3.10. Firstly, you need to have an account on Microsoft. Okay, and you can install Python 3.10 from Microsoft Store. Let's click on this Get Install App. Click on Open Microsoft Store. Let's click on Privacy and Terms. As you can see here, I installed this Python version 3.10 previously. Here I can just update this Python 3.10, but I will not do that here. Now, if you installed previously any other version for Python, you should remove it. You click on Search here, Control Panel, and here we should write Add or Remove Programs, and we should click on this place here. Now we should remove all Python versions that we don't want here. As you can see here, here's the Python version that we installed, 3.10.6. Actually, I don't have any other Python versions here, just this one, 3.10.6. We will use this one to install Automatic 1111 graphical user interface. Now we will click on Search again, and we will open Command Prompts. So we will click here on CMD Command Prompt. Here we will type Python like this, and as you can see here, here's the Python version that we have, 3.10.9. So now we can say that we installed Python correctly. So now we will close the command prompt here. Now we will install Git. We will use Git to install and update Automatic 1111 software. So we will type here download Git for Windows like this, and we will click on this place here. We will click on Windows. Now if your machine it is 64-bit and your Windows it is 64-bit also, so you should click on this place here to download Git. Now you just need to click on install, nothing special here, to download Git in your Windows. I installed Git program previously. Now let's download Automatic 1111 software. Let's go to our command prompt like this. Now we will go to our desktop, so we will type cd desktop. Now what we will do, we will download automatic 1111 software. We will type get. As we know, we installed get program previously, so we can use this command get clone, and here we should pass the link of automatic 1111 repository. As you can see here, github.com/automatic 1111/stable diffusion web UI.get. Now what we will do, we will click enter to download automatic 1111 from GitHub. Now you should find automatic 1111 folder on your desktop, which is this one here, Stable Diffusion Web UI. Let's enter to this folder, and now we should click on web UI-user.bat. And here, this program will automatically install the requirements. From now on, we will use this program to run automatic 1111 software. We installed previously all the requirements. As you can see here, it will give you this URL. We will use it to run automatic 1111 software. We will put it here. And here's our automatic 1111 software. We have many things here. Text to image, image to image. If you want to specify which stable diffusion model that you want to use, you should select the model that you want to use between these models that you have here. By default, it will give you just this one, and I added these two models also. In the next lecture, we will learn how to add our own stable diffusion models inside automatic 1111 software. Now we will learn how to add these stable diffusion models in our automatic 1111. By default, it will give you this stable diffusion model, and this stable diffusion model, actually it is not that good, so we need to add better stable diffusion models like RPG v4. They used this RPG stable diffusion model to generate these amazing images. To add these amazing stable diffusion models in our automatic 1111 software, firstly we should download them in our local machine. Let's start with RPG v4.save tensors. Let's type RPG v4.save tensors. It is available in Hugging Face community. Let's click on this link. And now what we will do, we should click on files and versions, and we should click on download to download this stable diffusion model in our PC. As you can see here, it is available in downloads. We should copy this file that represents our stable diffusion model, and inside the stable diffusion web UI we should go to models folder. Let's go inside this models folder, and we should click on stable diffusion folder, And now what we will do, we should put our Stable Diffusion model rpgv4.savetensors inside this directory, inside this folder, or in other words, we should paste the file that represents our Stable Diffusion model here in this folder. So I did that previously, and I did the same thing for Dream Diffusion Checkpoint, which is another amazing Stable Diffusion model. You can also download it from Hugging Face community. And finally, you can also put your fine-tuned Stable Diffusion model here, a Stable Diffusion model that you trained previously on your custom images. As we said previously, we will use Dream Booth script to train it, and you will save it in your Google Drive. After that, you should download it in your local machine and put it in this folder also. And that's why we saved our fine-tuned Stable Diffusion model with extension checkpoint in our Google Drive to use it in Automatic 1111 software. Now we should specify which Stable Diffusion model that we want to use. Let's select rpgv4.savetensors. Now let's write our prompt here. Let's say that we want to create enemy, boy, half body, blue eyes, black hair. Let's click on generate. Here the number of sampling steps or the number of time steps that we will do during reverse diffusion equal to 20 time steps. And here's our image. It is a very good image. I used this rpgv4.savetensors model to create this image with the 20 time steps. Here I can control the size of the image that I want to create. Here in this case it is equal to 512 width and 512 height. Here we can change the importance of the prompt in the generated image, or in other words, the guidance scale, by changing the value of CFG scale. Now it is 7, and it is good value actually. If you want to reproduce the same image next time, you just need to click on this symbol here and save this seed to create the same image. This seed will create the same image for you. Now try to click on generate and you will get the same image. Here I changed the seed number, and as you can see here, the image, it is different now. The image that our Stable Diffusion model generated, it is different now because this seed represents another image. Let's go back and use this seed here. Okay. Now we have our previous image because we used the seed that will generate this image. We can save this seed and we can generate the same image again and again as we want by using this seed number. And here we used Euler algorithm, and we can also use DDIM algorithm that we used previously to do sampling during reverse diffusion, and it will also give us great images with a few number of time steps. There are actually many schedulers that we can use here. You can specify the number of samples that you want to generate at a time. Let's say that we want to generate 3 samples. So we should make the batch size equal to 3. And you should click on generate. And you can also specify the number of batches. Let's say that we want to increase the number of batches to 3. So we should change batch count argument to 3. By doing this, you will do reverse diffusion 3 times. Each reverse diffusion process will create one batch of samples. So if the batch size equal to 3 and the batch count equal to 3, it means that we will generate 9 images. As you can see here, we have 9 images. Now let's go to extensions. Let's say that we want to use control nets to add any control net that we want to our automatic 1111 software. Actually, we just need to copy the link of the repository. It is this one here. Actually, I installed it previously, but let's learn how to install this repository. We just need to copy this link, github.com microbill sd web UI control net. We should click on install from URL. We should paste it here and we should click on install. As you can see here, I installed it previously. After that, you should click on installed and click on apply and restart UI. When you install it, it will appear in this place here. Okay, SD web UI control net. Now we should specify which control net that we want to add to our automatic 1111 software. We have many control nets like Kenny control net, Scribble control net. If you want to download any control net, you should download it from Hugging Face community. From this repository, you just need to specify which model that you want to download. Let's say that we want to download Kenny control net. So you should download this file. The extension of this file should be pth. So if the extension of this file is pth, so this file is the model itself, the control net. So we just need to click on this symbol here to download it in our local machine. As you can see here, in downloads, we have this file, control version 11psd 15 canny.pth. Now let's add it to our automatic 1111 software. And we should go to extensions folder and we should open SD web UI control net. Okay, and we should enter to models. Now we should paste our Kenny control net model here in this directory. And actually I did that previously. Here is Kenny control net.pth file. It is available here. We don't need to download Kenny control net.yaml. We just need to download Kenny control net.pth. And we can do the same thing with any other control net that we want to download and use in our automatic 1111 software. If you want to download any other control net, you just need to search about what you want. Let's say, for example, in Paint control net, and click on this symbol here to download the file and do the same procedure. I downloaded Scribble control net and OpenPose control net. Now we should click on settings and we should click on reload UI. Let's go back to image, and now you should see ControlNet version 1.1.224. Click on this symbol here. Now if you want to select specific ControlNet, you just need to click on this place here and select the ControlNet that you want to use. For example, Kenny ControlNets. Now let's say that we have this image here and we want to use our Kenny input to change the style of this image based on our prompts, but at the same time we don't want to change the identity of this person. We just need to change the style. We should click here and download our image, and here's our image. We should select Kenny, and here we should select the model, and we should check enable box to activate this ControlNet. Here I will select Kenny ControlNet, and the preprocessor that I will use, it is Kenny function. This Kenny function will convert this image into Kenny input. I should click on this place here, and here's our Kenny input that we will use as condition. We can change Kenny low threshold and Kenny high threshold to improve our Kenny input. I will reduce low threshold, Kenny low threshold, to get more details like this. Now what we will do, we will go here. Here I created this prompt, enemy boy. Let's see enemy style for this image, and here's the result. We can see more results by making batch size equal to 3 and batch count equal to, let's say, 6. Let's click on generate. As you can see here, we generated many different images for this reference image. This one, this one, this one. As you can see here, it is our image with enemy style. It is something similar to this one here. And there are many other control nets that we will learn how to use in the future. Actually, we can use multiple control nets at the same time to generate our image. We will talk about all these things later. Thanks for watching. Hi, in this lecture we will learn how to use Automatic 1111 software, and we will talk about all the parameters inside it. Firstly, let's run Automatic 1111 software. We should click on Web UI user.bat program. Now you should copy this URL and paste it in your browser like this. Okay. In the previous lecture, we learned how to add our Stable Diffusion model to this list. Now, I will use RPG v4.save tensors Stable Diffusion model, so I will click on it. So now, Automatic 1111 software will use this Stable Diffusion model to generate the images. We have many tabs in Automatic 1111 software. We will start with the first one, Text to Image tab. In this tab, Text to Image tab, we will be able to generate the images based on our prompt, our text. How can we do that? We just need to write our prompt here in this place. So now let's say that we want to generate an image for cat. So we just need to type cat here and we will click on generate. Automatic 1111 software will use our GPU automatically to do reverse diffusion, so it will do reverse diffusion quickly. And here's the result. It is an amazing image. So here you will describe what you want to see. Let's say that we want to see red cats like this. And here's the result. It is red cats, as you can see here. Now let's say that we want an image with large width and height. So how can we control the width and height of the generated image from Stable Diffusion? How can we do that? We have this argument here, width argument and height argument. We just need to change them to change the size of the generated image. And it is a good idea to keep one dimension equal to 512, let's say the width dimension, and changing the other dimension, like the height dimension. And let's make it, for example, 768. Or you can increase the width dimension to 768 and keeping the height dimension as it is, which is 512. But what is the reason behind this? To know the answer, firstly, let's talk about Stable Diffusion version 1.5. They fine-tuned this Stable Diffusion model on images with the 512 width and 512 height. So we can say that this Stable Diffusion model will generate images with 512 width and 512 height. For this reason, we should keep at least one dimension equal to 512, and it's up to you to change the other. You should not increase it a lot actually. Just try to increase it gradually and try to use your Stable Diffusion model with each new size to find the best value for the other dimension. And it is the same thing with the Stable Diffusion version 2. This Stable Diffusion model, they fine-tuned it previously on images with 768 width and 768 height, which means this Stable Diffusion model will generate images with 768 width and 768 height. For this reason, we should keep one dimension equal to 768 and changing the other to find the best value for the other dimension. Now let's change the height of the image that we will generate to 768 like this, and we will click on generate. By doing this, we will make the height of the image that we will generate equal to 768. And here's the result. The height of the generated image, it is more than the width of the generated image, as you can see here. Now let's change the width of the generated image. Let's make it equal to 768, and we will make the height of the generated image equal to 512. We just need to click on this symbol here to do that. Now let's click on generate. As you can see here, now the width of the generated image, it is greater than the height of the generated image. And we have another parameter, which is batch size. By increasing this parameter, we will increase the number of images that we will generate each time. Let's say that we want to generate 2 images. Okay, so let's click on generate. As you can see here, we generated 2 images. Here is the first image and the second image. If you want to see just the first image, you just need to click on this place here. Here is the first image, and here is the second image. If you want to save this image, you just need to do right click on this image and click on Save Image As. And after that, you just need to click on Save. This symbol will refresh this list if you put it in your Stable Diffusion model in Automatic 1111 software. So you should update this list to see your new Stable Diffusion model. And we have this place here that we will put our prompt in. What about this place here, negative prompt? Here we should put the things that we don't want to see in the image that we will generate. For example, we don't want to see orange background, so we should type orange background in this place, and we will click on generate to see the result. As you can see here, now the background in the generated image, it is white. Let's say now that we don't want to see white background, so we will add it also to the negative prompt. As you can see here, now the background, it is black. Let's say now that we don't want to see two cats in the same image, so we should type two cats in the negative prompt, and here is the result. It is just one cat in this image. We have also this sampling method. We can select the sampling algorithm that we want. For example, DDIM sampling algorithm. Now let's click on generate and see the result. And it will also give us good images. And we can also control the sampling steps, or the number of the denoising steps, or in other words, the number of reverse diffusion time steps. We can increase it to, let's say, 60. Now we will click on generate to see the final result. And here is the generated image. Actually, the best value for sampling steps, it is 25. Sometimes increasing the number of sampling steps will not give you a good image. We have also this parameter here, CFG scale, which means the classifier-free guidance scale. By increasing it, we will increase the importance of our prompt in the generated image. But when you make it very large value, the colors in the generated image will be saturated. As you can see here, I set the value of CFG scale to 20, and the resulted image, the colors of the resulted image, they are saturated. And by making CFG scale equal to 1, our Stable Diffusion model will not respect our prompt, and our generated image will be completely different from our prompt. As we can see here, this image, it is completely different from our prompt. I don't think it's cat. Actually, the best value for CFG scale parameter is 7. It will give you good image, and it will make your Stable Diffusion model respect your prompt. Now let's talk about this seed parameter. We will use the value of this seed parameter to generate xt capital that we will use during reverse diffusion to generate our image. The default value of seed parameter equal to -1, which means that it will create xt capital randomly. In other words, we will get different image each time. If we want to reproduce the same image again and again and again, so we need to get the seed number for this image. To do that, we just need to click on this symbol here, and as you can see here, this is the seed number for this image. By using this seed number, we will end up with the same image each time. But why we need to do that? Why we need to fix the seed number? To know the answer, firstly, let's say that we have this image. Now let's take the seed number of this image, or in other words, let's fix the seed number. We just need to click on this symbol here. Now we fixed the seed number, which means that we will end up with the same image each time. Now let's say that we want to change this image a little bit. Let's say that we want to change the background of this image and we want to make it black. To do that, we will just change the prompt that we used to generate this image. We will add black background, and by fixing the seed number of our image and changing our prompt a little bit, we will increase the chance that we will get the same content but with different style. In this case, black background. And here is the result. It is a little bit different from our original image. Sometimes you will get completely different image. Now to solve this problem, we will use keyword blending method. But what is keyword blending? Let's say that we have XT capital for a specific image. We fixed the seed of that image, and now we have XT capital that we will use to generate this image. Here what we want to do actually, we want to change the prompt to change a little things in our image. We don't want to change our original image completely. How can we do that? To do that, to keep the content of the image but with the style of our new prompt, we should do the following. Firstly, we should use our original prompt, the prompt that we used previously to create our original image. We will pass it through our U network in the first n number of time steps. For example, in the first 10 time steps during reverse diffusion, we will use our original prompt. And when we reach time step 10, now we are sure that we will get the same content of our original image in the new image, because in the first 10 time steps we specified the contents that we will get in our new image. And these contents, they are actually just the contents inside our original image, because we used the original prompt during these 10 time steps. Now we will add the style. How can we do that? In the rest time steps, we will not use our original prompt, but we will use our new prompt to add new style to the content of our original image. And finally, we will get x0. This generated image will have the content of our original image with the style in our new prompt. Now let's do that practically. Now let's say that we have this image, and here is our original prompt that we used to create this image, which is cat with a black background. Okay, and here is the seed number for this image. We fixed the seed number, so now we have XT capital for this image. Okay, let's click on generate. As you can see here, we will get the same image because we fixed the seed number. Now what we will do, we want to change the background of this image, and at the same time we don't want to affect on the content of the original image. We want to see the content of the original image in the new image. How can we do that? We will open these square brackets. Here we will put black background, and we will put colon, and here we will put what we want actually. Let's say that we want red background, so we will put red background here, and we will put colon again, and let's put here this number 0. For example 1, What is this number? Firstly, let's multiply this number 0.1 by 20. The result will be 2. Okay? It means that in the first two steps in reverse diffusion, we will use this sentence, black background, while in the rest time steps we will use red background. In other words, we will use our original prompt in the first two time steps, while we will use the new prompt in the rest time steps. Now let's click on generate. As you can see here, now the background is red. When we increase this number, this image will get closer and closer to our original image. Okay? So we need to find the best value. As you can see here, the content inside this image, it is very close to the content inside our original image. Let's take another example. As you can see here, here is our original image. Okay? Now what we will do, we will replace this background with another one. Let's replace it with the city background. Okay. Now let's reduce this factor to 0.8, which means that we will change dark background to city background at time step 0.8 times 60, which is time step 48. Okay, let's see the result. As you can see here, it is similar to our previous image, our original image. Let's reduce this factor again to 0.5, for example. It is also similar to our previous image. Let's reduce it again to 0.3. Okay, now we have something new. Now the background, it is different from what it was previously, but with the same content. The content of the original image, it is available in this new image. Let's reduce it again to 0.2, which means that we will replace this dark background with this city background at time step 12, which means that we will use dark background in the first 12 time steps, while in the rest time steps we will use city background. Let's click on generate. Now the background, it is better, but I think that the content changed a little bit, which means that we should decide the best value for this factor here. Okay? Now we created this image here for a cat, and we fixed the seed number of this image. Now we have another thing in text to image tab, which is extra checkbox. Let's click on this box. Okay, now automatic 1111 will give us all these new parameters: variation seed parameter, variation strength parameter, resize seed from width parameter, and the last one, resize seed from height parameter. Let's talk about each one of them. The first one is variation seed parameter. Let's say that you have the seed number of another image and you want to mix that image with this image here. To do that, firstly you should put the seed number of that image in variation seed parameter. We have another parameter which is variation strength parameter. We will use this parameter to specify the degree of interpolation between the seed and the variation seed. By making this variation strength parameter equal to 0, it means that we will just depend on the seed of this image here during reverse diffusion. Or in other words, we will just use xt capital for this image here. And when we make variation strength equal to 1, it means that we will use xt capital for the seed number that we put it in variation seed parameter. Now let's create another image and take the seed number of that image. Firstly, you should copy the seed number of this image. Now we will make seed parameter equal to -1 to generate random seed, or in other words, generate random image, but with the same prompt that we used to generate this image here. So let's put -1 and we will click on generate button. And here we have another image. Let's take the seed number of this image. We will keep this seed number in seed parameter, and we will paste our previous seed number in variation seed parameter. So now we can say that if variation strength equal to 0, at this case we will generate this image. If variation strength equal to 1, so we will generate the previous image. And if you want to mix these two images, you just need to select a value between 0 and 1. Now let's select the value of variation strength. Let's make the value equal to 0.1 and let's click on generate. As you can see here, by increasing the variation strength parameter, we will get closer and closer to our previous image. Let's now increase variation strength parameter to 0.2 and we will click on generate. Now it is closer to our previous image again. Now let's make variation strength equal to 1. And here is the result. It is our previous image, which is the image with this seed number here. Finally, we have these two parameters, resize seed from width parameter and resize seed from height parameter. Let's say that we have an image and we fixed the seed of this image and we changed the width and height to create the same image but with different width and height. Actually, you will not get the same image. You might end up with completely different image, even when you fix the seed of your image. Okay? These two parameters will try to fix the content of the image when resizing the image. Okay? Actually, it is not perfect. For example, let's say that we have this image here, and let's see the seed of this image, and here is the seed of this image, the seed number of this image. Now let's click on extra. We will change, let's say, the height of the image and we will make it 768. Okay? What we want actually here, we want to see this image but with this new size. Now what we will do, here we will put the width and height of this image, which is 512 times 512. Or in other words, the width and height before resizing. Now let's click on generate. And here is the result. I know it is not the exact same image, but it is similar to it. And now the height of this image, it is 768. And the width of this image is 512. Okay, let's now try with another image. Let's generate another image. The width and height of this image is 512 times 512. Let's fix the seed number of this image. Now let's click on extra. Here we should put the previous width and height. Now let's change the height of this image. Let's make it 656. Let's click on generate. And here is the result. It is similar to our previous image. Thanks. Now let's say that we want to create a periodic image. An image with repetitive patterns. How can we do that? Firstly, we should put our prompt. Let's type doc, and we should click on tiling checkbox. Now let's click on generate, and here is the result. It is periodic image. As you can see here, we have many docs in this image. Here is another example. Here I created this prompt apple. It is periodic image. Now we will talk about face restoration, and we will use face restoration model to do that. Firstly, I created this image, and here is the prompt of this image, which is man blur face. Okay, now we will go to settings, and we will go to face restoration. Let's click on face restoration, and here we should specify the model that we will use to do face restoration. Here we have two models, CodeFormer and GFP-GAN. We will use the first one. And we have this parameter, CodeFormer weight parameter. When we make this parameter equal to 0, we will get maximum effect. But when we make this parameter equal to 1, we will get minimum effect. Let's start with 1. And we should click on apply settings. Let's go back to text to image. Let's fix the seed of this image by clicking on this symbol here. Now we should click on this checkbox, restore faces checkbox. Now let's click on generate, and here is the result. The face now it is more clear than what it was previously. Let's go again to settings, and let's reduce CodeFormer weight. Let's make it 0, maximum effect. Let's click on apply settings, and let's go to text to image, and let's click on generate. And here is the result. Here is the face. It is more clear than what it was previously. Now as you can see here in this image, the face it is not that good. We will use CodeFormer model to make this face better. We just need to click on restore faces, and we should click on generate like this, and let's see the result. As you can see here, now the face it is very good compared to what it was previously. Okay, now let's talk about this checkbox, higher fix option. It means higher resolution fix option. We will use this option to increase the resolution of our image, to increase the size of our image. In other words, to upscale our image. As we said previously, we can change the size of the image that we want to generate by changing width and height parameters. But actually it is not a good idea because, as we said previously, Stable Diffusion version 1, they trained it previously on images with 512 times 512 It means that the chance that we will get good image will be higher when we use 512 width and 512 height, because this size, it is similar to the size that we used to train our Stable Diffusion model previously. So now we will not change the width and height parameters. We will use another way. We will use hires fix option. As you can see here, now we have this image with 512 width and 512 height. And we want to increase the resolution of this image. We want to upscale this image. How can we do that? Let's click on hires fix option, and we will get all these things here. From here, we can select the upscaler that we will use to upscale our image. Okay, we will choose the first one. Here, this upscaler will upscale the latent representation, which means that after doing reverse diffusion, we will get finally x0 latent representation. We will upscale it. After that, we will add a noise to this upscaled version of our x0 latent, and we will do higher steps. Now let's talk about this parameter, higher steps parameter. This parameter, it is applicable just with latent upscalers, just these latent upscalers. Okay, so what is this parameter? We will use this parameter to specify the number of higher steps. Actually, here we will do another reverse diffusion. We will take the upscaled version of our x0 latent representation, and we will add a noise to it to move it to specific time step, and we will do reverse diffusion to get another upscaled x0 latent. This x0 latent now, this upscaled x0 latent is much better than the previous one. And during these higher steps, we used another diffusion model. This diffusion model, it is very small compared to our Stable Diffusion model. So when we pass upscaled latent to it, it will not fill our memory. And it's not the case with our Stable Diffusion model. When we pass upscaled latent representation through our Stable Diffusion model, it will fill our memory and it will return an error. And as we said previously, we will add a noise to our upscaled x0 latent before doing the higher steps, and we will specify the amount of noise by using this denoising strength parameter. When we increase this parameter a lot, the image that we will get finally, it will be a lot different from our original image. So you should adjust the value of this parameter carefully. And let's make denoising strength equal to 1. It means that we added very large noise to our upscaled x0 latent, which means that we lost most of the information about upscaled x0 latent. And here we moved our upscaled x0 latent to time step 40, because here higher steps, it is equal to 40. Okay, from this time step 40, we will do reverse diffusion with another diffusion model to reach better upscaled x0 latent, and we will pass this upscaled x0 latent through our decoder to get our image, our upscaled image. Now let's reduce this denoising strength to 0.5. 5, it means that we will move our upscaled x0 latent to time step 20. 0.5 times 40 is equal to 20. We will move it to time step 20. It means we will not delete most of the information about our upscaled x0 latent here, which will increase the chance that we will get the same contents of our original image in the final upscaled image. And when we make the higher steps equal to 25 and denoising strength equal to 0.5, it means that we will move our upscaled x0 latent to time step 12. And we will do reverse diffusion from time step 12. Now to specify the new size, you need just to specify upscale by parameter. Here we set this parameter to 2. It means that the width of the final image will be 2 times 512 and the height of the final image will be 2 times 512. In other words, the new size will be 1024 times 1024. If you want to specify the width and height as you want, you just need to change resize width to and resize height to parameters. And here I made resize width to equal to 768 and resize height to equal to 768. And here is the result. Our previous image, the width and height of our previous image were 512 times 512, and here is our new image, which is this one here. It is good image, and the resolution of this image, it is higher than our previous one. Let's see our previous image. Here is our previous image, and here is our new image. If the content inside our new image, it is a little bit different from what it was previously in our low resolution image, you just need to decrease denoising strength. Let's make it 0.3 and let's click on generate. Now this image is closer to our previous image, and here I think that we should decrease denoising strength a little bit just to make our diffusion model do its magic to create amazing image. Now it is better than what it was previously. If we want to make the face better, we just need to click on restore faces like this, and let's click on generate. And now the face, it is better, as we can see here. Let's use upscale by parameter. Let's make it equal to 2. Let's click on generate, and here is our image. Let's increase the higher steps. Let's make it 50. And now what we will do, actually, we will move our x0 latent with a new size to time step 50 times 0.5, which means 25. So we will do 25 higher steps. It will take long time to create this image because we will do 25 higher steps, and we will use larger latent representation during reverse diffusion or during these higher steps, so we will take long time. Here's the result. It is good image here. Now we have this image here. Let's say that we removed the prompt of this image and we changed the original height and width. Now we want to return all the information that we used to create this image, like the prompt, the width and height, etc. So we just need to click on this symbol here. As you can see here, here is the prompt that we used to generate this image, and the width and height and CFG scale and the seed number of this image, and we returned the values of all the other parameters that we used to create this image. Now let's say that we want to save this prompt, this style. How can we do that? We just need to click here, and we just need to put the name of this style. Let's say man and city, like this. And now we have new style here in this list, which is man and city. When we click on it, we will add this style to our prompt. Let's say that we have a new prompt, ocean, for example, and we want to add our previous prompt or our previous style to this new prompt. We just need to click here, and we just need to click on the style that we want to add here, which is man and city. Let's click on it like this. By doing this, automatically 1111 will add this style or this prompt with our new prompt directly, and when we click on generate, we will get this image. As you can see here, we have this city and this ocean and this person here. Okay, if you want to delete your prompt and your negative prompt, you just need to click on this symbol here and click OK. So you will delete this prompt. Let's go back and talk about the upscaler. As we said previously, there are many upscalers, but here we used latent upscaler. It is good upscaler actually, because it will not create any artifacts in the resulted image. But the problem with this upscaler is you will change the content of your original image in the resulted image when you increase denoising strength parameter. So there are another upscalers that it will not affect on the content. We will talk about them later. Let's click on this symbol here. We have many things, we have many tabs inside this button. The first one is textual inversion. The second one is hyper networks, checkpoints, and the last one, LoRa. Now let's talk about LoRa. What is LoRa? It means low rank adaptation. It is just a technique of training or fine-tuning our stable diffusion model. By using LoRa technique, we will not train all the parameters of our stable diffusion model, but we will just train these cross-attention layers. Okay? It will update the parameters of this layer, this layer, this layer, this layer, because they found that fine-tuning just the cross-attention layers, it will give you good results. As we said previously, these cross-attention layers will inject the text inside our U network. We will update the weights of these layers. So now, by doing this, we will reduce the memory consumption during the training. And actually, LoRa will do another thing also. It will modify these cross-attention layers in some way to reduce their size, and it will save these parameters, these cross-attention blocks, in a file, and we will call this file LoRa model. The size of this file will be very, very small compared to our Stable Diffusion model, because here in this file we will just have the parameters of our cross-attention blocks after training, after fine-tuning, and we will store these blocks in efficient way, and we will learn how to do that. And because that we will just store the parameters of the cross-attention blocks in this LoRa model, so we need our original model, our Stable Diffusion model, to use this LoRa model to put the parameters of this LoRa model in our original Stable Diffusion model to use this LoRa model. So in other words, now we are using our original Stable Diffusion model, but with the cross-attention blocks of our LoRa model. The most important thing here is that we can download many LoRa models on our local machine, and they will not take large space from your hard disk. And the other advantage is that you can download them quickly from internet, because the size of each one of these LoRa models is small. We said previously that we can store the parameters of these cross-attention blocks in efficient way. But what is that way? Firstly, you should know that each one of these cross-attention layers, the weights of each one of these cross-attention layers are arranged in matrices. Actually, LoRa will do the following. Let's say that we have this tensor here, this matrix. This matrix has 1000 rows and 2000 columns. Okay? LoRa will decompose this tensor into two tensors, this one and this one. The first tensor here will have 2 columns and 1000 rows, while the second tensor will have 2000 columns and 2 rows. Let's see the number of elements for each one of these tensors. The first one, the number of elements in the first tensor, this one here, will be equal to 1000 elements, or in other words, 2000 parameters. The second one, the number of parameters, or the number of weights, or the number of elements inside this tensor will be 4000 parameters, while the number of parameters in the original matrix will be 2000 times 1000, which will be 2 million parameters. And now let's add 2000 to 4000. The result will be 6000. Okay, the number of parameters of our original matrix, it is 2 million. And the number of parameters, the total number of parameters after using LoRa, it will be 6000. So here we reduce the size. We will do this thing for each tensor in our cross-attention layers. So by doing this, we will reduce the size of these cross-attention blocks a lot, and we will put them in the file that represents our LoRa model. Now let's download one of these LoRa models in our local machine, and after that we will add it to our Automatic 1111 software. As you can see here, I have this LoRa model, Ghibli style offset.safe tensors LoRa model. I downloaded this model previously from the internet. Now what I will do, I will copy this LoRa model. As you can see here, the size of this LoRa model, it is 147 megabyte. It is very small compared to our previous Stable Diffusion model. Now we will go to our Stable Diffusion web UI, and we will go to models folder. We will go to LoRa folder, and here we will paste our LoRa model in this place. Now what we will do, we will go to settings, reload UI, and we will click on this symbol here, and here is our model, Ghibli style offset. Now we want to use this model, we want to use this LoRa model. How can we do that? Firstly, we will use dreamlike diffusion, stable diffusion model, and we will use this LoRa model to adjust the output from this dreamlike diffusion model. Now if we want to use this LoRa model, we just need to click on it like this. Now we will see this text here, LoRa Ghibli style offset, and here we have this number here, 1. So what is the meaning of this? This one, it is just the weight that we will apply on LoRa model. When we make it equal to 0, it means that we will disable this LoRa model and we will just use this dreamlike diffusion model alone. But if you want to mix between them, just put a value between 0 and 1. And now we should write the trigger words. They used these words during the training. This LoRa model. For this LoRa model, Ghibli style offset model, the trigger words are Ghibli style, like this. And now we can write what we want. And here's the result, as you can see here. Without the trigger words, you will not get good results, okay? As I said previously, these trigger words, they use them during training this LoRa model, okay? Just put them here, Ghibli style, and write your prompt here. Let's write old man. As you can see here, here is another image, old man with Ghibli style. Now I can reduce the weight of this LoRa model. Let's make it 0.5 to mix between our dreamlike diffusion model and our LoRa model. As you can see here, now we are mixing between dreamlike diffusion model and LoRa model. Let's reduce it more and make it 0.2. Here is another image. Let's make it 0.1. And here's another image. When we make it equal to 0, so we will not use this Ghibli LoRa model. Now you might ask yourself why we got this image with the anime style. It is not exactly Ghibli style, but it is anime style. That's because that we put it Ghibli style in our prompt previously, and I think that dreamlike diffusion model understood this prompt. It means that they trained it on Ghibli style images, but actually it's not that good compared to our LoRa model. Here I used RPGv4 stable diffusion model, and let's increase our LoRa model. Let's make it 0.5. Now it will get closer and closer to Ghibli style. 0.7. Yes. 0.8. That's also a good image. when we decrease the weight of this LoRa model, we will increase the weight of our RPG v4 Stable Diffusion model. Now let's talk about the last thing in this text to image app. As you can see here, we have many buttons here. The first button here, it will give us all the images that we generated previously. Let's click on it. Let's open this folder. As you can see here, we created these images in this lecture. Let's talk about the second button. We will use it to save this image. Let's click on it, and we will see this thing here. You should click on download, and now you save this image, as we can see here. Now we can also send this image to image tab, okay, or we can send it to InPaint, or we can send it to extras. Hi, in this lecture we will learn how to download LoRa Dream Booth to train our Stable Diffusion model on our local machine. To do that, firstly we should open Automatic 1111 software. We just need to click on web UI user.bat program. Now let's copy this URL, and here is our Automatic 1111 software. Firstly, we need to add Dream Booth extension. Okay, we just need to go to extensions, and we should go to available and click on load from. Now you should type Dream Booth like this, and you will see Dream Booth extension, and you should click on install to download this extension in your Automatic 1111 software. After that, you should go to installed, and you should click on check for updates, and finally you should click on apply and restart UI. Okay, and you will see this tab, Dream Booth tab. Now the first thing that we should do, actually, we should click on create tab here, and we should create our model that we will train. Firstly, let's put the name of our Stable Diffusion model that we want to create. Let's type, for example, my model. Okay, and now here you should specify the source checkpoint, because as you know, we will not train our Stable Diffusion model from scratch, but we will start with a pre-trained diffusion model and fine-tune it on our own images. Let's select Dream like Diffusion version 1 checkpoint. Okay, and now what we will do, we should click on create. Now we created our model. Okay, let's go to select, and we should click on LoRa checkbox here. I will train my Stable Diffusion model on these 6 images. Firstly, I will copy the directory of these images, and I will keep the training steps per image as it is, equal to 100. Here we will use mixed precision, so we will make mixed precision parameter equal to floating point 16, and we will make memory attention equal to X formers. Now let's go to concepts tab. Firstly, we should put the directory of our images that we want to use to train our Stable Diffusion model. And here we will specify the prompt that we will use during training and inference. Let's make it equal to ZWX. And here we will put the class prompt. We will put general information about our images in this class prompt. For example, person, man, adult. Here during training, we will use this class prompt to generate another images that we will add to our own images to enhance the training, to make the training better. And here we will also add the negative prompt. We will put the things that we don't want to see in the generated images. For example, ugly, bad anatomy, body out of a frame, etc. And here we will make a class images per instance image parameter equal to 10, which means for each image in my dataset, I will create 10 different images using the class prompt and my Stable Diffusion model. And now I will click on a training wizard person to save all this information. Now we will click on a train to start fine-tuning. Here I'm using a GPU with 6 GB memory. Now we will create a checkpoint file by clicking on generate checkpoint. Now let's go to text to image, and we should select our model, which is my model 1200 LoRa.safe tensors. Here I put the prompt that I used for my images, which is ZWX person man, and I used the same negative prompt that I used during training. Let's see the result. And as you can see here, this image, it is similar to my images that I used to train my Stable Diffusion model. And here I changed the prompt. I put it watercolor painting ZWX as a wizard. And here's the result. It is an amazing image. Finally, if you face any problem like there is no X-formers, you just need to do right click on web UI.bat program, and you should click on show more options, and here you should click on edit, and here you should make command line args equal to --X-formers space --mid VRAM and save it. And that's it. Thanks for watching.
An array is a container object that holds a fixed number of values of a single type. An array is used to store a collection of data, but it's often more useful to think of an array as a collection of variables of the same type. Instead of declaring individual variables, such as for this example, if I'm going to say integer numbers 0, numbers 1, numbers 2, numbers 3, up until numbers 9, and I'm assigning values, instead of doing that, I can declare one array like I'm doing there, and then I can use numbers at a specific index value, in this case numbers 0, numbers 1, numbers 2, numbers 3, numbers 4, and assigning values to those index values to represent individual variables. And the length of an array is established when the array is created. After creation, the length is fixed. So if we quickly have a look at this picture then, if I declare an array, you can see that the declaration basically is just int, or you can have different types. Obviously, you can have any primitive data type. So you'll start off with the type, and then two brackets there, and then the name of your array, and then you must say new int, because to create a new object in Java, we use the new keyword, but we'll get that in the next set of videos. So the new keyword creates a new object in memory, and this object will basically be an array of integer values that can accept 10 or store 10 values. So it's basically the same as what we're doing here. We're declaring there 10 variables and setting those values to 10 specific variables. So instead of doing that, we declare one array, and an array looks like this when declared in memory. So I'm essentially declaring 10 spaces in memory where I can save integer values, and you can see that they are indexed. So to get to the very first value in the array, we'll start at position number 0, 1, 2, 3 up until 9. So if the length of the array is 10 like we've declared there, then it can hold 10 integer values, but it will be indexed from position 0, 1, 2, 3 up until position 9. And you can see that's how we will then assign values. We will say numbers 0 equals 5, numbers 1 equals 10, and so it carries on until you get to numbers 9. Unfortunately, if your array is declared as a size 10 there, you cannot try to access the 11th value, which will be numbers 10. So now that we have a slight idea of what an array is, let's just close that picture. Let's see how we can declare it. So I'm going to delete all of these and just stop with the declaration of the array. Okay, so there's the declaration of our array. Another way to declare the exact same array would be to say int. I'm just going to call it something else. So let's say numbers. Instead of having the brackets there, we can say numbers 2 and then have the 2 brackets at the end equals new int and have it the 10 values. So declaring these two in this specific way, we are essentially creating two of the same arrays that can hold 10 integer values. But if you declare more than one array at a time, so if I'm going to say int numbers 3, comma numbers 4, comma numbers 5. In this case, numbers 3, numbers 4, and numbers 5 is declared as arrays. They're not initialized like we did in those two. And the other way of then declaring them would be to say, let's say this one should be numbers 6 with the block brackets at the end, and then numbers 7, numbers 8. So now the difference here is, you can see there I've placed the brackets at the front, and then we've got numbers 3, numbers 4, and numbers 5. If I do it this way, it means that only this one called numbers 6 will be an array. These two will be normal ints. So if I want to have these two also as arrays, then I would have to add the block brackets to both of them. So if you want to declare 3 arrays of the same type, then I can easily do it by just basically doing that first one, to have the block brackets at the beginning and then declaring them. All 3 of them will be integer arrays. But if I declare it with the block brackets at the end, then every array that you declare must have the block brackets at the end. So just some information that could be useful for you in the future. Right, so let's delete all of these and stick with that first one again. Integer numbers equals new int 10. So how do we assign values to the array? We've seen that now in the previous example, but you can basically go to your numbers array and switch to the specific index where you want to go and save a value. So in this case, in index number 0, I'm going to save a value of 10. In index, let's go to just another one there, index number 2, I will assign a value of 15. And let's say numbers at position 3 equals, let's make it a 20 there. So this is how I'll assign values to the specific elements inside of an array. Let's start with 0, 1, and 2 there. So let's just create, instead of saying 10 there, let's use 4 values there just to keep this simple. So I'm going to say numbers, let's do the last one there, 3 equals 25. So you can see then that we've assigned values to every single index value for that array. Now another way of doing this a bit short, if you know the values right from the start, I could say numbers, let's say 2 now, equals new int, and let's use that same values. So I'm going to say 4 again. So this is the declaration to say that I want to have 4 values stored in it. But instead of doing this, we could use the curly brackets and give the values right from the start. So I could say I want 10 there, then 15, then 20, and then 25. So this is essentially doing the exact same thing as what we did there. We're basically saying go and create a new array of size 1, 2, 3, 4, exactly like we had there, and into position 0, 1, 2, and 3, go and place those values. So these 5 lines of coding is doing essentially the same as this 1 line of coding. Okay, so there we have initialized it, we've declared the array, we've set the size to 4, and we set the values already in the array. So let's just quickly print out one of these values. So I'm going to say system.out.println, and let's print out numbers, which is the top array there, and let's go to, let's say what is in numbers 0. If you run this quickly, just to print out to see what is in numbers 0, and you can see there that it's the 10. So number 0, we placed a 10. If I change that to a 1 and run it quickly again, you can see the value prints out as 15, and that's what's saved into 15, or into position 1. So I can also change this to numbers 2 and go to position 1, and numbers 2 is this one, and position 1 is 0, 1 should be the 15. So now let's run this quickly again to see how it prints out, but that should be the 15 there, so you can see it prints out 15. Okay, so now an easier way to print out all the specific values of an array is to use a for loop. So with a for loop, I'll start at an index, and that's why normally we use an I when we're working with arrays, but it's up to you, it's just a variable name, but I stands basically for index there. So I will normally start my I variable there at a 0 because of our arrays starting at position 0 as the index value. And then we're going to test for the length of the array. So I'm going to say I less than, and the array, let's take the first one, numbers there. I'll use numbers, and there's a useful variable we can use there as part of the array class there, and that's called the length. And I'm going to use the length in there in order to indicate or to see how long that specific array is, or how many values can it store. In this case, you can see it's 4. So numbers.length will return a 4. If I say numbers2.length, it will return also 1, 2, 3, 4. It will return a 4. So we're essentially saying go from the index value 0 up until the index value of numbers.length, but less than numbers.length. So if I use a comment here, you're going to start at 0, and it should be less than numbers.length, in this case is 4. So what will happen is we're going to start at position 0, then it increments. Is 0 less than 4? Yes, it increments. Is 1 less than 4? It goes to 1 there. Yes, it is. So then we're going to go increment 2 less than 4. Yes, it is. And then the third one, is 3 still less than 4? Yes, it is. But as soon as we increment again, then 4 is not less than 4. So you can see that we're not going to go to numbers 4 there at all. Okay, so this is very important. You will go 1 less than the length of that specific array. So if it can hold 4 values, I will go to index number 3 as the last value. You see it's also 1 less, or always 1 less than the size of your specific array. So in this case, we're going to say numbers.length, which is 4. So we're going to go from 0 to 3 basically. And then we can print it out. So we're going to say system.out.println, and then we can print out that specific array. So we're going to say numbers at a specific index, and the index will be I in this case. And we know that I will start from 0, then go to 1, then go to 2, then go to 3, and then it will stop. So if we run this quickly, you'll see it prints out now all the values for me in a new line. So we've got 10, 15, 20, and 25. And even for this one, if we add another value of 30 there, and I say let's go to numbers2.length, and I print out numbers 2, then it should print out 10, 15, 20, 25, and 30. And there you can see it. So now the length of this array changed now to 1, 2, 3, 4, 5. Remember, after you declared it, you cannot change it again. It will stay these values, or it will stay only 4 values that you can assign. Obviously, I can go and change it there afterwards, but after I had this one line in my coding, afterwards I cannot change the size. It will stay that specific size. Now let's just quickly have a look at the enhanced for loop. So there's a better for loop to do this. And this for loop, let me just add a system out print line here so that you can see a little space between the two. Okay, so we're going to have another for loop here, and the enhanced for loop will basically be something where we declare a value or variable there that's called value, or whatever you want to call it, and then we pass in numbers, or well, you can use either numbers, this array, if you want to print that one out, or this one. So let's print out the top one, which will just have 10, 15, 20, and 25. So this is the enhanced for loop then, and I'm going to have a system out print line there. But instead now of printing out numbers I, there's no I in this for loop. So what we print out is that variable called val. So basically what happens in this for loop, it will take, you can see there's the name of the array, and there's a variable. So this variable val will, when the first time the loop runs, it's going to get numbers 0 into val, and then we print it out. Second time the loop runs, numbers 1 will be saved into value, and then we print out the value. Then the next time it runs, numbers 2 will be saved. Then numbers 3 will be saved and print out to the screen. Okay, so if we run this quickly, you can see there's the space between the two, but you can see that the bottom one is 10, 15, 20, and 25, which is this one that we printed out, numbers. We can also say, let's print out numbers 2 there, run it again, and you can see the two for loops will now do exactly the same thing. 10, 15, 20, 25, and 30.
Hi, now we will talk about image to image tab. Here in this image to image tab, we have many things like image to image, sketch, in paint to sketch, in paint upload, and batch. Let's start with image to image. Here we should put our reference image, the image that we want to change its style. Okay, we just need to click here and we put it this image here. Now it is our reference image. Now we should adjust the width and height of this image. Okay, why we need to do that? We need to do that to make it suitable for our Stable Diffusion model. Here we should adjust the size. Let's change the width and see. As you can see here, 512 times 512, it is good size for this image. It will not affect on the aspect ratio of this image. In other words, we will not squeeze and stretch this image, and we will not affect on the information inside this image. Now let's specify our sampling algorithm. We will use DPM plus 2M keras. Okay, let's make the batch size equal to 4, which means that we will generate 4 images each time. Now let's add our new prompt, which is a photorealistic illusion of a dragon. We want to put the style of this prompt on this reference image. Okay, let's firstly make the denoising strength equal to, for example, 0.1, which means that we will add a noise to this image and we will move it to time step 2, and from time step 2 we will do reverse diffusion. By doing this, we will make sure that we will get something similar to our reference image. Let's click on generate, and here is the result. As you can see, the first image, the second image, third image. Here, all these images, they are very close to our original image. So let's increase the denoising strength here. Let's make it 0.3. By doing this, we will move this image x0 to time step 0.3 times 20, which is equal to time step 6, and we will start reverse diffusion from time step 6 to time step 0. In other words, here we increased the noise that we added to this image. Let's click on generate and see the result. And here's the result. Let's increase denoising strength again. Let's make it 0.5. Wow, it is very different from what it was previously. This one also, this one, and this one. I think this image it is good actually. Here is good image also we have here. It is amazing image. Now let's say that we want to get an image with different size. For example, let's make the size of the image that we want to generate. For example, 512 times 768. Okay, let's see the aspect ratio after doing resizing. As you can see here, by just resizing this image, we will stretch and squeeze this image, which will affect on the information inside this image. This thing will affect on the contents inside this image. Because here, the new aspect ratio, it is different from the original aspect ratio of this image. But why we need to change the size of this image? When we want to generate an image with different size, we should change also the size of the reference image, because as you know, we will pass this reference image also through our Stable Diffusion model as input to generate our final image. Now we have two things that we can do. We can just resize this reference image, which is not a good choice as we said previously, and we can do crop and resize. By doing this, we will cut our reference image to make the aspect ratio of our original image similar to the new aspect ratio. Actually, the aspect ratio, it is just the width of the image divided by the height of the image. So what it will do, actually, our crop and resize function, it will just change the width and height of our reference image to make the width divided by the height of our reference image equal to the width divided by the height of our image that you want to generate. So it will do the following. It will delete this region and this region to make the aspect ratio of this reference image similar to the aspect ratio of the image that we want to generate. After that, it will do resizing for this area here. And now, because that the aspect ratio of our reference image similar to the aspect ratio of the image that we will generate, so we don't need to squeeze and stretch our image, our reference image, during resizing. In other words, we will not affect on the contents inside our reference image. We have also resize and fill, and finally we have just resize, latent upscale. We will not use these two methods here. And the second method, I know it is good to preserve the aspect ratio of our reference image, but it will delete some information from our reference image, as we said previously. Let's try to use crop and resize. We want to generate, let's say, this size 512 times 768. Let's click on generate. Let's reduce the batch size to avoid this error, out of memory error. Let's increase batch count to 34. In other words, we will do reverse diffusion 34 times. As you can see here, in all these images, we don't see this region here or this region here. We just see this region. Okay? Actually, this image, it is good here. We have also CFG scale, which is a classifier free guidance scale, and it's a good idea to make it 7. We have denoising strength parameter. This parameter will control how much this reference image will change. Okay, when you make it very large value, at this case you will change this image a lot. When you make it 1, you will get completely different image. It's like the xt capital that you will use, it is just pure noise from the Gaussian distribution without any information about our reference image. Let's say that we have this image here, and here is the prompt that we used to create this image. Now what we will do, we will send this image to our image to image tab. Okay, what we will do actually here, we want to extend this image using outpainting. Actually here we can use our Stable Diffusion model to extend this image. The width and height of this image is 512. We want to extend this image by putting many things around it. Okay, firstly we should select the model that we will use for outpainting. We will use the same model that we used to generate this image here. Okay, it is a good idea to use the same model. Now what we will do, we will select crop and resize to preserve the aspect ratio, and here we will make seed number equal to -1 to get different results each time. Okay, now let's enable outpainting. We should click on this list here, script list, and we will click on poor man's outpainting. It is better than outpainting MK2. Okay, and we will get many things here. We will get this parameter, pixels to expand parameter. This parameter will specify the new width and height of our image. This parameter will specify the thickness of the region that we will add around our original image. Okay, our previous width and height of this image equal to 512. We will add 128 for this 512 and this 512. Now what we will do, we will make masked content parameter equal to fill. It means that before adding noise and do reverse diffusion, we will fill these new pixels that we added around this image. We will fill them with the average color of our original image, and this thing will help our Stable Diffusion model during reverse diffusion to make the information that our Stable Diffusion model will add to this region around our original image, matching the information of our original image. It's like the repaint algorithm that we talked about previously. And it's a good idea to outpaint one direction at a time. Let's firstly outpaint the right direction. We will do reverse diffusion to fill the new pixels that we added to our original image with the new information that it will complete the contents inside our original image. And here's the result. As we can see here, we added this new region to our original image, and the information inside this region matching the information of our original image. Now let's take this one and put it here, and what we will do now we will work on the left side of our image, and we will get something like this. We can let's say click on generate again to get something better, and it is good also, as you can see here. Let's increase this thing. Yes, it is good image. Now we will work on the upside Let's click on generate also. Yes, that's good. We can generate another image. Let's click on generate to get something better. Now the weather is cloudy, as you can see here. Now let's click on down, and here's the results. If it is not good, you just need to click generate again. We can increase denoising strength. Here the result, it is good actually. Here I made denoising strength equal to 0.96. Okay, now it is good image. Let's send it to our image to image. Okay, now we will fix some details inside our new image also using in painting. So let's click on in paint. Firstly, we should mask the region that we don't want. Let's say that we don't want this region, so we will use this brush to create the mask. Okay, and we will regenerate it again. We will regenerate just the masked area to get something better. Let's see the settings here. We have also many things in this in paint. We know the resize mode. We will use crop and resize. As you can see here, the new size of our image is 640 times 640. Now what we will do, as you can see here, we have many parameters. Let's talk about this parameter, mask mode. We will make it equal to in paint masked. It means that we will regenerate just the masked area. Now if you want to regenerate everything except the masked area, you just need to click on in paint, not masked. And we have also mask blur parameter. This parameter will define a region around the in-painted area. Inside this region, we will blend the in-painted results and the original information. And we will do that just to force our regenerated area or our in-painted area to become more and more similar to our original image. You should try many different values for this parameter to find the best one. Now we have other parameter, which is mask content. Here we will select original. It means that we will not remove the original information under the mask, but we will just add a noise to this region, and after that we will use our Stable Diffusion model to do a reverse diffusion and to create something new. Actually, by using this option, you will keep the general shape of the region under the mask, and you will just adjust and enhance the details of this region. We have another option, which is fill option. At this case, we will fill the pixels under the mask with the average color of our original image. After that, we will add a noise to these pixels, and we will do reverse diffusion using our Stable Diffusion model to generate something new. And we have also latent nothing. It will completely replace the area under the mask with tannish color, regardless of the image contents. After that, we will add a noise to this region, and we will use our Stable Diffusion model to regenerate this region by doing reverse diffusion. If you want to use latent noise or latent nothing, you should make the noise strength greater than or equal to 0.6. Sometimes if you want to get specific thing, you can edit your image before doing in painting. After editing, you will mask the region and select the original option to create something good using your Stable Diffusion model. It's like that you will guide your Stable Diffusion model during regenerating process. As you can see here, I have this image. I generated this image with this prompt. Okay. Now I will edit this image. I changed this image a little bit. I added lightning here on this stick. Okay. Now what we will do actually, we will send this image to image tab, and you just need to remove this one and click here and choose your image after editing. As you can see here, here is our image. You just need to mask this region. Okay, firstly we should send this image to InPaint tab, and you just need to mask this region here. And what we will do actually here, we should select original, because here we want the same shape but we want to change the details. And here we will make the noise strength equal to something small like 0.4. When we use original option, we should make the noise strength something between 0.2 and 0.4. Okay, and here's the result. As you can see here, it is very good result. Our Stable Diffusion model created very good magical effect. Now let's talk about another parameter in InPaint tab. This parameter is InPaint area. When we make InPaint area only masked, it means that we will just take a crop of our image. This crop will have our masked region. And when we make InPaint area equal to whole picture, it means that we will resize our picture into new size, which is this 640 times 640, and we will use this picture. We will add a noise to this picture, and we will do reverse diffusion using our Stable Diffusion model on this picture. It's like repaint algorithm that we talked about previously. And here you should take care of the new size to avoid the problem of aspect ratio. When you select only mask option and making the noise strength very large, sometimes it will create some problems in the generated image. So you might need to increase the mask blur to make the results better. The last parameter that we will talk about in this InPaint tab is only masked padding pixels. By increasing the masked padding, you will decrease the resolution of the regenerated area or the InPainted area. Let's say that you made this masked padding equal to 0. It means the regenerated area will have high resolution and many stuff inside it. So if you want to decrease these things, you should reduce the resolution of this regenerated area. So we should increase mask padding parameter. And if you want to generate a specific thing in the masked region, you should change your prompt a little bit to specify what you want to generate in your masked region. Yes. Let's click on generate again. Now this image it is good actually. That's really good. Now let's talk about sketch. Here what we will do actually, we will create a sketch and we will use our Stable Diffusion model to generate an image based on that sketch. Here we have white background with the 512 width and 512 height. We should put it here in this place. Okay, just drag and drop this white background. Now we can create our sketch. You will find this background in lecture resources. Let's create a home like this. And here's the door. Okay. That's it. Actually, here you can select many colors. You just need to click on this symbol here and click here and select the color that you want. Let's select this one for the sky. Now we have our sketch. Let's generate an image based on this sketch. Let's click on generate. And here's the result. We should actually remove this prompt and let's type house with blue sky. And let's click on generate. Yes, that's good. It is good. House. Let's make this green. Okay, to understand this region. And here's the result, which is also good. And here I added grass to my prompt and I increased the noise strength. I increased denoising strength a little bit. And here's the result. It is good image. It is very good image actually for this sketch. And if you want to modify something in your image, you can also put your image here in a sketch. So let's click here. Now let's say that we have this image here, and here's the prompt of this image. It is our previous image. Now we want to convert the color of this beard to black. How can we do that? Just need to click here. We want a black beard like this. We will also reduce the denoising strength to avoid changing this image a lot. And here's the result. And here is another good image. We have this black beard, and the best image is this image here. Let's now save it. Let's click on download here. Now just drag and drop this image here, and here I put this hat on the head of this person, and here's the result, as you can see here. By increasing the denoising strength, the content of the image will change a lot. So you just need to find the best value of denoising strength parameter. Here is another image with the denoising strength 0.8, 0.81. Okay. Now we will talk about in-paint sketch. Here we will combine in-painting and sketch. We will be able to in-paint here, and here we will just change the painted area and we will not change the in-painted area. As you can see here, I painted this region here, and here's the result, as you can see here. Now let's say that we have this image here. Let's save this image. Now we will click on download. Let's go to image. Now let's click on inpaint sketch. Now let's put this image here. Okay, now we have this image. What we'll do actually, here I draw this sunglasses, and here's the result. Is good. Here is another result here. Now let's change this shirt to let's say green. Let's do it. Let's click here and let's change it to green, like this. And here also. Let's click on generate. Yes, that's good also. This one is much better. I just changed the denoising strength to 0.66. Okay. Now let's change this tie to, let's say, pink. So click on generate. That's good. Now it is pink. This one, it is also good. Let's draw hat here. Now let's click on generate. Yes, that's good. Let's increase denoising strength to add some kind of creativity here. Yes, this image, it is good. Okay. Now we will learn how to get a prompt from our image. Now we have this image and we want to extract the prompt that represents this image. For example, let's say that we don't have the prompt that we used to create this image and we want something similar. We just need to click on interrogate clip like this, and our automatic 1111 software will try to generate a prompt based on this image. And here's the result. Okay, a man with a beard and a suit and tie is looking at the camera with a serious look on his face. Okay, this prompt will give us something similar. We can say it is similar to this image. Let's click on generate and see the result. And here is the result. We can say it is similar in some way to our image, our original image. Okay, it will not give us the exact same image. And we have also interrogate deep book. And we have also interrogate debrew. It is good if you are working with enemy image. It will give you good prompts. Now let's learn how to do upscaling. We need to go to extras. Okay, we will send our image to extras. Let's go to this tab. Let's put our image in this tab. Now we should set the value of scale by parameter. Let's make it, for example, 2. The original size of this image is 512 times 512. Now we will multiply the size of this image by 2. Now let's select the upscaler. We will use this upscaler. RESR GAN 4x plus. It is good upscaler actually. Here we will not do higher steps. We will use special model to increase the size of our image or to upscale our image. Now let's click on generate to see the result. Now let's see the final result. As you can see here, we upscaled our original image. Let's see our original image. Here is our original image, and here is our upscaled image. The resolution of this image, it is much higher than our original image, and it is good actually. And you can also, rather than using scale by parameter, you can use scale to parameter, and you can specify the width and height that you want, and it's up to you to choose between these two things. Let's see the other upscalers. This one here, lens source and nearest, they are old upscalers. They are not that good actually. While the other upscalers, you should try them to find which one of them is the best for your image. Now, what is upscaler 2? Let's say that you want to combine the effect of two upscalers at the same time. So, in this case, you will use two upscalers. The first upscaler, it is RESR GAN 4x plus, and here you should specify the second upscaler that you will use. So the final image will be based on these two models, these two upscalers. And to control the amount of blending, we can set the value of upscaler to visibility. When the value of this parameter equal to 0, it means that we will use just the first upscaler. When the value of this parameter equal to 1, we will use just upscaler 2 to upscale our image. So we will choose something in between to combine these two upscalers. Here we have another parameter, which is GFP GAN visibility and code former visibility. Actually, we can do base restoration during upscaling. How can we do that? We can just increase the value of this parameter GFP GAN visibility. Let's make it something like this, 0.1. By doing this, we will use GFP model to do face restoration during upscaling to get high quality face. And we can also use code former visibility to do that also. Let's use code former model. Firstly, you should make it 1, okay, and code former weight equal to 0, and we should click on generate to see the results. And if the result is very different from our original image, we should increase the weight of our code former model. And after that, just click on generate. By doing this, you will make sure that you will get good face after upscaling. We have also here PNG info. Let's put our image here, and we want to know the information about this image. Here is the prompt of this image, and the number of time steps that we used to create this image, the sampling algorithm, the classifier free guidance scale, the seed of this image, the size of this image, and many other things. It will give you complete information about this image. And we have this tab, checkpoint manager tab. We can use this tab to combine two or more models to create a new model. Here we should specify the primary model, model A, let's say dreamlike diffusion model, and secondary model, model B. Let's select rpgv4.safe_tensors model, and you can also add third model. Let's work with just two models here. But why we need to combine two or three models? We need to do that just to mix the styles of these two models. But sometimes when you mix two models, you will not get good results. And here we have this parameter, interpolation method. We will use it to specify the way that we will do to merge these two models. Here we will use weighted sum. So here the results will be equal to A, it means model A, times 1 minus M, plus B, which is the model B, times M. M, it is the weight of model B. When we increase the weight of model B, we will decrease the weight of model A. When we decrease the weight of model B, we will increase the weight of model A. We have also this bake-in VAE parameter. We will use it to change the variational autoencoder that we will use. And we can click on merge like this to get this new model. And as you can see here is our new model, 0.7 dreamlike diffusion plus 0.3. 0.7 here, it means the weight of this model, plus 0.3 is the weight of rpgv4 model. Okay, and we can use this new model. Actually, you can change the weight from this multiplier. You can increase it to, let's say, 0.9 or as you want. And here's the result. We passed this prompt doc and we used this new model, and here's the result. It is good result. The style of these two models are available in this image. Thanks for watching. Hi, in this lecture we will learn how to create a good prompt. But firstly we will train our stable diffusion model on our images, and after that we will use it. And here you should know that to use stable diffusion version 2 we need to enable Xformers. But how can we do that? Let's do right click on web UI users.dat program, and here we should click show more options, and here we should click on edit. Now what we will do, actually we will make command line underscore h equal to hyphen hyphen Xformers space hyphen hyphen mid VRAM. Okay, and that's it. By doing this you will enable Xformers and mid VRAM, and you will be able to generate an images with 768 width and 768 height using stable diffusion model version 2. As you can see here, this is Dream Booth collab notebook. Firstly, let's activate GPU. Now let's click on connect, and let's click on this cell, and this cell, and here we will connect our Google Drive. to this notebook. Let's click on this symbol here, and we will run this new cell also, and we should click on connect to Google Drive, and here we should pass our token. You should pass the model ID of Dreamlike Diffusion model. Here we will use Dreamlike Diffusion model version 2. This notebook will download this Dreamlike Diffusion model version 2 directly from Hugging Face community. Now we will specify the directory that we will use to put our model after training inside it, which is Stable Diffusion weights, and here put it Riyadh model. Riyadh, it is my name. We should now run this cell, and here we should create our concepts. Firstly, instance prompt. Here we will put the prompt that we will use to create my photo. We will use this prompt during training Dreamlike Diffusion model version 2 on my images, and we will use it also during inference, which is photo of ZWX Riyadh Al Madani, and we should describe my photo a little bit, like person, man, etc. And here we have class prompt. It is just a general prompt about what is inside my images. Based on this prompt, class prompt, we will create many images using Dreamlike version 2 diffusion model. We will use these images during the training to make the training better. And here we should put the data directory and the class data directory. Actually, it's not important. And we should run this cell like this. Here you can pass your images. And here we will run train reboot script. But you should remove revision equal to FP16. You should remove it from here and start to train. We will train our Dreamlike Diffusion model for 800 steps with resolution 512. Here we should put the model path. You will find it in your Google Drive. Here in this Stable Diffusion weights Riyadh model, and we should open this folder and copy this directory. Now we will run this cell, conversion cell. Firstly, we should specify the value of weights directory, which is equal to, we should make it like this. Now you will see model.checkpoint. Now we will create our pipeline. Just we need to pass the path of our model. Now we should write the prompts that we created previously. And let's click on enter. And here's the result. Okay, that's good model. This one's also good. Now let's put this Dreamlike Diffusion model in our Automatic 1111. To use this model during learning how to create a good prompt, you will find it in your Google Drive. You just need to download it from there. It is model.checkpoint file inside the 800 folder. Now let's put our model in our Automatic 1111 software. Firstly, we should go to models like this, and we should open Stable Diffusion, and here we should put our model. Let's put it here, and here's our model. Let's change its name to Riyadh model, like this. Now let's open our automatic 1111 software. We need just to click on web UI user.bat program. Now let's copy this URL and put it in our browser. Now let's use our model. We just need to click here, and we should select Riyadh.checkpoint, like this. Now let's put the prompt that we used to train our Stable Diffusion model on our images. So let's type photo of ZWX Riyadh Al-Madani, like this. Now let's click on run to see the result. And here's the result. It is good image. Now let's learn how to build a good prompt. Firstly, we need to specify the subject. In other words, what we want to see in our image. Let's say, for example, photo of ZWX Riyadh Al-Madani as a king. Okay, yes, this image it is good actually. Now we should specify the medium, which is the material that our Stable Diffusion model will use to create our image. It is a good idea to put it at the beginning of your prompt. You just need to put comma here, and here you should specify the medium. For example, water color, like this. This is the medium. Water color painting. Let's click on generate. Yes, this image it is good. Here our Stable Diffusion model used watercolor pens to create this amazing image. Actually, the medium it is very strong modifier that will make your image very good. Let's try another medium. For example, let's try digital painting. And let's click on generate. And this image it is also good. As you can see here, the medium will affect a lot on the style of the generated images. Let's change the medium to oil painting, like this, and let's see the result. Here, our Stable Diffusion model used the oil painting materials to create this image. Let's now use photography medium, photography painting. Okay. By using this medium, we will get more realistic images. Let's click on generate, and here's the result. Let's click on generate again to see another image. This image it is good also. We can also use ink wash painting, and here's the result. If it is not like what we want, you can increase the importance of this sentence. You just need to open and close these parentheses, and here you should put colon, and you should put the importance of this sentence. Let's make it equal to 1.2, which means we increased the importance of this sentence by 20%. Now we will click on generate. Okay. And here's the result. This one it is also good image. And this one also good image. We can also change the medium to acrylic painting like this. This image it is good, and this one also it is good image. As you can see here, the medium will change the style of the generated images a lot. Okay, this image it is good also, and we can also use pastel painting as a medium, and here is the result. As you can see here, now the style it is different than what it was previously because we changed the medium. And here is another result. It is also good image. Now let's use just digital painting here. Okay, let's add more to our subject. Let's type casting lightning magic like this. So now we add it to our subject. Let's click on generate, and here is the result. Let's increase the importance of this sentence. Let's make it 1.2, for example. And here is the result. Let's click on generate again. Yes, this one is good. This image it is good. Now to make sure that we will get detailed clothing and detailed face, we just need to add these things to our prompt. So we should type detailed clothing and detailed face, for example. Let's click on generate. Yes, this image it is good also. I think this sentence, casting lightning magic, affected a lot on our images. So let's put these square brackets here. Let's put the here, which is meaningless word, and let's put 0.7, for example. It means for the first 70% of the time steps we will use just that, which is meaningless word, while the rest time steps we will use this sentence. Okay, let's see the results. Let's make this number smaller. Let's make it 0.4. If you want to increase the importance of this sentence, for example, you just need to put these two parentheses, and here you should put, for example, 1.5, which means that we will increase the importance of this sentence by 50%. And sometimes when we increase the importance of the sentence a lot, it will affect on the subject inside our images. So we use these square brackets to increase the importance of the sentence of casting lightning magic sentence without affecting on the subject a lot. Let's add more to our subject. Let's type looking to the camera like this. Let's increase the importance of this sentence. Let's make it 1.2. Actually, the best value for this sentence is 1.3. Now we will add the artist style, which is also strong modifier that will affect a lot on the style of our generated images. For example, let's use fantasy artwork, and let's click on generate. Yes, this image it is good. Let's click on generate again, and this one also, it is also good image. Actually, you can combine 2 or more art styles. And here let's specify the background. Let's type fantasy. Background surrounded by massive mountain ranges. Let's click on generate to see our new background, and here's the result. Here I increased the importance of this sentence by 40% to make sure that I will see this background. The best value here actually it is 1.3. We can also add very beautiful scenery like this. Let's click on generate. Okay, we have good images here. And this one also. This image it is good. Let's add another art style. Let's add hyper-realistic art style. Here I added hyper-realistic artwork. It will make the generated images more realistic. We can also use full body artwork. Okay. Actually, all these images are good. And you can also add the name of your favorite artist. Here I put it Stanley Artgerm Plus Artist. It is also good modifier that will affect a lot on the style of your generated images. And here I added dragons in the background, and I made the importance of this sentence equal to 1.5, and here is the results. Yes, they are good images. This one is good, and this one and this one. Now let's add more to our prompt. Let's type sharp focus like this, detailed eyes, and we will make this one detailed gorgeous, like this, detailed gorgeous face. Let's click on generate, and we will add big depth in field to our prompt to make most of our image clear and sharp. Let's click on generate. Here I added also detailed nose and science fiction. Okay, the results are good actually. This one is very good. Now we will control the colors of our image. Now let's put the color keywords inside our prompts. Let's put them here. We just need to add the color keywords to our prompts. For example, iridescent blue. As you can see here, we added iridescent blue. Let's click on generate. As you can see here, the color here, it is blue. We can convert it to gold like this, iridescent gold, and here is the result as you can see here. And we can convert it into green like this. As you can see here, the green color, it is more in this image than the images that we generated previously. And here we used iridescent red, and as you can see here, the red color, Now we will control the lightning, okay? We will use the lightning keywords to do that. The lightning keywords will affect a lot on our generated images. Let's firstly use low key lightning, okay? Let's click on generate. By using this low key lightning will give high contrast lightning to enhance the mysteriousness of a scene or film, in this case our image. You should know that the entire emotions in your image can change just by slightly changing the lightning direction. We can also use high key lightning. As you can see here, it is brighter than low key lightning with minimal shadows and less contrast. And by reducing the contrast, we mean that we reduce the difference between the colors of our image. For example, we will not see very dark regions in our image. We can also add sunlight, and here is the results using sun lightning. And here I increased it again, and here's the result. As we can see here, the light here from the sun. Now let's put the lightning source behind the object. How can we do that? Let's delete this one. Here I used backlight, and here is the result. We put the light source behind the object. And the same thing here, the light source actually it is behind the object, as you can see here. And the same thing here. Now let's use another brightening technique. We will use crepuscular rays. It will create light ray breaking through the clouds. Let's click on generate to see the result. And here is the result, as you can see here. I will delete casting lightning magic to see the difference here. And here is the result, as you can see. And this one, it is also good. Here I used backlight again. We will learn many different things about lightning later, okay? Now let's talk about the negative prompts. It is very important thing, especially if you are using Stable Diffusion model version 2. By specifying your negative prompt, you will increase the quality of your image. You will create amazing images. Let's say that we have this image here. Let's fix the seed of this image. Now what we want, actually we don't want to see these clouds here. So what we should do, actually we should type clouds here. And here is the result. You can increase the effect of clouds word by let's say 20%, like this, to make sure that you will not see clouds in your generated image. And here is the result. We don't see any cloud here. Now let's say that I want to change the color of the skin. In other words, I don't want to see brown skin. Let's click on generate. Now the color, it is different. Now it is white, but the image changed a lot. How can we keep our previous image but with different skin color? We just need to put meaningless word, which is the, and we should put 0. Let's say 5. It means for the first 50% of the time steps we will use this meaningless word that it will not affect on our image, and in the rest time steps we will use this brown skin in the negative prompt. Let's click on generate. Yes, now it is better. And the color of the skin, it is we can say it is white now. Okay, let's increase this one to 0.6. By doing this, you will see that the generated image will be similar to the previous image. Let's say now that I don't want to see black hair, so I will type black hair like this. Let's increase the importance of this black hair. Okay, let's make it 1.3. Let's increase it again to 1.9, for example. The color of the hair, now it is different from what it was previously, but our image changed a lot. So we will do like what we did previously. We will open these square brackets, we will put the here, and we will put colon, and we will put colon here also, and let's type here 0.5. okay, and here's the result. Actually here the hair color, it is not completely black. Let's reduce this one to 1.8. let's make this one 0.3. as you can see here, the color is blue now. And here we can also improve our image by putting, let's say, blurry, for example. It will make our image more clear and more sharp. We don't want to see blur in our image. Let's click on generate, and here is the result. It is better than what it was previously. If you want to make your image more realistic, you just need to type cartoon here, and painting also, and here is the result. It is more realistic image. And to avoid destroying our original image, we just need to use our previous way. We will type the here colon, and colon here also 0.5 like this, and here is the result. Okay, we can increase this number. Now this image, it is good. Now let's add these words: under exposed, over exposed. Actually, in photography, we refer to the images that are darker than the actual scene by underexposed, and the images that are brighter than the actual scene by overexposed. Let's see the result. Let's now open these brackets to make our image better, and we will put the here colon, and overexposed, underexposed, colon 0.6, for example. Now it is good. We can make it smaller. Now this image, it is also a good image. Let's add more negative words like ugly, and disfigure, and deform, like this. And let's do the same thing here, and here, for example, 0.5. Actually, the best value here it is 0.7. Let's add low contrast here also. Let's put it here also in this place. Yes, this image it is good. Let's make it younger. 20 age. Now that's better. We can increase it if we want to, let's say 1.2 for example, and the result now it is good. Here I removed age from my prompt. Let's add to our prompt, for example, bad anatomy and body out of frame. Okay, and watermark, for example, signature like this, cut off, draft, grainy. Let's click on generate, and here is the result. And like what we did previously, we can put all these things here. Okay, the best value here it is 0.2 actually. Now we have this image here. If we want to make it even better, how can we do that? Let's send it to image to image. Okay, firstly let's improve the nose here. We just need to send it to InPaint, and let's mask this nose here. Here we will select only mask like this, and let's reduce denoising strength to something small. We don't want to change this nose completely, but we want to enhance it to make it better. Here let's make this one -1, and let's click on generate. Now this one it is good. Let's delete this image and let's send this image to InPaint. Now if we want to change another thing, we can change it. Now we can also use poor man's outpainting to extend this image. We will firstly start with the left side, and here we will click on generate, and here we should make this one whole picture, and we will make this one fill. Let's click on generate, and let's increase the denoising strength here to, let's say, 0.8. Now this thing it is good. Let's increase the bottom here. We will just select the down. This one we will send it firstly to our InPaint, and we will click on generate. Now this image it is good. Let's now send it to extras to upscale this image to get high quality image. Here we will specify the first upscaler, which is this one, and the second upscaler, which is this one, and we will increase the contribution of this scaler by doing this, and we will also try to enhance the face. Let's click on generate, and here's the final result. It is high quality image. Thanks for watching.
In this video, we're going to see another useful operation, and that is to copy two arrays, or copy one array into another array. So let's say we've got this array. We're going to say integer array, I'll call it array 1, equals, and let's initialize it with a few values. So I'm going to say 2, 4, 6, 8, and 10, again like the previous example. And now we've got an array with values 2, 4, 6, 8, 10. So it's of size 1, 2, 3, 4, 5 again. That's the size 5. And we've got the values 2, 4, 6, 8, 10 in positions 0, 1, 2, 3, and 4. Now let's declare a second array, and we want to have that array have the exact same values as the one at the top. So you agree that I can just say array 1, or can we? If you remember, when comparing arrays, we talked about memory locations here. So if I say int array 2 equals array 1, what am I copying? Am I copying the values there? Or am I just saying that array 1 and array 2 should point to the exact same object? I didn't make a copy of the object, I'm pointing to the exact same object. So this is a way of not copying two arrays. And let me just show you when we print this out. So let's say system out print line. Well, instead of just having a print line method, let's just create our own method quickly here. So I'm going to say public static void, and let's call this one print array. And for this print array, I'm going to pass in, and now we can just quickly have a look at methods also when we're passing in array. So we can say int array and call this one, let's just call it array there. And then we're going to take this array, the value that was passed in the array, and we print it out. So you remember that enhanced for loop, where we just get the value from the specific array that was passed in, and it will print out those values for us. So I'm going to say system out print line, and I will just print out the value there. So now by calling this method print array, and I pass in an array of type int, it will go and say, well, let's take from this array position 0 and place it into value, and then we print it out. The next time it runs, it will take position 1 of the array and place it into value, and so forth. That's just the enhanced for loop. So now, if I want to print out my array, I can just call print array and pass in, let's pass in array 1 there. And then let's use a system out print line to put a gap between the two printouts. And then I'm going to use the same method again, and let's print out array 2 now. So if we do that, let's run it from here. So you'll see the values are exactly the same. It's 2, 4, 6, 8, 10 and 2, 4, 6, 8, 10. It's because essentially these two are pointing to the exact same array. So let's say I'm going to say array 1 at position, let's say 1, should not be, you can see that array 1, this one at position 1 is the 4. So let's change the 4 to a 5 there and see how it prints out now. So if I run this now, array 1 should now be a 5 at position 1. So let's see the printout. You can see, yeah, it changed to a 5. But look at the bottom one, it also changed to a 5. So this is again just confirming what I said, that both array 1 and array 2 is pointing to the exact same object. So if I change something in array 1, it will be essentially changed for array 2 as well. And that's not what we want. Okay, so this is the way of not copying two arrays. Right, so let's take that away. So step number 1, what we want to do is to create an array of the exact same size as the one we want to copy. So I can see that the size here is 5 by just counting them 1, 2, 3, 4, 5 values. But in coding, normally you can't see the size, and your sizes could be fixed or not. Could be a size of 10 or 15 or whatever that you know, but it can also be a size that you don't know. So the best way of doing this is to say new int create a new array, but we're going to set this size. Instead of passing in 5 there, if you don't know the size, we'll just passing array1 dot length, and that will give us the same size. So now the two arrays, there's array 1 already declared and initialized. This one, array 2, is now initialized with a length of 5. And now if I don't set any values, then at position, essentially this array will now look like this. If I don't set values, it will just have zeros there, 0, 0, 0, 0, 0, 0. That will be how the array looks if I don't assign any values. So this one, after this one line, I will have 1, 2, 3, 4, 5 zeros saved in the array. Okay, now we get to step number 2. After setting the array the exact same size as that one, we can now use a for loop. So I'm going to use a normal for loop. There you've got the enhanced one. So I'm just going to use a normal for loop here. So integer I equals 0, I less than, and I can take array 1 or array 2 because they are now of the same length. But let's just take array 1, and then we need to increment using I++ to run through every element. So essentially what we want to do for step number 2 is to take every single value of array 1 and place it into this exact same position in array 2. So we're going to say array 2 at that specific position should be what array 1 is at that same position, which we call I. So now after this for loop, let's just print out these two arrays again. So I'm going to print out array 1. Let's say array 1 there. I'm going to have a simple system out print line to just separate the two with one line. And let's print out array 2 the same way again. So if I run this, obviously it's the same as the previous example. Both will have the 2, 4, 6, 8, 10. But now the difference is I can now go to array 1 and go to, let's say, position 1 now and change the 4 there to a 5. And let's run this again, and you can see then that array 1's 4 has been changed, but not the one for array 2. And you can see there, the 4 has been changed to a 5, but that one is still a 4. And in this way, you can see that the two arrays are not pointing to the same object or the same array. We are working with different arrays.
Hi, in this lecture we will talk about regional prompter, and we will learn how to apply our prompt on just specific region in our image. Firstly, we should go to extensions, available, and you should click on load from. And now here you should type regional prompter, and you will find the regional prompter here. I downloaded the regional prompter previously. Let's go to installed. It is this one here, SD Web UI regional prompter. After downloading the regional prompter, you just need to click on apply and restart UI. Now let's say that we want to generate an image for black cat and white dog. Let's put our negative prompt to make the image that we will generate good image. Let's click on generate, and here's the result. The first image, it is good image. Here we have black cat and white dog. This one is not correct, and this one also. We don't want a black and white cat, and this one also, it's not good. This one's good. This one is not good actually. Okay, we will try to make all the images something like this image by using regional prompter. We just need to click on this section and we need to activate regional prompter. Here we have the generation mode attention, and the divide mode or the split mode is horizontal. It is good also. We don't need to change these settings. Now we should click on visual and make templates, and here's the result, 0 and 1. These two regions divided equally, and you can change this ratio from this divide ratio parameter. Now let's go again to our prompt. What we will do now, a black cat and a white dog. Here we should type break, and you should repeat your prompt again here. Okay, here in the first prompt we should type, let's change it a little bit, a cat and a dog, and here we will specify, for example, the color of the cat, a cat with black color. We will use this prompt for the region number 0, like this, and the same thing here. Let's copy this and put it here, and here a dog with the white, and here we put it break to separate these two prompts. Now the first prompt for the first region and the second prompt for the second region. In the first region we want to see a cat with a black color, while in the second region we want to see a dog with a white color. You should write break in capital case like this to work. Now let's see the results. Yes, the results now, they are better than what it was previously. But why we wrote a cat with a dog in these two prompts? You need to do that to tell Stable Diffusion that this picture will have two objects, two animals. That's it. Now let's say that the prompt that will specify the objects in the image, it is very long prompt. So it's not a good idea to repeat it for each region. So we will click on prompt, and here we will check on use common prompts like this, and here we will click enter. We will type break here, and we don't need this one. We need just to write this text one times, and here we will type the style of this region and the style of the other region. Let's click on generate. All these images are good. In the first region we have black cat, and in the second region we have a white dog. Now let's create complex regions. Firstly, we have horizontal. When we make split mode parameter equal to horizontal, it means that automatic 1111 software will stack these two regions horizontally. Let's add another region. We just need to type comma, and we should put 1 here, and we should click on visualize and make templates, and here's the result. Now we have 3 regions. Now let's say that we want the region of the first bigger than these two regions. Let's say that we want to make the area of this region equal to 2 times the area of the first region or the area of the second region. So let's type 2 here, and let's click here, and here's the results. Now this region, it is bigger than these two regions. We can also select vertical. Let's click on visualize and make template, and here's the results. Now these regions stacked vertically. Now we can divide the regions vertically and horizontally at the same time. How can we do that? Firstly, we should select horizontal. Let's click on visualize and make template. Now we have this row, okay? It is like a row with the 3 elements or 3 regions, 0, 1 and 2. Let's create another row. We just need to put semicolon here and let's put the regions of the second row like this. Let's make them similar to the regions in the first row and let's click here. The first number in each row, this one and this one, will specify the height of the row. Let's say that we want to increase the height of this row, so we will make it 2 like this and we will click on visualize and make template. And here's the result. Now the height of this row is larger than the height of this row. Okay, it is 2 times the height of the second row. The other numbers, they will specify the width of each region. Let's say that we want to increase the width of this red region. Just make it 2 and click on visualize and template. And here's the result. Now this one is wider than this one. This region is wider than this region. Now let's make this region wider than this region. We just make this equal to 1 and this equal to 2 and let's click on visualize and make template and here's the results. And the same thing for the regions in this row here. We can make this region wider than this region, so let's make it equal to 2 and here's the result. It is wider than this region. Now let's make the number of regions in the row at the top equal to 3. Let's say we have 3 regions. Let's put the number of the third region. Let's make it 2 also. Let's click on this button and here is the result. And here the area of region 1, it is equal to the area of region 2 because both region 1 and region 2 have the same value, which is 2. And here the area of region 1, it is 2 times the area of region 0, and the area of region 2, it is 2 times the area of region 0. And we have 3 regions in this row, while we have just 2 regions in this row here. Now let's say that we have 3 regions. Okay, let's click on visualize and make template. For example, we have this image here and here's the prompt that I used to create this image. I used Riyadh model checkpoint here. The prompt is digital painting photo of ZWX Riyadh Al Madani with 0.5, which is the importance of this sentence. As a king looking to the camera, fantasy artwork, full body, detailed face, detailed nose, detailed eyes, sharp depth of field. Okay, and here is our image. And now we want to make the left side here has trees and the weather and this side is winter. And we want to make this side here, this right side, has sun and sky and clouds. How can we do that? As we said previously, we have 3 regions. And now we want to make this region, the first region here, region 0. We will make the weather winter here and we will put trees here. So what we will do, we will put break and now we will put trees and winter like this, and we will put a break again here. We will not change the middle region, we will make it as it is. We will just use this prompt to create it, to keep our face as it is. Okay, and we will type break again, and here what we will do, we will specify what we want to see in this region here. We want to see sun with the sky, clouds like this, and here I should activate regional prompter, and here's the result, the same face. Here on the left side we have trees, and the weather is winter here, and here we have sky, clouds. Here I increased the sunward importance by 30% in the first 50 time steps, and I increased it again by 70% in the rest time steps. And as you can see here, you can see the sun, and here I put it detailed trees to make them more clear. Let's put here blur, and here we will change the sun to moon, and here we will put night, and here's the result. Let's increase moon word, and here's the final result. Here's the moon. Thanks for watching. Hi, in this lecture we will talk about dynamic prompts. Firstly, we need to go to extensions tab and to available tab, and here we should install dynamic prompts. We just need to type dynamic prompts here, okay, and you should install it. You should click on this button here, and you should go to installed and click on check for updates, and finally you should click on apply and restart UI. Now let's say that I have this prompt: digital painting, a portrait photo of ZWX Riyad Al Madani, comma, handsome, sharp, detailed eyes, detailed nose, detailed face, blue t-shirt with importance 1.5, neon lightning, crime city background. And I put this universal negative prompt here, and here's the result. This one is good, and this one also, and this one is very good. Now let's use dynamic prompts. You will see dynamic prompts here. Click on it. Now let's learn how to use dynamic prompts. Let's say that I want to try many different haircuts. Okay, so what we will do actually here, we will open these curly brackets. Here I will use ChatGPT, which is a chatbot. You can ask ChatGPT any question and it will answer you. So now, rather than searching about the haircuts using our browser, which is tedious, so what we will do actually, we will ask ChatGPT to give us the name of the haircuts, and it will answer you directly. And it is free actually, and it is very easy to open an account here. Now let's ask ChatGPT about what we want. Let's say create a list of 20 male haircuts like this. That's great. We will copy just 4 of them, okay? Now we will put these 4 haircuts between these curly brackets. Here we will put vertical stick, and we will put vertical stick here again, and here also, and let's increase the importance of each one of these choices. Let's make this one 1.4, and this one also, and this one, and this one. Okay, and we should put these parentheses here, here, and here. Okay, now dynamic prompts will take one of these choices each time. So firstly it will take this prompt and it will put the first choice with it, and it will generate one image. After that it will take this prompt and it will take the second choice and put it with our original prompt and generate one image again, and it will take this prompt and we will put this choice with it and we'll generate another image, and finally we will put this original prompt with this choice, the final choice, and we will generate another image. Okay, but before that, here is our dynamic prompts. We should click on combinatorial generation to do this process, and let's click on generate, and here's the result. We have all these amazing images, each one with different haircut. This one, and this one. That's great. Now let's change the color of our hair. Let's take just these two haircuts. Okay, and now what we will do, we will specify the color of our hair. Let's put the choices. Firstly, we want to see red hair. Let's increase the importance of this color to 1.4 also. And the second choice is let's say green with 1.4 importance, like this. And let's put another color like brown, and let's make its importance equal to 1.4. And now what we want, actually we want to mix these colors. For example, we want red and green, or green and brown, or brown and red. How can we do that? We just need to type 2 sign dollar, like this. By doing this, you will take two choices each time. In other words, each time it will take two colors and combine them with our original prompt. Let's click on generate. And here is the result. This one, the hair is green, and this one it is brown. This one it is green again, green, brown, green, and this one is red, green, red. That's good. Actually here we didn't see the mix between colors, so you can increase the importance of these colors to increase the opportunity that you will see the mix between them. As you can see here, these colors affected on the t-shirt color, but here actually we want to make the color of t-shirt blue, like what we said in our prompt. So how can we do that? For example, you can use a regional prompter to change just this region here and keep this region as it is. Let's do it. Let's click on regional prompter, active, like this. And here we should click on visualize and make template, like this. We will make it vertical Okay, we will change this region and we will keep this region. Let's make the height of this region 2 times the height of this region. Let's make it 2. Now that's good. By doing this, we will keep this region and we will change just this region here. So now let's change our prompt. Our original prompt is this one here. Okay. Now what we will do, actually, we will put break like this. We will change just the region number 0. Here we put the prompt that related with region number 0. And here we will put break and break because we don't want to change region number 1. That's it. Now we will click on use common prompt, and we will click on prompt ex like this. We will use this prompt for region number 1, and we will use this prompt plus this prompt for region number 0. Now let's click on generate, and here's the result. This one is good, with a blue t-shirt and a green hair with a specific haircut. This one also brown hair, blue t-shirt. This one green hair with a blue t-shirt. This one I think brown and green. This one is brown. This one green. This one green, red, and this one green, I think, red, green. Yes, that's good. And there is another way to do it, to keep most of your image as it is and change just a specific part of your image. Let's say that we have this image here. We should send it to in Paint like this. Here we will not use regional prompter, so we will deactivate it by clicking on this checkbox. Okay, so we will go back here and we will put this here in this place. Okay, we will delete this, and that's it. Now we will mask the region that we want to change, which is this region. Okay, we will mask it to change the style of the hair and the color of the hair. Now what we will do, we will select only mask like this, and we will make this one -1 to generate different images each time, and we will click on combinatorial generation, and let's click on generate, and here are the results. This one green, brown, I think it's green also. Okay, this one is good, and this one and this one. Yes, that's good. Here we didn't change our original image a lot. We changed just this region here. And there are many other things in this dynamic prompts extension, but we talked about the most important one. Thanks for watching. Hi, in this lecture we will talk about ControlNet and how to use it with Stable Diffusion models to create amazing images. Firstly, let's go to image. Okay? Previously we learned how to add any ControlNet to our Automatic 1111 software. Firstly, we should go to ControlNet version 1.1 like this. and we should enable this control net unit 0, because we can use many control nets at the same time, and we will learn how to do that later. Now we will add our image here, our reference image. We just need to click on this place here and add our image, and here is our image. Okay, now what we will do, we will specify the control net that we want to use. Let's click here, and we want to use open pose control net. This control net model will take the human poses as inputs to make condition using these poses. In this case, the poses of this player in our reference image. We will make the poses in the generated image similar to the poses of this player in our reference image using this control net. Now we will select the preprocessor that we will use with open pose control net. This preprocessor will extract or detect the poses in our reference image, and it will create the input to our open pose control net. Here we have 5 preprocessors. Each one of them will detect specific poses in our reference image. Let's select the first one, open pose preprocessor. Let's now click on this symbol to apply this preprocessor on our reference image to detect the poses. And here's the result. As you can see here, we will make the poses in the generated image similar to these poses here. Now let's use another preprocessor. Let's use open pose full preprocessor. This one will give you all the poses in our reference image. By using this open pose full preprocessor, you will make the image that you will generate more similar to your reference image. We will click on this symbol here to pre-process this image and finding the poses that we will use as input to our control net open pose. And here is the results, as you can see here. Now we have the poses inside this image, the poses for this player with all the details like the hand and the face expression. Here we can control the weight of this open pose control net to specify the importance of this condition. Now I created this prompt: digital paintings, man running, fantasy background, mountains, dragons, and here I put it the universal negative prompt. Now here is the result. As you can see here, this man, the poses of this man similar to these poses here for this one. Okay, and that's great. And here I used ZWX Riyad al-Madani prompt to get my face in the generated image. Okay, it is good, but the face is not that good actually, and we will learn how to handle this problem later. But as you can see here, when we use the control net, the fingers of the hand, they are very good compared to the images that we generated with just using our prompt without any control net. Now this image, it is good. We can send it to extras. Now let's scale up our image. Firstly, we should specify upscaler 1 and upscaler 2. And we can also improve the face by using GFP-GAN or by using code former, or we can use both of them. Let's click on generate. Now this image, it is very good actually. Let's try another open pose preprocessors. We have also open pose face. Let's see this processor. This one will work similar to the first preprocessor on this list, but this one will give you the facial details also. For example, let's say that I have this image here. Let's click on this symbol to see the result. And as you can see here, this preprocessor extracted the facial details of our reference image. Now let's click on generate, and here is the result. As you can see, the facial details in the generated image similar to the facial details in our reference image. We have also open pose face only. This one will just give you the facial details without any other thing. Okay, so let's click on this symbol here, and here is the result. Let's click on generate, and here is the result. The position of the shoulder will be different each time, but the facial details are the same, because this preprocessor will just detect the facial details. Now let's select open pose hand. This one will work similar to the first preprocessor in this list, but it will give you more information about the fingers and the hand. As you can see here, this preprocessor extracted the hand poses also. And here is the result. And now actually we can change these poses a little bit as we want. Firstly, we should go to extensions, available. We should click on load from. You should add this SD Web UI Open Pose Editor, and you should also download Open Pose Editor extension. And you will find this edit here. Just click on it. Let's change this pose here and make it in this place, for example. Now let's send it to Open Pose Control Net, and now we will click on generate, and here is the result. As you can see. Hi, in this lecture we will learn how to use Tile Control Net to upscale our images in a very smart way. Firstly, we should go to Extensions tab, and now we should go to Available. We should click on Load From, and here we should search about Ultimate SD Upscale, and we should install it like this. Now we should go to Installed, and we should click on Check for Updates, and now let's click on Apply and Restart UI. Now I have this image. Now what we want, actually, we want to upscale this image using Tile Control Net. Firstly, we should send this image to Image tab like this. Now let's go to Control Net version 1.1, and now we should click on Tile, and here is the model that we will use to upscale our image, this Tile Control Net model. And here is the preprocessor, which is Tile Resemble preprocessor, and we should click on Script here, and we should select Ultimate as the upscale, and here we should make the sampling steps equal to 50, and denoising strength equal to 0.5. Now let's go back to our Ultimate SD upscale script. Firstly, we should specify the target size type. Let's select scale from image size, and let's make a scale parameter equal to 4. Okay, which means that the size of the new image after upscaling will be equal to 4 times the previous size. And here we should select the upscaler, Let's select RESR again, like this. And here we will check tile width parameter and tile height parameter by making tile width parameter equal to 512 and tile height parameter equal to 0. It means the width and height of each tile during upscaling equal to 512. Now let's click on generate to see the results. And here's the result. That's amazing. This upscaled image is highly detailed image, as you can see here, compared to our previous image. This tile control net added more details to our original image during upscaling. It is high resolution image with more details. Let's see this tree here. Let's zoom in. You can see how much details that our tile control net added to our original image during upscaling to get this tree here. That's amazing. Actually, there are many different upscalers, but this one is the best. This tile control net, it is the best upscaler. But you should know that you should reduce the denoising strength, because as we said previously, this tile control net will add new information to your image. So to avoid changing your original image a lot during upscaling, you should make denoising strength something like 0.5, for example, to keep the main idea behind your original image. Thanks for watching. Now let's use another control net model, which is inpainting control net. So firstly, let's send our image to image tab. Actually, this model, it is better than our previous way, because now we can make denoising strength very large value, and at the same time we will get good results. Now let's mask the head here like this using this paint brush, and here we will make the inpaint area equal to only masked, and you can increase denoising strength to, let's say, 1, and we will get good results also. And now we will go to control net, and we should select inpaint like this, and here we will make the processor inpaint global harmonious. We should click also on enable, this one. Let's click on generate now to see the result, and here is the result. It is good. The face here, it is good actually. And now let's use our previous way. Let's disable our control net by just clicking on this enable checkbox here. Now let's use our previous inpainting algorithm with very high denoising strength, and let's see the result. And here's the result. As you can see, it is very bad. The result is not good at all compared to our inpainting model. So from now on, we will use this control net inpainting model to do inpainting. Let's enable it again. And here's another result. That's really good. We can send it to extras and using GFP-GAN and code former to make the face better. Okay, let's use this one and this one, and let's click on generate, and here's the result. That's very, very good. let's talk more about control net tab here. We have also this right icon. Let's click on it. Here we can create a new canvas. Okay, we can specify the width and height of this canvas. And if we want to create it, so we just need to click on create a new canvas. And here is the result. Now you have this empty canvas. Let's, for example, using Scribble, Control Net, and you can draw on this canvas anything that you want. For example, bat, like this, and we use this processor, invert from white, BG, and black line processor, and we use this processor, invert from white, BG, and black line processor. Okay, and now here is the result. It is a bat from this Scribble. That's amazing. And here is another result. And you can click on this icon if you want to take a photo using your camera. Let's take an image. Let's click on this button here. Now we will use Canny Control Net. Okay, let's tune Canny low threshold and Canny high threshold to get the best Canny input. And this is good. Now let's click on generate to see the result. And here is the result. As you can see here, it's a good image. We have also low VRAM checkbox. If the memory of your GPU is smaller than 8 GB, so check this one. It will help you to avoid out of memory problem. And we have allow preview. This one will make us able to see the output from the preprocessor, or in other words, the input to the control net. Let's disable this one so you will not see the output. Let's click on it and you will see the output from the preprocessor. Okay, let's now click on this symbol to see the output. That's it. And we have preprocessor. This thing will pre-process the input before passing it to our control net. For example, this Canny preprocessor will convert our image into Canny input. And after that, we will pass this Canny input through our control net. We have also model parameter. Here we can specify which model that we want to use. For example, you can click on all here and click here and choose the model that you want. For example, let's select this one, Canny, and here you should specify the preprocessor that you should use, and we will select Canny preprocessor like this, and here's the result. Okay, and here we have control weight. This control weight will specify the importance of our control net. When we increase it, we will increase the importance of control net in the generated image. When we decrease it, we will reduce the importance of the control net in the generated image. And we have also starting control step parameter. This parameter will specify the time step that we will start using our control net in. If the value of this parameter equal to 0, it means that we will start using control net from the first time step in reverse diffusion. And we have also ending control step parameter. This parameter will specify the time step. When we reach this time step, we will not use control net anymore in the rest time steps during reverse diffusion. And when the value of this parameter equal to 1, it means we will stop using control net in the last time step in reverse diffusion. Actually, starting a control step parameter has more effect on the generated images than ending control step parameter. Because as you know, in the first time steps, to be more specific, in the first 20% of the total number of time steps, we will use them to create the contents inside our image, while the rest time steps we will just use them to add the style. So the controlling process actually will be in the first time steps. For this reason, we said that ending control step parameter will not have strong effect on the controlling process. Here we have another parameter, which is control mode parameter. And here we have three choices. The first one is balanced. The second one is my prompt is more important. By selecting this one, you will prefer your prompt on the control net during generation. And the last one is control net is more important. By selecting this one, you will prefer your control net on your prompt during generation. We have also resize mode parameter. We will use resize parameter to change the size of the input control map before passing it through the control net. For example, you will change the size of the output from OpenPose preprocessor to make it similar to the size of the image that you want to generate. This option will not take care about the aspect ratio. Sometimes this will not give you good results. So we have another options here. Now let's say that the aspect ratio of the control map similar to the aspect ratio of the image that we want to generate. In this case, we can select just resize option and it will not affect on the results. Because both of them, the aspect ratio of the control map and the aspect ratio of the image that you want to generate are the same. Now let's say that the aspect ratio of the control map and the aspect ratio of the image that you want to generate are not the same. So what we should do? Here we can select crop and resize. This one will take care about the aspect ratio problem, but it will cut from your control map, which will affect also on the results. For example, this option might delete the facial poses to make the aspect ratio of this control map similar to the aspect ratio of the image that you want to generate. At this case, the generated image will not have a head. The last one is resize and fill option. This one will just add pixels to our control map. It will add rows and columns to control map image to make the aspect ratio of it similar to the aspect ratio of the image that you want to generate. So by using this choice, you will not delete anything from your control map. Okay? Now let's learn how to use multiple control nets at the same time. Firstly, we should go to settings, and here we should go to control net like this, and here we should specify the maximum number of control nets that you can use simultaneously. Here we will make this parameter equal to 3, which means the maximum number of control nets that you can use at the same time equal to 3. And finally, we should click on apply settings. Okay, now let's do that. We have 3 control nets: control net unit 0, control net unit 1, and control net unit 2. Let's put our image here. Firstly, we will use Canny model. Let's apply this preprocessor on our image, and here's the result. Let's tune these parameters, Canny low threshold and Canny high threshold, to get the best Canny input. Now this is good. Here I will use resize and fill. Okay. Let's specify the size that we want, the size of the image that we want to generate. Let's make it 512 times 768, like this. And here is the result. We can change these parameters to get better results. Now here's the result. This image is good actually, but let's try to do more. Let's reduce the importance of Canny. Let's make it 0.6 for example. Let's click on generate. Now this image is really good here. Now let's use another control net. So we will go to control net unit 1, and here we will use open pose control net. Okay, and here we will put our image, our reference image. Okay, and now what we will do, we will click on this symbol here to find all poses for this image, and here we will also use resize and fill, and here's the result. Okay, and here's the result. This image is really good actually. Here I put it moon, and here is the result. As you can see here, the facial features similar to the reference image because of the open pose control net. That's great. Thanks for watching. Hi. In this lecture we will learn how to create good hands with perfect fingers in our generated image. We previously learned how to use open pose control net to make the poses of the generated image similar to the poses of the reference image. And we used open pose full preprocessor to find all the human poses in the reference image. And we noticed that the human poses in the resulted images were similar to the human poses in the reference images. But the problem actually in the poses of the hand and fingers. Most of the time you will not get good hand and fingers. Sometimes you will see 6 fingers in the hand and 7 fingers or less than 5 fingers, and that's not good actually. So we need another way to make good hand. So how can we solve this problem? Firstly, we should go to extensions, and what we will do, we will go to available, and we will install open pose editor. So let's write open pose. So you should install SDWebUI open pose editor. Firstly, I installed it previously, and you should go to check for updates. You should click on check for updates, and you should click on apply and restart UI. And you should also go to install from URL, and here you should put this link here to install WebUI depth library. It is another extension that we will use to get good hand. Okay, we should click on install, and we should go to install, click on check for updates, and we should click finally on apply and restart UI. That's it. Now you will see this tab, open pose editor tab. Okay, you should see this skeleton. Now let's select this skeleton. Let's move it down like this and increase its size. Okay, that's great. Now what we will do, we will change the position of these poses. Let's change the position of the arm. We just need to click on these circles and drag them to change their position. Let's make them like this. Okay. Yes. And if we want to save it here in this tab, we just need to click on Save, Preset, and put any name here, My Skeleton. And we should click on OK. Okay, now you will see this skeleton here in this list. And if you want to use this skeleton at any time, you just need to click on the name of this skeleton in this list. And after that, you should click on Load Presets. And if you want to add another skeleton or another body, you just need to click on Add button here. And the size of this condition, this image, by default equal to 512 times 512. But actually, you should change it based on the size of the image that you want to generate. Now, let's save this image. Let's click on Save PNG. Let's save it here. Now what we will do, we will go to Depth Library. You should see this tab, this extension here. We should click on it. And now we should click on Add Background Image. Here we should select our skeleton that we created previously. Now we should put the hands. We have many hand position choices that we can select from. Just select the one that you want. You should click on one of these choices here. Let's select this one. And now we should click on Add, like this. Let's reduce the size of this hand. And let's rotate this hand to make it align with our skeleton appropriately. Yes, like this. That's okay. Now let's add this hand again here. And now what we will do, we will flip this hand like this. And let's rotate this hand and put it here. Let's increase the size of the hand a little bit, like this. That's great. Now let's say that you put it another one, and now you want to remove it. That's easy. We just need to select it and click on Remove Selected. Okay. If you want to remove all these things here, we just need to click on Reset. If you want just to remove the background image, you just need to click on Remove Background Image, which is our skeleton. Now what we'll do, we will send these two hands to our control net. We will send this condition to our control net. Okay, now you will see this condition here. It is a depth map, so we should use a depth model, and we don't want to use a preprocessor because, as you can see here, this condition, it is depth map condition. We don't want to send it to our preprocessor to get the depth map again because we have it. Why we need to send it again to our processor? So we will make it none. And what we will do now, we will go to Control Net Unit 1. We will enable this CTRL-Net also, and we will click on Open Pose. And we will put our skeleton here. And here is our skeleton. We don't want to use a preprocessor because we have our skeleton here. Let's make the weight of this CTRL-Net equal to 0.5, and let's make the weight of this CTRL-Net, for example, 0.6. Okay. Now we should put our prompt here. Here I will use this model, Riyadh model, the model that I trained previously on my own images. Let's type digital painting. Okay. Now we specified the medium. Here I will put my prompt ZWX Riyadh Al Madani, and let's put the subject as a king, for example. Let's put mountain, background, and fantasy art, work, sharp, detailed face, detailed eyes, night, and let's put our negative prompt, for example, ugly, blur, and deformed, and disfigured. Let's click on generate. We will create an image with 512 width and 512 height. I think we should increase the weight of our condition. Here I made the weight of this CTRL-Net equal to 1 and this CTRL-Net equal to 1 also. And here is the result. That's good. As you can see here, we have 5 fingers here and 5 fingers here. Let's create many images, like 10, and take the best one. Let's see the results. We have this image. We have 5 fingers here and here. This one, it is good also. This one. Okay. This one, it is good. And we have also 5 fingers here and here. And during upscaling, we will make this image even better. Okay. This one, it is very good. Yes. Let's now choose one of these images. For example, this one. Let's send it to image to image. Now what we will do, we will go to CTRL-Net and we will enable this unit, and we will click on tile. We will go to script and we will select ultimate SD upscale. We will select the upscaler. Let's select this one, and let's make this one equal to scale from image size. Okay. And now let's click on generate to upscale this image. Yes, this image, it is good, but we have problem here. So we should reduce the denoising strength to keep our original image, or most of the information about the original image. Let's make it 0.33, and let's click on generate, and here is the result. That's good. And if you have any problem here, you just send it to InPaint, Okay, for example, if you have any problem with this hand, for example, we will not use a tile here. So we will make script equal to none, and what we will do, we will use in paint control net, and we will make the preprocessor equal to in paint global harmonious. Now what we'll do, we will select only masked. Okay, and let's change the size here to this. Let's mask the region that we don't like. For example, this region. Actually, let's increase the denoising strength a little bit, like let's make it 0.4, and let's mask the hand here. And here I changed the prompt to make it more specific to what I want to see in this region. I set open hand front view pictures, and here's the result, as you can see here. Now, as you can see here, this hand is better than what it was previously. Thanks for watching. Hi, in this lecture we will learn how to control light using control net. Firstly, we should install lighting based picture version 1.0. You will find it in the resources of this lecture. So you should download it in your local machine and add it to our control nets like what we did previously. Now what we will do, we will create our image using Riyadh model checkpoint. So let's type digital painting, and here we should type ZWX Riyadh Al Madani, like this, young, and let's type here night, background, half body, fantasy, artwork, wearing t-shirt like this, and here is the result. That's good. Now what we want, actually, we want to add a light source here in this place. Okay, so what we will do, firstly we should go to Photo P tab. We should click on new project, and here we will make the width equal to 512 and the height equal to 512, and we will make the background black background, and let's create our canvas. Now what we will do, we will add our source here. So what we will do, actually, we will click on this brush tool, and we will add a new layer. We will click on new layer. Now we will go to this place here, and we will control the size of the brush. Let's make it 133 pixels, and we will select soft round, and we will add our source, our lighting source here, and that's it. We will send it to text to image control net, and Here is our lighting source. We will make control weight equal to 0.6. It's a good idea to make it between 0.4 and 0.6. And let's change our prompts a little bit. Here I put it red bulb in the background, and as you can see here our Stable Diffusion model put this red bulb in the same place where we wanted to put our light source, okay, which is this region here. That's great, as you can see here. Now we will use this gradient corner condition. We will pass it through our lighting based picture. Let's change starting control step. Let's start using our control net after the first 20% of the total number of the time steps. Let's click on generate. And as you can see here, the lighting source from this corner. We have also spotlight. And here is the result. Here is our spotlight source. Okay, which is something similar to this. Now let's try to use this one. Now the light source from the bottom, as you can see here. And here is another result. Now let's say that we have this image and we want to add a light source in a specific region here. So what we should do, the size of this image actually it is very large. Firstly, let's send it to extras, and now what we will do, we will change its size to 512 times 512. Let's click on generate. Now we will send it back to image tab, and now what we will do, we will make denoising strength equal to 0, and we will click on generate to get the same image but with 512 width and 512 height. And now we have the same image. We will send it now to our photo P. Okay, now what we will do, we will convert this image to grayscale. We should click on this symbol here, and we should click on hue saturation. And now what we will do, we will reduce the value of this parameter. And now we converted this image into grayscale. That's good. Now what we will do, we will make this image blurry. Okay, so we will click on our image here, and we should go to filter, and we should go to blur, and we should click on lens blur. And now we can increase or reduce the blur in our image. Let's make it something like this, and we should click on OK. Now we will add another layer, and what we will do, we will add the lighting source here. We should click on this brush tool and click on this one. Okay, now what we will do, we will click on this one here, and we will specify the size of this brush, and we should specify the color. We will make it white. Okay, and now let's add the light source here. Let's reduce the size of this brush. Okay, let's make it 20 pixels, and let's add these small lighting sources here, here, and here. That's great. Okay, now what we will do, we will send this image to text to image control net. Okay, now we have our condition here, and here is the result. As you can see, we have this moon and all these stars Here I reduced the control net weight to 0.4, and here is the result. This one is better than our previous result. Okay, but the hand, it is not good here. Let's click on generate again. Actually here we made ending control step equal to 0.71, so we will stop using this control net after 71% of the total number of the time steps. This one is also good. We have this light source and all these stars here. If you want to keep the same poses in our reference image, we just need to use another control net. For example, open pose control net, and here we should put our reference image. Here we will use open pose face preprocessor, and here is the result. Now what we will do, we will click on generate. Now this image, it is very good image, as you can see here. Now the image, it is very good. Here what I did, actually I reduced the CFG scale to 7, and I used this reference image, our original image, as reference image. Okay, and the result now, it is very good image. Here is our light source and all these stars here. That's amazing. And here's another image. That's very good. Thanks for watching. Hi. In this lecture, we will learn how to create good hands with perfect fingers in our generated image. We previously learned how to use open pose control net to make the poses of the generated image similar to the poses of the reference image. And we used open pose full preprocessor to find all the human poses in the reference image. And we noticed that the human poses in the resulted images were similar to the human poses in the reference images. But the problem actually in the poses of the hand and fingers. Most of the time you will not get good hand and fingers. Sometimes you will see 6 fingers in the hand and 7 fingers or less than 5 fingers, and that's not good actually. So we need another way to make good hand. So how can we solve this problem? Firstly, we should go to extensions, and what we will do, we will go to available, and we will install open pose editor. So let's write open pose. So you should install SDWebUI open pose editor firstly. I installed it previously. And you should go to check for updates. You should click on check for updates, and you should click on apply and restart UI. And you should also go to install from URL, and here you should put this link here to install WebUI depth library. It is another extension that we will use to get good hand. Okay, we should click on install, and we should go to install, click on check for updates, and we should click finally on apply and restart UI. That's it. Now we will see this tab, open pose editor tab. Okay, you should see this skeleton. Now let's select this skeleton. Let's move it down like this and increase its size. Okay, that's great. Now what we will do, we will change the position of these poses. Let's change the position of the arm. We just need to click on these circles and drag them to change their position. Let's make them like this. Okay. Yes. And if we want to save it here in this tab, we just need to click on Save Preset and put any name here, My Skeleton, and we should click on OK. Okay, now you will see this skeleton here in this list. And if you want to use this skeleton at any time, you just need to click on the name of this skeleton in this list. And after that, you should click on Load Presets. And if you want to add another skeleton or another body, you just need to click on Add button here. And the size of this condition, this image, by default equal to 512 times 512. But actually, you should change it based on the size of the image that you want to generate. Now, let's save this image. Let's click on Save PNG. Let's save it here. Now what we will do, we will go to Depth Library. You should see this tab, this extension here. We should click on it. And now we should click on Add Background Image. Here we should select our skeleton that we created previously. Now we should put the hands. We have many hand position choices that we can select from. Just select the one that you want. You should click on one of these choices here. Let's select this one. And now we should click on Add, like this. Let's reduce the size of this hand. And let's rotate this hand to make it align with our skeleton appropriately. Yes, like this. That's okay. Now let's add this hand again here. And now what we will do, we will flip this hand like this. And let's rotate this hand and put it here. Let's increase the size of the hand a little bit, like this. That's great. Now let's say that you put it another one, and now you want to remove it. That's easy. We just need to select it and click on Remove Selected. Okay. If you want to remove all these things here, we just need to click on Reset. If you want just to remove the background image, you just need to click on Remove Background Image, which is our skeleton. Now what we'll do, we will send these two hands to our control net. We will send this condition to our control net. Okay, now you will see this condition here. It is a depth map, so we should use a depth model, and we don't want to use a preprocessor because, as you can see here, this condition, it is depth map condition. We don't want to send it to our preprocessor to get the depth map again because we have it. Why we need to send it again to our processor? So we will make it none. And what we will do now, we will go to Control Net Unit 1. We will enable this Control Net also, and we will click on Open Pose. And we will put our skeleton here. And here is our skeleton. We don't want to use a preprocessor because we have our skeleton here. Let's make the weight of this control net equal to 0.5, and let's make the weight of this control net, for example, 0.6. Okay. Now we should put our prompt here. Here I will use this model, Riyadh model, the model that I trained previously on my own images. Let's type digital painting. Okay, now we specified the medium. Here I will put my prompt ZWX Riyadh Al Madani, and let's put the subject as a king, for example. Let's put mountain, background, and fantasy art, work, sharp, detailed face, detailed eyes, night, and let's put our negative prompt, for example, ugly, blur, and deformed, and disfigured. Let's click on generate. We will create an image with 512 width and 512 height. I think we should increase the weight of our condition. Here I made the weight of this control net equal to 1 and this control net equal to 1 also. And here is the result. That's good. As you can see here, we have 5 fingers here and 5 fingers here. Let's create many images, like 10, and take the best one. Let's see the results. We have this image. We have 5 fingers here and here. This one, it is good also. This one. Okay. This one, it is good. And we have also 5 fingers here and here. And during upscaling, we will make this image even better. Okay. This one, it is very good. Yes. Let's now choose one of these images. For example, this one. Let's send it to image to image. Now what we will do, we will go to control net, and we will enable this unit, and we will click on tile. We will go to script, and we will select ultimate SD upscale. We will select the upscaler. Let's select this one, and let's make this one equal to scale from image size. Okay. And now let's click on generate to upscale this image. Yes, this image is good, but we have problem here. So we should reduce the denoising strength to keep our original image, or most of the information about the original image. Let's make it 0.33, and let's click on generate, and here is the result. That's good. And if you have any problem here, you just send it to InPaint. Okay, for example, if you have any problem with this hand, for example, we will not use tile here, so we will make script equal to none, and what we will do, we will use InPaint, control net, and we will make the preprocessor equal to InPaint global harmonious. Now what we'll do, we will select only masked. Okay, And let's change the size here to this. Let's mask the region that we don't like. For example, this region. Actually, let's increase the denoising strength a little bit, like let's make it 0.4, and let's mask the hand here. And here I changed the prompt to make it more specific to what I want to see in this region. I said open hand front view pictures, and here's the result, as you can see here. Now, as you can see here, this hand is better than what it was previously. Thanks for watching. Hi, in this lecture we will learn how to control light using ControlNet. Firstly, we should install lighting based picture version 1.0. You will find it in the resources of this lecture. So you should download it in your local machine and add it to our control nets like what we did previously. Now what we will do, we will create our image using Riyadh model checkpoint. So let's type digital painting, and here we should type ZWX Riyadh Al Madani, like this, young, and let's type here night, background, half body, fantasy, artwork, wearing t-shirt like this, and here is the result. That's good. Now what we want, actually, we want to add a light source here in this place. Okay, so what we will do, firstly we should go to Photo P tab. We should click on new project, and here we will make the width equal to 512 and the height equal to 512, and we will make the background black background, and let's create our canvas. Now what we will do, we will add our source here. So what we will do, actually, we will click on this brush tool, and we will add a new layer. We will click on new layer. Now we will go to this place here, and we will control the size of the brush. Let's make it 133 pixels, and we will select soft round, and we will add our source, our lighting source here, and that's it. We will send it to text to image control net, and here is our lighting source. We will make control weight equal to 0.6. It's a good idea to make it between 0.4 and 0.6. And let's change our prompts a little bit. Here I put it red bulb in the background, and as you can see here our Stable Diffusion model put it this red bulb in the same place where we wanted to put our light source, okay, which is this region here. That's great, as you can see here. Now we will use this gradient corner condition. We will pass it through our lighting based picture. Let's change starting control step. Let's start using our control net after the first 20% of the total number of the time steps. Let's click on generate. And as you can see here, the lighting source from this corner. We have also spotlight. And here is the result. Here is our spotlight source. Okay, which is something similar to this. Now let's try to use this one. Now the light source from the bottom, as you can see here. And here is another result. Now let's say that we have this image and we want to add a light source in a specific region here. So what we should do, the size of this image actually it is very large. Firstly, let's send it to extras, and now what we will do, we will change its size to 512 times 512. Let's click on generate. Now we will send it back to image tab, and now what we will do, we will make denoising strength equal to 0, and we will click on generate to get the same image but with 512 width and 512 height. And now we have the same image. We will send it now to our photo P. Okay, now what we will do, we will convert this image to grayscale. We should click on this symbol here, and we should click on hue saturation. And now what we will do, we will reduce the value of this parameter. And now we converted this image into grayscale. That's good. Now what we will do, we will make this image blurry. Okay, so we will click on our image here, and we should go to filter, and we should go to blur, and we should click on lens blur. And now we can increase or reduce the blur in our image. Let's make it something like this, and we should click on OK. Now we will add another layer, and what we will do, we will add the lighting source here. We should click on this brush tool and click on this one. Okay, now what we will do, we will click on this one here, and we will specify the size of this brush, and we should specify the color. We will make it white. Okay, and now let's add the light source here. Let's reduce the size of this brush. Okay, let's make it 20 pixels, and let's add these small lighting sources here, here, and here. That's great. Okay, now what we will do, we will send this image to text to image control net. Okay, now we have our condition here, and here is the result. As you can see, we have this moon and all these stars. Here I reduced the control net weight to 0.4, and here is the result. This one is better than our previous result. Okay, but the hand, it is not good here. Let's click on generate again. Actually here we made ending control step equal to 0.71, so we will stop using this control net after 71% of the total number of the time steps. This one is also good. We have this light source and all these stars here. If you want to keep the same poses in our reference image, we just need to use another control net. For example, open pose control net. And here we should put our reference image. Here we will use open pose face preprocessor. And here's the result. Now what we will do, we will click on generate. Now this image, it is very good image, as you can see here. Now the image, it is very good. Here what I did, actually I reduced the CFG scale to 7 and I used this reference image, our original image, as reference image. Okay, and the result now, it is very good image. Here is our light source and all these stars here. That's amazing. And here's another image. That's very good. Thanks for watching. Hi, in this lecture we will learn how to do infinite zoom. Firstly, we need to go to extensions, and now we should go to available. Let's click on load from, and here let's write infinite zoom, and you will get this one. You just need to click on install to download it, and that's it. Now we just need to go to installed and click on check for updates. Now we should click on apply and restart UI. Now you will see this infinite zoom tab. Okay, here we have many things. Firstly, we have total video length. You can specify it as you want. When you increase it, you will make your video that you will generate longer. Here, firstly, you should specify the command prompt that you will use with all these prompts here during out zooming or in zooming process. The first prompt, it is the first prompt in the video. The first prompt, it is a dense tropical forest. And our common prompt also, we can see it here, huge spectacular waterfall. And now let's see. And here we have a lash jungle, and as you can see here, we have this jungle. This means that at each second we will use different prompts. In second number 0 and 1, we will use a dense tropical forest. In second number 2, you will use a lash jungle. In second 3, you will use a thick rainforest. In second 5, you will use a verdant canopy. We will put this prompt with our common prompt, and we will do the same thing with all these prompts in this table. We will do this thing in zoom out mode, but in zoom in mode, we will move through these prompts in this table in reverse order. Now let's click on generate video, and here is the result, as you can see here. Now the resolution, it is very high. Let's see this video. That's great. Yes, that's really great. Here I made output with an output height equal to 768 to get this high resolution video. And we have this parameter custom initial image. If we want to start with a specific image, we can put this image here. We just need to click on drop image here to load your initial image, which is the first image in your video. Now let's go to another tab, which is video tab. Here we can specify zoom mode parameter. Now let's try to use zoom in. And here's the result. This zoom in video, it is much better than zoom out video. And we can do also upscaling. We just need to click on post process tab, And here we should specify the upscaler, and you should specify the value of upscale by factor. Here the value of this parameter equal to 2, which means that we will increase the size of each frame in the generated video by 2. And click on generate. And here is the result, which is a high resolution video. Thanks for watching. Hi, in this lecture we will learn how to transform our video into animation using temporal kit extension. Firstly, we should install this extension. We just need to go to extensions tab, and here we should go to available, and here you should write temporal, and you will find temporal kits, and you just need to click on install here, and you should click on check for updates, and we should click on apply and restart UI, and you will see this tab here, temporal kit tab. Now we should install another thing. Here we need to download FFmpeg. It is important program to make our temporal kit extension works correctly. So we need to click on Windows, and we should click on the first choice here. Now we should go to this place here, and we should click on this choice here. Now we downloaded this folder. Let's open it. Let's open this folder and this one. We should copy these files, Ctrl C. Now you should put here percentage user profile, okay, and click enter. And now you should create a new folder here. We will call this new folder bin, okay. So right click and click on new, and click on new folder, and here is our new folder. Rename it. Click on this symbol here to change the name of this folder. We will make it bin, the name of this folder. Now it is bin, but actually I created this folder previously, which is this one here, okay. So let's open it, and here you should paste these files that we copied previously. I pasted these files here, and that's it. Now you should go to this place here, and you should write edit the system environment variables. Let's click on this, and here you should click on environment variables, and you should click on path, okay. Now we should put the directory of these files, okay. Actually I put it the directory previously here, but to do that you just need to click on new, okay, and you should put the directory, which is percentage user profile, percentage again, backslash bin. That's it, okay. As I said previously, I added this path previously. Now we should click on OK, OK again, and that's it. In temporal extension, we have this tab, pre-processing tab. In this tab, firstly, we should put our video that we want to change into animation. So, firstly, we should click on this place here, and I put it my video here. Okay, this is my video. Okay, the second step, we should create a folder. This folder will have our new video after transformation. Here I create this folder. The name of this folder is resulted video folder. I put this folder in my desktop. It is empty folder. And now we should also download another program here to make this temporal kit extension work fine. Here we should also install EBSynth program. Okay, it is a free program. We just need to click on download, and that's it. After downloading EBSynth program, you will see this folder. You just need to click on it, and you should copy all these things here and put them in another folder. I create this folder in my desktop. It is EBSynth folder, and I put it all these things here. Okay, now I have this program, EBSynth beta program. Now what we will do, firstly, we have size parameter, height resolution, frames per key frame parameter, and frequency per second program parameter. And we have EBSynth mode. We just need to click on this EBSynth mode. And here we have target folder. We need to put the path to the target folder, which is the folder that we created previously, resulted video folder. We just need to copy its path, and we should put it here, and that's it. Now we just need to click on run to see the result, and here is the result. We have 4 frames. Here automatic 1111 took 4 frames from my video. We will call them keyframes. When we increase the number of sites, we will create an array of frames. This array, the size of this array is 3 times 3. It means that we have 9 keyframes inside this array. But now we need to also increase the height resolution, because as you know, we want to make each frame, the height of each frame equal to at least 512 to make sure that our Stable Diffusion model will work good on these keyframes. In this case, if the height resolution equal to 1024, so the height of each keyframe in our array will be equal to 1024 divided by 3, which is equal to 341. As you can see here, it is smaller than 512. To make the height of each frame in our array equal to 512, we should make the height resolution equal to 512 times 3, which is equal to 1536. Actually, this array, it is also an image. The height of this image, in this case, it is equal to 1024, and the width of this image, it is something larger than 1024, and this image, it is very large. The size of this image, it is very large, and we don't have enough space in our memory to work with this large image. But why we need to pass this large image through our Stable Diffusion model? Why don't just pass each keyframe individually? Because they found that when we put all these keyframes in just one image and pass it through our Stable Diffusion model, by doing this, all the keyframes that we will get from our Stable Diffusion model will have the same style. And this thing will make us avoid the flickering problem. And we will see that later. We can do that by changing the size parameter. We will reduce the size parameter, which means that we will reduce the keyframes. Now we will make slides equal to 2, and we will make the height resolution equal to 124. Let's click on run. Now we have 4 keyframes. The height of each keyframe now it is equal to 512, because the height of this large image, it is equal to 1024. So the height of each keyframe will be equal to 1024 divided by 2, which is equal to 512. If the memory of your GPU, it is 8 GB or more than that, so you can pass this large image through your Stable Diffusion model, but the memory of my GPU equal to 6 GB. So I should reduce the resolution of this large image to be able to pass it through my Stable Diffusion model. We will learn how to do that later. We have also this parameter, frames per keyframe. We will use this parameter to make sure that the last keyframe represents the last frame in our video. We just need to increase this one to make sure the last keyframe it is same as the last frame of our video. And at the same time, we should make these keyframes represent most of our video. They should represent most of the important thing that happened inside our video to make our EB synth work good. And here it is not a good idea to increase the number of keyframes, because when we increase the number of keyframes in our array and keeping the height resolution equal to 1024, it means that each keyframe will be very low resolution. And when you pass them through our Stable Diffusion model, you will not get good results. And when we increase the height resolution, the final image will be very large image, and we can't pass it through our Stable Diffusion model. So we can just change the value of frames per keyframe parameter to get good keyframes that represent the most important thing in our video. So here we will now change the number of keyframes. Now let's change the value of this parameter. Let's make it, for example, 20, and let's click on run. We should increase it again. We didn't reach the final frame. Let's make it 30, 60, like this. And again, let's increase it to make it 80. Until now we didn't reach the final frame. Let's make it 90. As you can see here, in 95 we lost one of these keyframes. So let's make it for example 90. Now here is the result. As you can see here, The hands here, they are not good. And as we said previously, we should make these keyframes good. So we should change frames per keyframe again. And I think the best value here it is 85. These keyframes will have all the important things that happened in our video. As you can see here, this one and this one, that's great. If the memory of your GPU is equal to 8 GB or more than that, so try to increase the number of keyframes to increase the chance that you will catch the most important thing that happened in your video. This thing will help EBSynth program. Now what we will do, we will click on Save Settings and we should click on Send to Image. Now let's open resulted video and you will see this folder, input folder. Inside this folder we have two images. We have these 4 images and we have this one here. This one, it is not important, you can delete it. We have this large image. Let's see the size of this image. The width of this image, it is equal to 1816, and the height of this image, it is equal to 1024. It is a very large image. We can't pass it directly through our Stable Diffusion model because we don't have enough space in our memory. So we will reduce the resolution of this image. We will divide the size of this image by 2. We will make this one equal to 908. Okay. We reduced the size or the width by 2. And we will make this one 512. And here we also reduced the height of our image by 2. I know here we reduced the size of each keyframe and the height of each keyframe now it is smaller than 512, which will affect on our Stable Diffusion model. Our Stable Diffusion model will not work very good, but what we will do actually, even if our Stable Diffusion model here didn't work good, we will do upscaling, and during upscaling we will try to, let's say, make the resulted images from our Stable Diffusion model better. Here I will use this prompt: digital painting, cyborg, man, best quality, masterpiece, detailed, 8K resolution. And here is my negative prompt: 3D cartoon enemy, sketches, worst quality, bad quality, child, cropped, etc. Okay. Now what we will do, we will specify the control nets that we will use. Let's use linear control net. Okay, let's click on enable. Let's make the weight of this equal to 0.6. Let's use another control net, for example canny control net. Let's click on enable. Let's make the weight of this equal to 0.6 also, and we will click on generate to see the results. And here's the result. As you can see here, all these keyframes have the same style. Here I reduced the denoising strength to 0.5 to make sure that I will get something similar to my face. And here's the result. As you can see here, that's great. Now let's fix the seed and let's do face restoration during generation. So we will click on restore faces. Let's click on generate. Now as you can see here, the faces are very good. Now what we will do, we will upscale this image. This image this large image. The size of this image, it is 908. The width of this image is 908, and the height of this image is 512. While in temporal kit, the height resolution equal to 1024. Okay, so what we will do, we will upscale this image by 2. How can we do that? We will use here tile control net, so we will click on tile. Okay, and we will go to scripts. We will click on ultimate SD upscale. Let's click on this target size type parameter, and we will click on select from image size. We will keep it 2. We will click on the upscaler that we want to use. We will use this one, and that's it. Here we sent our image, this image to image. Okay, and here we will click on generate, and now we will do upscaling. Now we increase the resolution of our image, but as you can see here, the style of each one of these keyframes, it is different from the others, and that's not good. So to reduce the difference, you just need to reduce the denoising strength to, let's say, 0.3, and let's click on generate again. Now these keyframes, they are better than the previous case, but we want to make the style even better. We want to make the style of each one of these keyframes similar to the other keyframes to avoid the flickering problem. And here I increased the tile size. As you can see here, I made the width equal to 908 and the height equal to 512. And this might help to make all the keyframes have the same style. And let's see the result. And here I made denoising strength equal to 0.1. Let's see the result. And here is our final result. All these images are good. All these keyframes are good. Now what we will do, actually the size of this image is 1024 times 1816, and that's good. It is similar to the size of this image here. And now what we should do, actually, we should save this image. We should click on save image as, and we should go to resulted video folder, and we should put it in output folder. We should change its name to input 0, and we should click on save. Now let's go to temporal kit, and now here we should put the path of our resulted video folder, which is this. Okay, this path, and we should click on read last settings, and it will automatically put our video here. And now we should click on prepare EB synth. Now you will see the frames of your video in this frames folder, and you will see 4 frames in this keys folder. These frames are the keyframes that we created previously. Okay, now what we will do, we will open EBSynth program. Here we have this folder, the EBSynth folder. Let's open it and let's click on ebsynth.exe. Now what we will do, we will put our keys folder and our frames folder. As you can see here, here's our key folder. Let's drag and drop it here in this place. And here we have frames folder. We will drag and put it here. And now we should click on run all like this. This EBSynth program will make our animation more smooth. And it will just use these 4 keyframes that we created previously to create the animation. And you will not see a lot of flickering in our animation. Now what we will do, we will click on Recombine EBSynth. And here we will generate our animation. Now let's download our animation. We just need to click on download. And here is our animation. That's really cool. Wow, that's amazing. And you can do more than that. Thanks for watching. Hi everyone. In this section, we will talk about CNC machine. We will use this CNC machine to convert the images that we generated previously using Stable Diffusion models into real paintings. Here we will use Totris CNC machine, which is this one here. The most important part in this machine is this part here, which will produce the laser to engrave or cut this plate here, which is a wooden plate. And we have many motors here. We call them stepper motors. We will use them to move this part here, right and left, and north and south. Okay, and we will use this part here to specify how much this laser producer should be above this plate. So now, how to use this thing here? If you want to just do engraving, at this case you should put your laser producer on this part here. You need to move it up, and after that move it down to touch this part here. Okay, at this case it will do engraving. If you wanted to move down in your plate by around 2 millimeters, you should make it touch this part here. Okay, if you wanted to remove around 4 millimeters, you should make it touch this part here. If you wanted to remove around 6 millimeters, you should make it touch this part here. Actually, we will make it touch this part here to do just engraving. Okay, it is actually easy to assemble this CNC machine. You just need to follow the guide. And you should know that this Totris company created an app for this CNC machine. You can download it on your smartphone easily. Firstly, this machine will create a network, a Wi-Fi network with a specific password name, and this application will try to connect to this network. By doing this, when you put an image in your mobile, you will be able to send it to this machine, and this machine will start painting this image on your plate. That's it. In the next video, we will learn how to use this CNC machine to convert our images to real paintings. Thanks for watching. Hi everyone, in this lecture we will learn how to engrave this image that I created using Stable Diffusion on my own notebook using our CNC machine. Firstly, we should send this image to our phone. Here is my phone, Galaxy J7 Prime. I just need to firstly copy this image, Ctrl C, and go back to this PC, and I should put it in somewhere in my phone, like in camera or screenshot, as you prefer. Just paste this image here, and that's it. And here is the application that I will use to control my CNC machine, but where you can find it and download it. If you are using Samsung phone, you just need to scan this QR code or write this link in your browser to be able to download this application. But if you are using iPhone, you will find it in App Store. Okay? You just need to write this name here, MKS Laser. Now, let's talk more about this guide here. Here in this guide, you will see many different things, like how to assemble this machine and how to do all this stuff. It is very easy guide. You can follow it step by step to be able to assemble and use the CNC machine. How to specify the level of your laser producer. Okay, we talked all about all these things in the previous lecture, and also how to use the application, the Android or iPhone application. They are the same actually. So now let's learn how to use this application. Here is our application. We have many things here. Firstly, we have the position of our laser producer in X and Y. At the beginning, it will be at the origin. The most important thing here is this part here, creation. Here you can draw your own painting, or you can load the images that you have in your gallery. Here we will use our image that we created using a Stable Diffusion model, so we don't need this. We should click on this symbol here, this button, and click on allow. You can choose photos or gallery, it's up to you. Now we will select our image, which is this one here, and here is our image. That's amazing. You can control many things here, like the brightness. Okay, and we have also contrast. You can change it as you want. You can also change the style of this image. Let's click on sketch. Here we change the style of the image. Now let's click on this symbol here. Now, before doing anything, we have many things that we need to set. Firstly, we should specify the size of our image that we want to engrave on our notebook. Here in this case, it is 5 centimeters times 5 centimeters. 5 centimeters width and 5 centimeters height. So if you want to change them, you can change them from here. It will automatically take care of the aspect ratio, so you don't need to care about it. You can also specify the laser power and the speed of your machine. Okay, let's make it, for example, 300. You should try many different values to find the best. And after that, to set the position of your notebook in correct way. So firstly, you should put your laser above your notebook and click on this symbol here to know the region that this laser producer will work on. Okay, at this case you can fit the position of your notebook to make sure that all the image inside your notebook. Okay, that's it. Now we will learn how to connect this application with our CNC machine. Firstly, we need to turn on our CNC machine, and after that we should connect this application, this mobile, this phone, with our CNC machine. Here's the machine. I connected it to the power. Okay, here you should wear these goggles that you will get with your machine, because the laser will hurt your eyes if you don't do that. Okay, now we should go to internet, and here we will see laser 40096. Here we should connect to this network. Okay, actually you will find the password of this network in the guide also. It is in this case from 1 to 8. Now we should go back to our app. Let's click on this symbol here. As you can see here, we should also connect in this app. Let's go back. Let's click on this symbol here. And here we should put the IP of our CNC machine. You will find it also in the guide, in app connection section. In our case, it is this one here. Let's click on connect. Okay, now our application connected to our CNC machine. That's great. Let's go back to creation. Let's go back to creation. Again, let's load our image. Let's select sketch. Let's reduce this one to this value. Okay, and let's move down and let's increase this one a little bit, and this one let's reduce it. Change it as you want. And now let's go to the final step. Now if I want to know what is the region that our laser producer will work on, I just need to click on this symbol here, and I will see the region that our laser producer will work on. Okay, now what I should do, actually, I will engrave on this notebook, so I need to move this laser producer up and down until specifying the correct level of this laser producer to do engraving. Here's what I will use to set the level of this laser producer. I should put it here, okay, like this. And to move this laser producer down, we just need to rotate this part here, okay, and move it down like what we did previously. We should make it touch the first circle, and that's it. Now we should tighten it again. That's right. Okay. Now let's again specifying the region that our laser producer will work on to make the image in the center of our notebook. Let's see that. It is not at the center, we just need to move it until make the image in the center. I think we should also increase the size. Let's make it, for example, 660 millimeters, which means 6 centimeters width and height. After testing, I realized that the best width and height should be equal to 80. Let's click on engrave, and it will start engraving. We should click on confirm, and that's it. As you can see here, now our machine works. It will take some time until finishing engraving our AI generated image on our notebook. Here is the result. It is not that good, actually, so let's try to change the settings to make it better. Okay, let's for example change the power to, for example, 50. Okay, it is a very small value. Here I made the size equal to 100 times 100 millimeters and the laser power equal to 50, which is a very small value. Let's try to do engraving. Here, as I can see, the machine, the CNC machine, is not able to engrave anything on my notebook with 50 laser power. So let's stop the engraving and increase the power to, let's say, for example, 100. And again, if our laser machine didn't able to engrave anything, we should increase the power, and so on. And here is the result. As you can see, it is good in some way, right? But we need to do more refining to get the best results, actually. Now look at this one here. I increased the brightness. As you can see here, there are more details in this engraving compared to this one, actually. And now what I did, I added my image to this website, DataChef, which will convert my image into line drawing, which will make things easier for my CNC machine to understand this image by just focusing on the outlines. And here we can change the settings. You can choose, for example, pencil, colored pencil, fine pen, smooth pen, vector graphics, smooth pen, or let's use pencil. And here's the result. That's good, actually. Now we should send it to our phone and do the same thing. And here's the final result. It is better than what it was previously, actually, but we can make it even better by testing many different level of laser power and brightness, etc. You should also focus on the contrast. It is also a very important parameter to make the details appear. Now let's do another test. Now we will engrave this image that generated using Stable Diffusion on our notebook. Okay? Actually, here I downloaded this image on my phone and did all what we learned previously. And here is the final result, which is amazing, right? It's really amazing. Okay? I think that when we slow the process of engraving, the results will be high resolution or something like that. But even with this speed, the results are good. Thanks for watching.
In this video, we will see how we can get the highest and the lowest value in an array. Okay, so in this array, we've declared integer numbers equals 2, 6, 10, 12, 15, 17, 1. So we can check this values. You can see the last one is the lowest one actually. So there's the highest value, 17, and the lowest one will be the 1. But let's say it's an array that you won't see in front of you. So you need to be able to do this in coding to run through every value and check the value and get the lowest or the highest value. So let's start with the highest quickly, and basically the logic behind it both works exactly the same way. So in order for me to get the highest value, I'm going to declare a variable called highest, and you can see it's the same type as the array, in this case an integer. And I'm going to set numbers at position 0 to the highest value. So I'm going to assume 2 here, or the value in that position, not necessarily a 2. In this case, it is a 2. So the 2 will basically then be set to the highest value. And now I can use a for loop, and I'm going to start the I now at 1. Because the reason for that is to check highest, which is 2, with the 2 itself there, doesn't make sense. So instead of starting the loop at 0, I will start comparing from the 6. So I'm going to take the first value as being the highest. Then I'm going to check, is 6 higher than this highest number that I had, which is the 2? And yes, it is. So I will change or put the 6 into highest. And then I'm going to compare the 6 with the 10 and say, okay, 10 is now higher than 6. So I'm going to put the 6 into highest. And then I'm going to put the 12 into highest, and then to 15 into highest. And at the end, we're going to say 17 should be placed in highest. And when I compare the 17 with the 1, I will not replace it, and you will have the highest value. Okay, so essentially, same thing. We're going to go to numbers dot length there, which will give me the length, and then I++. Okay, so this is very important. This for loop, we start at 1. You can start it at 0, but it's senseless to actually compare the 2 with the 2 itself. Okay, so we're going to start at I equals 1, and then what we do inside of this loop is just to go and compare if numbers at position I is greater than the highest value that we saved, then that one which is greater than the highest should become the highest. So we're going to say equals numbers at position I. And now after this, it will run through every element, check every element with what you saved in highest. If it's greater than the one that you saved in highest, then we will save it in highest again before we compare the rest. So this is the way how you compare to get the highest value in your specific array. So let's just print out the highest value. The highest value is, and let's print out the variable there called highest. So let's run this one quickly. We'll actually run it from here. So you can see there, still running the other one. Let's run it from here. It will say the highest value is 17. So the highest value, 17, is that correct? Yes, it is. Let's change that 10 there to a 20. So it will then tell us, well, the highest value is 20. So it doesn't matter which value you put there or which position you put the highest value, it will pick up the highest value. Now the exact same thing for the lowest one. Let's use the same array again, numbers. And now instead of declaring highest there, we're going to declare lowest. And we're going to set the lowest to numbers at position 0. So you can see it's essentially doing the same thing. It's just another variable there. So now we use the same for loop again. Also integer I starting from 1. I less than numbers dot length. Same as the other for loop. Exactly the same way. And now instead of having the if statement where I'm comparing where numbers is higher than highest, I'll just compare saying where numbers is less than the lowest. So we're going to say if numbers at the specific position is less than lowest, then lowest should get this new numbers at position I. So it's essentially saying the same thing there, but now I'm comparing for lower than lowest instead of higher than highest. Okay, and then lowest will get the new value, and we can print it out again by just saying system out print line, the lowest value is, and then we print out the variable called lowest. Okay, so if we run this again, we'll get the highest and the lowest value. You can see the highest value there is 20 and the lowest value is 1. Now let's go back to the array, and you can see there that the lowest value is in fact a 1 and the highest one is 20. So let's just change it again. Let's make this one a 35 and we make this one a -1 and run it again. And you'll see that your new values will be 35 and -1. Okay, so this is getting the highest and the lowest values from an array. Another very useful calculation that we can use on arrays is to get the sum and the average of values. So obviously by getting the average of a value you need the sum, because the average would be the sum of all values, divided by the number of values. That's essentially the average. So in order for you to get the average, you need to get the sum of all the values. And the sum of all the values divided by the number of values will give you your average. Okay, so now in this case, let's just take it easy values, 1, 2, and 3, and we're going to work out what is the sum of these divided by the number of to get the average. So this one is easy. It's 3 plus 2 is 5 plus 1 is 6. 6 divided by 3 values will give you an average of 2. So now, in order for us to work out the sum here, we will need a sum variable. So I'm going to say sum equals 0, just to start off the sum at 0, and then I'm going to add to the sum the 1, the 2, and the 3 to get the sum of all. So I'm going to use the for loop again, integer I equals 0, because now we're going to start at, and we want to read every single value. So I'm going to start at 0, I less than values, that's the name of the array, dot length, and that will give me a loop that will go through every single element in that array. And now every time we run through the array, we want to add to the sum variable. So I will say sum equals sum plus the value that we're going to read from the array. So it will be values at the specific position called I. So what we're going to do, the first time the loop runs, values I will return there the 1 because I will be at 0. So the 1 will be taken as 0, what it is at the beginning, plus 1, and that will be saved to sum. So now sum will be 1. Then when it runs again, values I will be now going to position 1, which is 2. And now the previous value of sum, which was a 1 plus 2, gives me a 3. And then we add the 3. 3 plus 3 gives me 6. So you can see that we have a running total here again, and this running total is called sum. So a shorter way of doing this whole thing will just be to say plus equals values. That's the same as saying sum equals sum plus values I. So now we've got the sum after this for loop. Do we know how many values there are? The values will be, or the number of values will be just the length of the array. So that's easy one. So let's work out the average quickly. So I'm going to say double average equals, now the average will be the sum divided by the number of values. And the number of values will be values dot length. Okay, now just remember this again. We've got integer division here because sum is declared as an integer and values.length returns an integer, which means that we've got integer division here again. So if you have integer division, make sure that you cast one of the sides to a double. So let's say the sum in this case is 6. By casting it to a double, it will become 6.0, and then we don't have integer division anymore, where it throws away the decimal part. So now we can print out to the screen the sum is, and then show the sum. And we can also print out the average is, and then just print out the average. Okay, so let's run this quickly and see what's the output. Actually, I should run it from here again. So I'm going to run it there. Let's just run it quickly and see what's the output there. And you can see there that the sum is 6. 3 plus 2 plus 1 equals 6. And the average is 2. So it's 6 divided by 3, which will give you an average of 2. And this is how you work out the sum and the average.